Section 51 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, InterfaceAudio.com. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 3. The Progress of Scientific Chemistry in France, Part 8. The history of the Institute of Egypt, as related by Cuvier, is not a little singular, and deserves to be stated. Bonaparte, during his occasional intercourse with Berthollet in Italy, was delighted with the simplicity of his manners, joined to a force and depth of thinking which he soon perceived to characterize our chemist. When he returned to Paris, where he enjoyed some months of comparative leisure, he resolved to employ his spare time in studying chemistry under Berthollet. It was at this period that his illustrious pupil imparted to our philosopher his intended expedition to Egypt, of which no whisper was to be spread abroad till the blow was ready to fall, and he begged of him not merely to accompany the army himself, but to choose such men of talent and experience as he conceived fitted to find there an employment worthy of the country which they visited, and of that which sent them forth. To invite men to a hazardous expedition, the nature and destination of which he was not permitted to disclose, was rather a delicate task, yet Berthollet undertook it. He could simply inform them that he would himself accompany them, yet such was the universal esteem in which he was held, such was the confidence universally placed in his honesty and integrity, that all the men of science agreed at once, and without hesitation, to embark on an unknown expedition, the dangers of which he was to share along with them. Had it not been for the link which Berthollet supplied between the commander-in-chief and the men of science, it would have been impossible to have united, as was done on this occasion, the advancement of knowledge with the progress of the French arms. During the whole of this expedition, Berthollet and Monge distinguished themselves by their firm friendship, and by their mutually braving every danger to which any of the common soldiers could be exposed. Indeed, so intimate was their association, that many of the army conceived Berthollet and Monge to be one individual, and it is no small proof of the intimacy of these philosophers with Bonaparte, that the soldiers had a dislike at this double personage, from a persuasion that it had been at his suggestion that they were led into a country which they detested. It happened on one occasion that a boat in which Berthollet and some others were conveyed up the Nile was assailed by a troop of Mamelukes, who poured their small shot into it from the banks. In the midst of this perilous voyage, M. Berthollet began very coolly to pick up stones and stuff his pockets with them. When his motive from this conduct was asked, "I am desirous," said he, "that in case of my being shot, my body may sink at once to the bottom of the river, and may escape the insults of these barbarians." In a conjuncture where a courage of rarer kind was required, Berthollet was not found wanting. The plague broke out in the French army, and this added to the many fatigues they had previously endured. The diseases under which they were already laboring would, it was feared, lead to insurrection on the one hand, or totally sink the spirits of the men on the other. Acre had been besieged for many weeks in vain. Bonaparte and his army had been able to accomplish nothing against it. He was anxious to conceal from his army this disastrous intelligence. When the opinion of Berthollet was asked in council, he spoke at once the plain though unwelcome truth. He was instantly assailed by the most violent reproaches. "In a week," said he, "my opinion will be unfortunately but too well vindicated." It was as he foretold, and when nothing but a hasty retreat could save the wretched remains of the army of Egypt, the carriage of Berthollet was seized for the convenience of some wounded officers. On this he travelled on foot, and without the smallest discomposure, across 20 leagues of the desert. When Napoleon abandoned the army of Egypt, and traversed half the Mediterranean in a single vessel, Berthollet was his companion. After he had put himself at the head of the French government, and had acquired an extent of power which no modern European potentate had ever before realized, he never forgot his associate. He was in the habit of placing all chemical discoveries to his account, to the frequent annoyance of our chemist, and when an unsatisfactory answer was given him upon any scientific subject, he was in the habit of saying, "Well, I shall ask this of Berthollet." But he did not limit his affection to these proofs of regard. Having been informed that Berthollet's earnest pursuits of science had led him into expenses which had considerably deranged his fortune, he sent for him, and said in a tone of affectionate reproach, "Monsieur Berthollet, I have always 100,000 crowns at the service of my friends," and in fact this sum was immediately presented to him. Upon his return from Egypt, Berthollet was nominated as senator by the first consul, and afterwards received the distinction of Grand Officer of the Legion of Honor, Grand Cross of the Order of Reunion, titulary of the Senatory of Montpellier, and under the Emperor he was created a peer of France, receiving the title of Count. The advancement of these offices produced no change in the manners of Berthollet. Of this he gave a striking proof by adopting his armorial bearing, at the time that others eagerly blazoned some exploit, the plain unadorned figure of his faithful and affectionate dog. He was no courtier before he received these honours, and he remained equally simple and unassuming, and not less devoted to science after they were conferred. As we advance toward the latter period of his life, we find the same ardent zeal in the cause of science which he had glowed in his early youth, accompanied by the same generous warmth of heart that he ever possessed, and which displayed itself in his many intimate friendships still subsisting, though mellowed by the hand of time. At this period Laplace lived at Arcueil, a small village about 3 miles from Paris. Between him and Berthollet there had long subsisted a warm affection, founded on mutual esteem. To be near this illustrious man, Berthollet purchased a county seat in the village. There he established a very complete laboratory, fit for conducting all kinds of experiments in every branch of natural philosophy. Here he collected round him a number of distinguished young men, who knew that in his house their ardour would at once receive fresh impulse and direction from the example of Berthollet. These youthful philosophers were organized by him into a society, to which the name Société d'Arcueil was given. M. Berthollet was himself the president, and the other members were Laplace, Biot, Gay-Lussac, Thenard, Collet d'Escotils, de Candolle, Humboldt, and A.B. Berthollet. This society published 3 volumes of very valuable memoirs. The energy of this society was unfortunately paralyzed by an untoward event, which embittered the latter days of this amiable man. His only son, M.A.B. Berthollet, in whom his happiness was wrapped up, was unfortunately afflicted with a lowness of spirits which rendered his life wholly insupportable to him. Retiring to a small room, he locked the door, closed up every chink and crevice which might admit the air, carried writing materials to a table on which he placed a second watch, and then seated himself before it. He now marked precisely the hour, and lighted a brazier of charcoal beside him. He continued to note down the series of sensations he then experienced in succession, detailing the approach and rapid progress of delirium, until, as time went on, the writing became confused and illegible, and the young victim dropped dead upon the floor. After this event, the spirits of the old man never again rose. Occasionally some discovery, extending the limits of his favorite science, engrossed his interest and attention for a short time, but such intervals were rare and short-lived. The restoration of the Bourbons and the downfall of his friend and patron Napoleon added to his sufferings by diminishing his income and reducing him from a state of affluence to comparative embarrassment. But he was now old, and the end of his life was approaching. In 1822 he was attacked by a slight fever, which left behind it a number of boils. These were soon followed by a gangrenous ulcer of uncommon size. Under this he suffered for several months with surprising fortitude. He himself, as a physician, knew the extent of his danger, felt the inevitable progress of the malady, and calmly regarded the slow approach of death. At length, after a tedious period of suffering, in which his equanimity had never once been shaken, he died on the 6th of November, when he had nearly completed the 74th year of his age. His papers are exceedingly numerous, and of a very miscellaneous nature, amounting to more than 80. The earlier were chiefly inserted into the various volumes of the Memoirs of the Academy. He furnished many papers to the Analyse de Chimie and the Journal de Physique, and was also a frequent contributor to the Society of Arcueil, in the different volumes of whose transactions several memoirs of his are to be found. He was the author likewise of 2 separate works, comprising each 2 octavo volumes. These were his Elements of the Art of Dying, first published in 1791, in a single volume. But the new and enlarged edition of 1814 was in 2 volumes, and his Essay on Chemical Statics, published about the beginning of the present century. I shall notice his most important papers. His earlier memoirs on sulphurous acid, on volatile alkali, and on the decomposition of nitre, were encumbered by the phlogistic theory, which at that time he defended with great zeal, though he afterwards retracted these his first opinions upon all these subjects. Except his paper on soaps, in which he shows that they are chemical compounds of an oil, acting the part of an acid, and an alkaline base, and his proof that phosphoric acid exists ready formed in the body, and a fact long before demonstrated by Gahn and Scheele. His papers published before he became an anti-phlogistian are of inferior merit. In 1785 he demonstrated the nature and proportion of the constituents of ammonia, or volatile alkali. This substance had been collected in the gaseous form by the indefatigable Priestley, who had shown also that when electric sparks are made to pass for some time through a given volume of this gas, its bulk nearly doubled. Berthollet merely repeated this experiment of Priestley, and analyzed the new gases evolved by the action of electricity. This gas he found a mixture of 3 volumes hydrogen and 1 volume azotic gas. Hence it was evident that ammoniacal gas is a compound of 3 volumes of hydrogen and 1 volume of azotic gas united together, and condensed into 2 volumes. The same discovery was made about the same time by Dr. Austin, and published in the Philosophical Transactions. Both sets of experiments were made without any knowledge of what was done by the other, but it is admitted on all hands that Berthollet had the priority in point of time. It was about this time, likewise, that he published his first paper on chlorine. He observed that when water impregnated with chlorine is exposed to the light of the sun, the water loses its color, while at the same time a quantity of oxygen gas is given out. If we now examine the water, we find that it contains no chlorine, but merely a little muriatic acid. This fact, which is undoubted, led him to conclude that chlorine is decomposed by the action of solar light, and that its 2 elements are muriatic acid and oxygen. This led to the notion that the basis of muriatic acid is capable of combining with various doses of oxygen, and of forming various acids, one of which is chlorine. On that account it is called oxygenized muriatic acid by the French chemists, which unwieldy appellation was afterwards shortened by Kirwan into oxymuriatic acid. Berthollet observed that when a current of chlorine gas is passed through a solution of carbonate of potash, an effervescence takes place owing to the disengagement of carbonic acid gas. By and by crystals are deposited in fine silky scales, which possess the property of detonating with combustible bodies still more violently than saltpetre. Berthollet examined these crystals, and showed that they were compounds of potash with an acid containing much more oxygen than oxymuriatic acid. He considered its basis as muriatic acid, and distinguished it by the name of hyperoxymuriatic acid. It was not till the year 1810 that the inaccuracy of these opinions was established. Gay-Lussac and Thenard attempted in vain to extract oxygen from chlorine. They showed that not a trace of that principle could be detected. Next year Davy took up the subject, and concluded from his experiments that chlorine is a simple substance, that muriatic acid is a compound of chlorine and hydrogen, and that hyperoxymuriatic acid of chlorine and oxygen. Gay-Lussac obtained this acid in a separate state, and gave it the name of chloric acid, by which it is now known. Scheele, in his original experiments on chlorine, had noticed the property which it has of destroying vegetable colors. Berthollet examined the property with care, and found it so remarkable that he proposed it as a substitute for exposure to the sun in bleaching. This suggestion alone would have immortalized Berthollet had he done nothing else, since its effect upon some of the most important of the manufactures of Great Britain has been scarcely inferior to that of the steam engine itself. Mr. Watt happened to be in Paris when the idea suggested itself to Berthollet. He not only communicated it to Mr. Watt, but showed him the process in all its simplicity. It consisted in nothing else than in steeping the cloth to be bleached in water impregnated with chlorine gas. Mr. Watt, on his return to Great Britain, prepared a quantity of this liquor, and sent it to his father-in-law, Mr. Macgregor, who was a bleacher in the neighbourhood of Glasgow. He employed it successfully, and thus was the first individual who tried the new process of bleaching in Great Britain. For a number of years the bleachers in Lancashire and the neighbourhood of Glasgow were occupied in bringing the process to perfection. The disagreeable smell of the chlorine was a great annoyance. This was attempted to be got rid of by dissolving potash in the water to be impregnated with chlorine, but it was found to injure considerably the bleaching powers of the gas. The next method tried was to mix the water with quicklime, and then to pass a current of chlorine through it. The quicklime was dissolved, and the liquor thus constituted was found to answer very well. The last improvement was to combine the chlorine with dry lime. At first 2 atoms of lime were united to 1 atom of chlorine, but of late years it is a compound of 1 atom of lime and 1 of chlorine. This chloride is simply dissolved in water, and the cloth to be bleached is steeped in it. For all these improvements, which have brought the method of bleaching by means of chlorine to great simplicity and perfection, the bleachers are indebted to Knox, Tennant, and Mackintosh of Glasgow, by whose indefatigable exertions the mode of manufacturing chloride of lime has been brought to the state of perfection. Berthollet's experiments on prussic acid and the prussiates deserves also to be mentioned as having a tendency to rectify some of the ideas at that time entertained by chemists, and to advance their knowledge of one of the most difficult departments of chemical investigation. In consequence of his experiments on the nature and constituents of sulphuretted hydrogen, he had already concluded that it was an acid, and that it was destitute of oxygen. This had induced him to refuse his assent to the hypothesis of Lavoisier that oxygen is the acidifying principle. Scheele, in his celebrated experiments on prussic acid, had succeeded in ascertaining that its constituents were carbon and azote, but he had not been able to make a rigid analysis of that acid, and consequently to demonstrate that oxygen did not enter into it as a constituent. Berthollet took up the subject, and though his analysis was also incomplete, he satisfied himself, and rendered it exceedingly probable, that the only constituents of this acid were carbon, azote, and hydrogen, and that oxygen did not enter into it as a constituent. This was another reason for rejecting the notion of oxygen as an acidifying principle. Here were two acids capable of neutralizing bases, namely sulfuretted hydrogen and prussic acid, and yet neither of them contained oxygen. He found that when prussic acid was treated with chlorine, its properties were altered. It acquired a different smell and taste, and no longer precipitated iron blue, but green. From his opinion respecting the nature of chlorine, that it was a compound of muriatic acid and oxygen, he naturally concluded that by this process he had formed a new prussic acid by adding oxygen to the old constituents. He therefore called this new substance oxyprussic acid. It has been proved by the more recent experiments of Gay-Lussac that the new acid of Berthollet is a compound of cyanogen, the prussic acid deprived of hydrogen, and chlorine. It is now called chlorocyanic acid, and is known to possess the characters assigned it by Berthollet. It constitutes, therefore, a new example of an acid destitute of oxygen. Berthollet was the first person who obtained prussiate of potash in regular crystals. The salt was known long before, but had always been used in a state of solution. Berthollet's discovery of fulminating silver, and his method of obtaining pure hydrated potash and soda by means of alcohol, deserve to be mentioned. This last process was of considerable importance to analytical chemistry. Before he published his process, these substances in a state of purity were not known. I think it unnecessary to enter into any details respecting his experiments on sulfuretted hydrogen, and the hydrosulfurates and sulfurates. They contributed essentially to elucidate that obscure part of chemistry. But his success was not perfect, nor did we understand completely the nature of these compounds, till the nature of the alkaline bases had been explained by the discoveries of Davy. End of section 51. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 52 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 3. Progress of Scientific Chemistry in France. Part 9. The only other work of Berthollet which I think it is necessary to notice here is his book entitled Chemical Statics, which he published in 1803. He had previously drawn up some interesting papers on the subject, which were published in the Memoirs of the Institute. Though chemical affinity constitutes confessedly the basis of the science, it had been almost completely overlooked by Lavoisier, who had done nothing more on the subject than drawn up some tables of affinity, founded on very imperfect data. Morveau had attempted a more profound investigation of the subject in the article Affinité, inserted in the chemical part of the Encyclopédie Méthodique. His object was, in imitation of Buffon, who had preceded him in the same investigation, to prove that chemical affinity is merely a case of the attraction of gravitation. But it is beyond our reach in the present state of our knowledge to determine the amount of attraction which the atoms of bodies exert with respect to each other. This was seen by Newton, and also by Bergman, who satisfied themselves with considering it as an attraction, without attempting to determine its amount, though Newton, with his usual sagacity, was inclined, from the phenomena of light, to consider the attraction of affinity as much stronger than that of gravitation, or at least as increasing much more rapidly as the distances between the attracting particles diminished. Bergman, who had paid great attention to the subject, considered affinity as a certain determinate attraction, which the atoms of different bodies exerted towards each other. This attraction varies in intensity between every two bodies, though it is constant between each pair. The consequence is that these intensities may be denoted by numbers. Thus, suppose a body, M, and the atoms of 6 other bodies, A, B, C, D, E, and F, to have an affinity for M. The forces by which they are attracted towards each other may be represented by the numbers x, x plus 1, x plus 2, x plus 3, x plus 4, x plus 5, and the attractions may be represented thus. Attraction between M and A equal x, M and B equal x plus 1, M and C equal x plus 2, M and D equals x plus 3, M and E equals x plus 4, M and F equals x plus 5. Suppose we have the compound Ma. If we present B, it will unite with M and displace A, because the attraction between M and A is only x, while that between M and B is x plus 1. C will displace B, D will displace C, and so on for the same reason. On this account, Bergman considered affinity as an elective attraction, and in his opinion, the intensity may always be estimated by decomposition. That substance which displaces another from a third has a greater affinity than the body which is displaced. If B displace A from the compound AM, then B has a greater affinity for M than A has. The object of Berthollet in his chemical statics was to combat this opinion of Bergman, which had been embraced without examination by chemists in general. If affinity be an attraction, Berthollet considered it as evident that it never could occasion decomposition. Suppose A to have an affinity for M and B to have an affinity for the same substances. Let the affinity between B and M be greater between AM. Let B mixed with a solution of the compound AM, then in that case B would unite with AM and form the triple compound AMB. Both A and B would at once unite with M. No reason can be assigned why A should separate from M and B take its place. Berthollet admitted that in fact such decompositions often happened, but he accounted for them from other causes, and not from the superior affinity of one body over another. Suppose we have a solution of sulfate of soda in water. This salt is a compound of sulfuric acid and soda, two substances between which a strong affinity subsists, and which therefore always unites whenever they come in contact. Suppose we have dissolved in another portion of water a quantity of barytes, just sufficient to saturate the sulfuric acid in the sulfate of soda. If we mix these two solutions together, the barytes will combine with the sulfuric acid, and the compound, sulfate of barytes, will fall to the bottom, leaving a pure solution of soda in the water. In this case, the barytes has seized all the sulfuric acid and displaced the soda. The reason of this, according to Berthollet, is not that barytes has a stronger affinity for sulfuric acid than soda does, but because sulfate of barytes is insoluble in water. It therefore falls down, and of course the sulfuric acid is withdrawn from the soda. But if we add to a solution of sulfate of soda as much potash as will saturate all the sulfuric acid, no such decomposition will take place. At least we have no evidence that it does. Both the alkalis in this case will unite to the acid and form a triple compound, consisting of potash, sulfuric acid, and soda. Let us now concentrate the solution by evaporation, and crystals of sulfate of potash will fall down. The reason is that sulfate of potash is not nearly so soluble in water as sulfate of soda. Hence it separates, not because sulfuric acid has a greater affinity for potash than for soda, but because sulfate of potash is a much less soluble salt than sulfate of soda. This mode of reasoning of Berthollet is plausible but not convincing. It is merely an argumentum ad ignorantium. We can only prove the decomposition by separating the salts from each other, and this can only be done by their difference of solubility. But cases occur in which we can judge that decomposition has taken place from some other phenomena than precipitation. For example, nitrate of copper is a blue salt, while muriate of copper is green. If into a solution of nitrate of copper we pour muriatic acid, no precipitation appears, but the color changes from blue to green. Is not this an evidence that the muriatic acid has displaced the nitric, and that the salt held in solution is not nitrate of copper, as it was at first, but muriate of copper? Berthollet accounts for all decompositions which take place when a third body is added, either by insolubility or by elasticity, as, for example, when sulfuric acid is poured into a solution of carbonate of ammonia. The carbonic acid all flies off in consequence of its elasticity, and the sulfuric acid combines with the ammonia in its place. I confess that this explanation of the reason why the carbonic acid flies off appears to me very defective. The ammonia and carbonic acid are united by a force quite sufficient to overcome the elasticity of the carbonic acid. Accordingly, it exhibits no tendency to escape. Now, why should the elasticity of the acid cause it to escape when sulfuric acid is added? It certainly could not do so, unless it has weakened the affinity by which it is kept united to the ammonia. Now, this is the very point for which Bergman contends. The subject will claim our attention afterwards, when we come to the electrochemical discoveries, which distinguished the first 10 years of the present century. Another opinion supported by Berthollet in his chemical statics is that quantity may be made to overcome force, or, in other words, that if we mix a great quantity of a substance which has a weaker affinity with a small quantity of a substance which has a stronger affinity, the body having the weaker affinity will be able to overcome the other, and combine with a third body in place of it. He gave a number of instances of this. Particularly, he showed that a large quantity of potash, when mixed with a small quantity of sulfate of barytes, is able to deprive the barytes of a portion of its sulfuric acid. In this way he accounted for the decomposition of the common salt by carbonate of lime in the soda lakes in Egypt, and the decomposition of the same salt by iron, as noticed by Scheele. I must acknowledge myself not quite satisfied with Berthollet's reasoning on this subject. No doubt if two atoms of a body having a weaker affinity, and one atom of a body having a stronger affinity, were placed at equal distance from an atom of a third body, the force of the two atoms might overcome that of the one atom. And it is possible that such cases may occasionally occur. But such a balance of distances must be rare and accidental. I cannot think that all the cases adduced by Berthollet are of a complicated nature, and admit of an explanation independent of the efficacy of mass. And at any rate, abundance of instances might be stated in which mass appears to have no preponderating effect whatever. Chemical decomposition is a phenomenon of so complicated a nature that it is more than doubtful whether we are yet in possession of data sufficient to enable us to analyze the process with accuracy. Another opinion brought forward by Berthollet in his work was of a startling nature, and occasioned a controversy between him and Proust, which was carried on for some years with great spirit, but with perfect decorum and good manners on both sides. Berthollet affirmed that bodies were capable of uniting with each other in all possible proportions, and that there is no such thing as a definite compound, unless it has been produced by some accidental circumstances, as insolubility, volatility, etc. Thus every metal is capable of uniting with all possible doses of oxygen, so that instead of one or two oxides of every metal, an infinite number of oxides of each metal exist. Proust affirmed that all compounds are definite. Iron, says he, unites with oxygen only in two proportions. We have either a compound of 3.5 iron and 1 oxygen, or of 3.5 iron and 1 to 5 oxygen. The first constitutes the black, and the second the red oxide of iron, and besides these there is no other. Every one is now satisfied that Proust's view of the subject was correct, and Berthollet's erroneous. But a better opportunity will occur hereafter to explain this subject, or at least give the information respecting it, which we at present possess. Berthollet in this book points out the quantity of each base necessary to neutralize a given weight of acid, and he considers the strength of affinity as inversely that quantity. Now, of all the bases known when Berthollet wrote, ammonia is capable of saturating the greatest quantity of acid. Hence he considered its affinity for acids as stronger than that of any other base. Barytes, on the contrary, saturates the smallest quantity of acid. Therefore its affinity for acids is smallest. Now ammonia is separated from acids by all the other bases, while there is not one capable of separating barytes. It is surprising that the notoriety of this fact did not induce him to hesitate before he came to so problematical a conclusion. Mr. Kirwan had already considered the force of affinity as directly proportional to the quantity of base necessary to saturate a given weight of acid. When we consider the subject metaphysically, Berthollet's opinion is most plausible, for it is surely natural to consider that body as the strongest which produces the greatest effect. Now, when we deprive an acid of its properties, or neutralize it by adding a base, one would be disposed to consider that base as acting with most energy, which with the smallest quantity of matter is capable of producing a given effect. This was the way Berthollet reasoned. But if we attend to the power which one base has of displacing another, we shall find it nearly proportional to the weight of it necessary to saturate a given weight of acid, or at least those bases act most powerfully in displacing others, of which the greatest quantity is necessary to saturate a given weight of acid. Kirwan's opinion, therefore, was more conformable to the order of decomposition. These two opposite views of the subject show clearly that neither Kirwan nor Berthollet had the smallest conception of the atomic theory, and consequently that the allegation of Mr. Higgins, that he had explained the atomic theory in his book on phlogiston, published in the year 1789, was not well founded. Whether Berthollet had read that book I do not know, but there can be no doubt that it was perused by Kirwan, who, however, did not receive from it the smallest notions respecting the atomic theory. Had he imbibed any such notions, he never would have considered chemical affinity as capable of being measured by the weight of base capable of neutralizing a given weight of acid. Berthollet was not only a man of great energy of character, but of the most liberal feelings and benevolence. The only exception to this is his treatment of M. Clement. This gentleman, in company with M. Desaulniers, had examined the carbonic acid of Priestley, and had shown, as Cruikshanks had done before him, that it is a compound of carbon and oxygen, and that it contains no hydrogen whatever. Berthollet examined that same gas, and he published a paper to prove that it was a triple compound of oxygen, carbon, and hydrogen. This occasioned a controversy, which chemists have finally determined in favor of the opinion of Clement and Desaulniers. Berthollet, during this discussion, did not on every occasion treat his opponents with his accustomed temper and liberality, and ever after he opposed all attempts on the part of Clement to be admitted a member of the Institute. Whether there was any other reason for this conduct on the part of Berthollet, besides a difference of opinion respecting the composition of carbonic oxide, I do not know, nor would it be right to condemn him without a more exact knowledge of all the circumstances that I can pretend to. Antoine François de Fourcroy was born at Paris on the 15th of June, 1755. His family had long resided in the capital, and several of his ancestors had distinguished themselves at the bar. But the branch from which he sprung had gradually sunk into poverty. His father exercised in Paris the trade of an apothecary, in consequence of a charge which he held in the house of the Duke of Orleans. The corporation of apothecaries having obtained the general suppression of all such charges, M. de Fourcroy, the father, was obliged to renounce his mode of livelihood, and his son grew up in the midst of the poverty produced by the monopoly of the privileged bodies in Paris. He felt this situation the more keenly, because he possessed from nature an extreme sensibility of temper. When he lost his mother at the age of 7 years, he attempted to throw himself into her grave. The care of an elder sister preserved him with difficulty till he reached the age at which it was usual to be sent to college. There he was unlucky enough to meet with a brutal master, who conceived an aversion for him, and treated him with cruelty. The consequence was a dislike to study, and he quitted the college at the age of 14, somewhat less informed than when he went to it. His poverty now was such that he was obliged to endeavour to support himself by becoming writing-master. He had even some thoughts of going on the stage, but was prevented by the hisses bestowed on a friend of his who had unadvisedly entered upon that perilous career, and was treated in consequence without mercy by the audience. While uncertain what plan to follow, the advice of Vicar d'Azyr induced him to commence the study of medicine. This great anatomist was an acquaintance of M. de Fourcroy the father. Struck with the appearance of his son, and the courage with which he struggled with his bad fortune, he conceived an affection for him, and promised to direct his studies, and even to assist him during their progress. The study of medicine to a man in his situation was by no means an easy task. He was obliged to lodge in a garret, so low in the roof that he could only stand upright in the middle of the room. Beside him lodged a water-carrier with 12 children. Fourcroy acted as physician to this numerous family, and in recompense was always supplied with an abundance of water. He contrived to support himself by giving lessons to other students, by facilitating the researches of richer writers, and by some translations which he sold to a bookseller. For these he was only half paid, but the conscientious bookseller offered 30 years afterwards to make up the deficiency, when his creditor was become Director General of Public Instruction. Fourcroy studied with so much zeal and ardour that he soon became well acquainted with the subject of medicine. But this was not sufficient. It was necessary to get a doctor's degree, and all the expenses at that time amounted to 250 lire. An old physician, Dr. Deist, had left funds to the faculty to give a gratuitous degree and license, once every 2 years, to the poor student who should best deserve them. Fourcroy was the most conspicuous student at that time in Paris. He would therefore have reaped the benefit of this benevolent institution had it not been for the unlucky situation in which he was placed. There happened to exist a quarrel between the faculty charged with the education of medical men and the granting of degrees, and a society recently formed by government for the improvement of the medical art. This dispute had been carried to a great length, and had attracted the attention of all the frivolous and idle inhabitants of Paris. Vicar d'Azyr was secretary to the society, and of course one of its most active champions, and was in consequence particularly obnoxious to the faculty of medicine at Paris. Fourcroy was unluckily the acknowledged protégé of this eminent anatomist. This was sufficient to induce the faculty of medicine to refuse him a gratuitous degree. He would have been excluded in consequence of this from entering on the career of a practitioner, had not the society, enraged at this treatment, and influenced by a violent party spirit, formed a subscription and contributed the necessary expenses. It was no longer possible to refuse M. de Fourcroy the degree of doctor, when he was thus enabled to pay for it. But above the simple degree of doctor, there was another, entitled Docteur Regent, which depended entirely on the votes of the faculty. It was unanimously refused to M. de Fourcroy. This refusal put it out of his power afterwards to commence teacher in the medical school, and gave the medical faculty the melancholy satisfaction of not being able to enroll among their number the most celebrated professor in Paris. This violent and unjust conduct of the faculty of medicine made a deep impression on the mind of Fourcroy, and contributed not a little to the subsequent downfall of that powerful body. End of section 52. Recording by Lawrence Trask. InterfaceAudio.com. Section 53 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, InterfaceAudio.com, Mount Vernon, Ohio. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 3, Progress of Scientific Chemistry in France, Part 10. Fourcroy being thus entitled to practice in Paris, his success depended entirely on the reputation which he could contrive to establish. For this purpose he devoted himself to the sciences connected with medicine, as the shortest and most certain road by which he could reach his object. His first writings showed no predilection for any particular branch of science. He wrote upon chemistry, anatomy, and natural history. He published an abridgment of the history of insects, and a description of the bursa mucosa of the tendons. This last piece seems to have given him the greatest celebrity, for in 1785 he was admitted, in consequence of it, into the Academy as an anatomist. But the reputation of Buquet, at this time very high, gradually drew his particular attention to chemistry, and he retained this predilection during the rest of his life. Buquet was at that time professor of chemistry in the medical school of Paris, and was greatly celebrated and followed on account of his eloquence and the elegance of his language. Fourcroy became in the first place his pupil, and afterwards his particular friend. One day, when a sudden attack of disease prevented him from lecturing as usual, he entreated Fourcroy to supply his place. Our young chemist at first declined, and alleged his ignorance of the method of addressing a public audience. But, overcome by the persuasions of Buquet, he at last consented, and in this, his first essay, he spoke 2 hours without disorder or hesitation, and acquitted himself to the satisfaction of his whole audience. Buquet soon after substituted him in his place, and it was in his laboratory and in his classroom that he first made himself acquainted with chemistry. He was enabled, at the death of Buquet, in consequence of an advantageous marriage that he had made, to purchase the apparatus and cabinet of his master, and although the faculty of medicine would not allow him to succeed to the chair of Buquet, they could not prevent him from succeeding to his reputation. There was a kind of college which had been established in the Jardin du Roi, which at that time was under the superintendence of Buffon, and Marquer was the professor of chemistry in this institution. On the death of this chemist in 1784, both Berthollet and Fourcroy offered themselves as candidates for the vacant chair. The voice of the public was so loud in favor of Fourcroy that he was appointed to the situation in spite of the high character of his antagonist, and the political influence which was exerted in his favor. He filled this chair for 25 years, with a reputation for eloquence continually on the increase. Such were the crowds, both of men and women, who flocked to hear him, that it was twice necessary to enlarge the size of the lecture-room. After the Revolution had made some progress, he was named a member of the National Convention in the autumn of the memorable year 1793. It was during the Reign of Terror, when the Convention itself, and with it all France, was under the absolute dominion of one of the most sanguinary monsters that ever existed. It was almost equally dangerous for the members of the Convention to remain silent, or to take an active part in the business of that assembly. Fourcroy never opened his mouth in the Convention till after the death of Robespierre. At this period he had influence enough to save the lives of some men of merit, among others of Darcet, who did not know the obligation under which he lay to him till long after. At last his own life was threatened, and his influence, of course, completely annihilated. It was during this unfortunate and disgraceful period that many eminent men lost their lives, among others Lavoisier, and Fourcroy is accused of having contributed to the death of this illustrious chemist. But Cuvier entirely acquits him of this atrocious charge, and assures us that it was urged against him merely out of envy at his subsequent elevation. If in rigorous researches which we have made, says Cuvier in his Eloge of Fourcroy, we had found the smallest proof of an atrocity so horrible, no human power could have induced us to sully our mouths with his Eloge, or to have pronounced it within the walls of this temple, which ought to be no less sacred to honor than to genius. Fourcroy began to acquire influence only after the 9th Thermidor, when the nation was wearied with destruction, and when efforts were making to restore those monuments of science, and those public institutions for education, which during the wantonness and folly of the Revolution had been overturned and destroyed. Fourcroy began to acquire influence only after the 9th Thermidor, when the nation was wearied with destruction, and when efforts were making to restore those monuments of science, and those public institutions for education, which during the wantonness and folly of the Revolution had been overturned and destroyed. Fourcroy was particularly active in this renovation, and it was to him chiefly that the schools established in France for the education of youth are to be ascribed. The Convention had destroyed all the colleges, universities, and academies throughout France. The effects of this absurd abolition soon became visible. The army stood in need of surgeons and physicians, and there were none educated to supply the vacant places. 3 new schools were founded for educating medical men. They were nobly endowed. The term schools of medicine was prescribed as too aristocratical. They were distinguished by the ridiculous appellation of schools of health. The Polytechnic School was next instituted, as a kind of preparation for the exercise of the military profession, where young men could be instructed in mathematics and natural philosophy, to make them fit for entering the schools of the artillery, of engineers, and of the marine. The Central Schools was another institution for which France was indebted to the efforts of Fourcroy. The idea was good, though it was very imperfectly executed. It was to establish a kind of university in every department, for which the young men were to be prepared by a sufficient number of inferior schools scattered throughout the department. But unfortunately, these inferior schools were never properly established or endowed, and even the central schools themselves were never supplied with the proper masters. Indeed, it was found impossible to furnish such a number of masters at once. On that account, an institution was established in Paris, called the Normal School, for the express purpose of educating a sufficient number of masters to supply the different central schools. Fourcroy, either as a member of the Convention or of the Council of the Ancients, took an active part in all these institutions, as far as regarded the plan and the establishment. He was equally concerned in the establishment of the Institute and of the Musée d'Histoire Naturelle. This last was endowed with the utmost liberality, and Fourcroy was one of the first professors, as he was also in the School of Medicine and the Polytechnic School. He was equally concerned in the restoration of the university, which constituted one of the most useful parts of Bonaparte's reign. The violent exertions which he made in the numerous situations which he filled, and the prodigious activity which he displayed, gradually undermined his constitution. He himself was sensible of his approaching death, and announced it to his friends as an event which would speedily take place. On the 16th of December, 1809, after signing some despatches, he suddenly cried out, "Je suis mort," I am dead, and dropped lifeless on the ground. He was twice married, first to Mademoiselle Bettinger, by whom he had 2 children, a son and a daughter who survived him. He was married for the second time to Madame Belleville, the widow of Villais, by whom he had no family. He left but little fortune behind him, and two maiden sisters, who lived with him, depended afterwards for their support on his friend, M. Vauquelin. Notwithstanding the vast quantity of papers which he published, it will be admitted without dispute that the prodigious reputation which he enjoyed during his lifetime was more owing to his eloquence than to his eminence as a chemist, though even as a chemist he was far above mediocrity. He must have possessed an uncommon facility of writing. 5 successive editions of his System of Chemistry appeared, each of them gradually increasing in size and value, the first being in 2 volumes, and the last in 10. This last edition he wrote in 16 months. It contains much valuable information, and doubtless contributed considerably to the general diffusion of chemical knowledge. Its style is perhaps too diffuse, and the spirit of generalizing from particular and often ill-authenticated facts is carried to a vicious length. Perhaps the best of all his productions is his Philosophy of Chemistry. It is remarkable for its conciseness, its perspicuity, and the neatness of its arrangement. Besides these works, and the periodical publication entitled La Médecine Éclairée, of which he was the editor, there are above 160 papers on chemical subjects, with his name attached to them, which appeared in the Memoir of the Academy and of the Institute, and in the Annales de Chimie, or the Annales du Musée d'Histoire Naturelle, of which last work he was the original projector. Many of these papers contain analysis, both animal, vegetable, and mineral, of very considerable value. In most of them the name of Vauquelin is associated with his own as the author, and the general opinion is that the experiments were all made by Vauquelin, but that the papers themselves were drawn up by Fourcroy. It would serve little purpose to go over this long list of papers, because though they contributed essentially to the progress of chemistry, yet they exhibit but few of those striking discoveries which at once alter the face of the science, by throwing a flood of light on everything around them. I shall merely notice a few of what I consider as his best papers. 1. He ascertained that the most common biliary calculi are composed of a substance similar to spermaceti. This substance, in consequence of a subsequent discovery which he made during the removal of the dead bodies from the burial ground of the Innocents at Paris, namely, that these bodies are converted into a fatty matter, he called adipocere. It has been since distinguished by the name of cholestin, and has been shown to possess properties different from those of adipocere and spermaceti. 2. It is to him that we are indebted for the first knowledge of the fact that the salts of magnesia and ammonia have the property of uniting together and forming double salts. 3. His dissertation on the sulphate of mercury contains some good observations. The same remark applies to his paper on the action of ammonia on the sulphate, nitrate, and muriate of mercury. He first discovered the double salts which are formed. 4. The analysis of urine would have been valuable had not almost all the facts contained in it been anticipated by a paper of Dr. Wollaston, published in the Philosophical Transactions. It is to him that we are indebted for almost all the additions to our knowledge of calculi, since the publication of Scheele's original paper on the subject. 5. I may mention the process of Fourcroy and Vauquelin for obtaining pure barytes by exposing nitrate of barytes to a red heat as a good one. They discovered the existence of phosphate of magnesia in bones, of phosphorus in the brain and in the milts of fishes, and of a considerable quantity of saccharine matter in the bulb of the common onion, which, by undergoing a kind of spontaneous fermentation, was converted into manna. In these and many other similar discoveries, which I think it is unnecessary to notice, we do not know what fell to the share of Fourcroy, and what to Vauquelin, But there is one merit at least to which Fourcroy is certainly entitled, and it is no small one. He formed and brought forward Vauquelin, and proved to him ever after a most steady and indefatigable friend. This is bestowing no small panegyric on his character, for it would have been impossible to have retained such a friend through all the horrors of the French Revolution, if his own qualities had not been such as to merit so steady an attachment. Louis Bernard Guyton de Marveaux was born at Dijon on the 4th of January, 1737. His father, Anthony Guyton, was professor of civil law in the University of Dijon, and descended from an ancient and respectable family. At the age of 7, he showed an uncommon mechanical turn. Being with his father at a small village near Dijon, he there happened to meet a public officer returning from a sale, whence he brought back a clock that had remained unsold on account of its very bad condition. Morveau supplicated his father to buy it. The purchase was made for 6 francs. Young Morveau took it to pieces and cleaned it, supplied some parts that were wanting, and put it up again without any assistance. In 1799 this very clock was resold at a higher price, together with the estate and the house in which it had been originally placed, having during the whole of that time continued to go in the most satisfactory manner. When only 8 years of age, he took his mother's watch to pieces, cleaned it, and put it up again, to the satisfaction of all parties. After finishing his preliminary studies in his father's house, he went to college, and terminated his attendance on it at the age of 16. About this time he was instructed in botany by M. Michaud, a friend of his father, and a naturalist of some eminence. He now commenced law student in the University of Dijon, and after 3 years of intense application, he went to Paris to acquire a knowledge of the practice of the law. While in Paris, he not only attended to law, but cultivated at the same time several branches of political literature. In 1756, he paid a visit to Voltaire at Ferney. This seems to have inspired him with a love of poetry, particularly of the descriptive and satiric kind. About a year afterwards, when only 20, he published a poem called Le Rat Iconoclaste, ou le Jésuite Croquet. It was intended to throw ridicule on a well-known anecdote of the day, and to assist in blowing the fire that had already threatened destruction to the obnoxious order of Jesuits. The adventure alluded to was this. Some nuns who felt a strong predilection for a Jesuit, their spiritual director, were engaged in their accustomed Christmas occupation of modeling a representation of a religious mystery, decorated with several small statues representing the holy personages connected with the subject, and among them that of the ghostly father. But to mark their favorite, his statue was made of loaf sugar. The following day was destined for the triumph of the Jesuit, but meanwhile a rat had devoured the valuable puppet. The poem is written after the agreeable manner of the celebrated poem Ververs. At the age of 24, he had already pleaded several important causes at the bar, when the office of Advocate General at the Parliament of Dijon was advertised for sale. At that time all public situations, however important, were sold to the best bidder. His father, having ascertained that this place would be acceptable to his son, purchased it for 40,000 francs. The reputation of the young advocate and his engaging manners facilitated the bargain. In 1764 he was admitted an honorary member of the Academy of Sciences, Arts, and Belles Lettres of Dijon. 2 months after, he presented to the assembled chamber of the Parliament of Burgundy a memoir on public instruction, with a plan for a college on the principles detailed in his work. The encomiums which every public journal of the time passed on this production, and the flattering letters which he received, were unequivocal proofs of its value. In this memoir he endeavored to prove that man is bad or good according to the education which he has received. This doctrine was contrary to the creed of Diderot, who affirmed in his essay on the life of Seneca that nature makes wicked persons, and that the best institutions cannot render them good. But this mischievous opinion was successfully refuted by Morveau in a letter to an anonymous friend. The exact sciences were so ill taught and lamely cultivated at Dijon during the time of his university education, that after his admission into the academy, his notions on mechanics and natural philosophy were scanty and inaccurate. Dr. Chardonnot was in the habit of reading memoirs on chemical subjects, and on one occasion Morveau thought it necessary to hazard some remarks which were ill received by the doctor, who sneeringly told him that having obtained such success in literature, he had better rest satisfied with the reputation so justly acquired, and leave chemistry to those who knew more of the matter. Provoked at this violent remark, he resolved upon taking an honourable revenge. He therefore applied himself to the study of Marquère's Theoretical and Practical Chemistry, and of the Manual of Chemistry which Baume had just published. To the last chemist he also sent an extensive order for chemical preparations and utensils, with a view of forming a small laboratory near his office. He began by repeating many of Baume's experiments, and then trying his inexperienced hand at original researches. He soon found himself strong enough to attack the doctor. The latter had just been reading a memoir on the analysis of different kinds of oil, and Morveau combated some of his opinions with so much skill and sagacity as astonished every one present. After the meeting, Dr. Chardonnot addressed him thus: "You are born to be an honour to chemistry. So much knowledge could only have been gained by genius united with perseverance. Follow your new pursuit, and confer with me in your difficulties." But this new pursuit did not prevent Morveau from continuing to cultivate literature with success. He wrote an elegy of Charles V. of France, surnamed the Wise, which had been given out as the subject of a prize by the Academy. A few months afterwards, at the opening of the session of Parliament, he delivered a discourse on the actual state of jurisprudence, on which subject, 3 years after, he composed a more extensive and complete work. No code of laws demanded reform more urgently than those of France, and none saw more clearly the necessity of such a reformation. About this time a young gentleman of Dijon had taken into his house an adept, who offered, upon being furnished with the requisite materials, to produce gold in abundance. But after 6 months of expensive and tedious operations, during which period the roguish pretender had secretly distilled many oils, etc., which he disposed of for his own profit, the gentleman, beginning to doubt the sincerity of his instructor, dismissed him from his service, and sold the whole of his apparatus and materials to Morveau for a trifling sum. Soon after he repaired to Paris, to visit the scientific establishments of that metropolis, and to purchase preparations and apparatus which he still wanted to enable him to pursue with effect his favourite study. For this purpose he applied to Baume, then one of the most conspicuous of the French chemists. Pleased with his ardour, Baume inquired what courses of chemistry he had attended. "None," was the answer. "How then could you have learned to make experiments, and, above all, how could you have acquired the requisite dexterity?" "Practice," replied the young chemist, "has been my master. Melted crucibles and broken retorts, my tutors." "In that case," said Baume, "you have not learned, you have invented." About this time Dr. Chardonnot read a paper before the Dijon Academy on the causes of the augmentation of weight which metals experience when calcined. He combated the different explanations which had been already advanced, and then proceeded to show that it might be accounted for in a satisfactory manner by the abstraction of phlogiston. This drew the attention of Morveau to the subject. He made a set of experiments a few months afterwards, and read a paper on the phenomena of the air during combustion. It was soon after that he made a set of experiments on the time taken by different substances to absorb or emit a given quantity of heat. These experiments, if properly followed out, would have led to the discovery of specific heat, but in his hands they seem to have been unproductive. End of section 53. Recording by Lawrence Trask, interfaceaudio.com, Mount Vernon, Ohio. Section 54 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. The History of Chemistry, Volume 2, Chapter 3, The Progress of Scientific Chemistry in France, Part 2. In the year 1772, he published a collection of scientific essays under the title of Digressions Académiques. The memoirs on phlogiston, crystallization, and solution found in this book deserve particular attention and show the superiority of Morveau over most of the chemists of the time. About this time an event happened which deserves to be stated. It had been customary in one of the churches of Dijon to bury considerable numbers of dead bodies. From these an infectious exhalation had proceeded, which had brought on a malignant disorder and threatened the inhabitants of Dijon with something like the plague. All attempts to put an end to this infectious matter had failed, when Morveau tried the following method with complete success. A mixture of common salt and sulphuric acid in a wide-mouthed vessel was put upon chafing dishes in various parts of the church. The doors and windows were closed and left in this state for 24 hours. They were then thrown open, and the chafing dishes with the mixtures removed. Every remains of the bad smell was gone, and the church was rendered quite clean and free from infection. The same process was tried soon after in the prisons of Dijon, with the same success. Afterwards, chlorine gas was substituted for muriatic acid gas, and found still more efficacious. The present practice is to employ chloride of lime or chloride of soda for the purpose of fumigating infected apartments, and the process is found still more effectual than the muriatic acid gas, as originally employed by Morveau. The nitric acid fumes, proposed by Dr. Carmichael Smith, are also efficacious, but the application of them is much more troublesome and more expensive than of chloride of lime, which costs very little. In the year 1774, it occurred to Morveau that a course of lectures on chemistry, delivered in his native city, might be useful. Application being made to the proper authorities, the permission was obtained, and the necessary funds for supplying a laboratory granted. These lectures were begun on the 29th of April, 1776, and seem to have been of the very best kind. Everything was stated with great clearness, and illustrated by a sufficient number of experiments. His fame now began to extend, and his name to be known to men of science in every part of Europe, and in consequence he began to experience the fate of almost all eminent men, to be exposed to the attacks of the malignant and the envious. The experiments which he exhibited to determine the properties of carbonic acid gas drew upon him the animadversions of several medical men, who affirmed that this gas was nothing else than a peculiar state of sulphuric acid. Morveau answered these animadversions in 2 pamphlets, and completely refuted them. About this time he got metallic conductors erected on the house of the Academy at Dijon. On this account he was attacked violently for his presumption in disarming the hand of the Supreme Being. A multitude of fanatics assembled to pull down the conductors, and they would probably have done much mischief had it not been for the address of M. Maret, the secretary, who assured them that the astonishing virtue of the apparatus resided in the gilded point, which had purposely been sent from Rome by the Holy Father. Will it excite any surprise that within less than 20 years after this, the mass of the French people not only denounced the Christian religion and the spiritual dominion of the Pope, but declared themselves atheists. In 1777, Morveau published the first volume of a course of chemistry, which was afterwards followed by 3 other volumes, and is known by the name of Elements de chimie de l'Académie de Dijon. This book was received with universal approbation, and must have contributed very much to increase the value of his lectures. Indeed, a textbook is essential toward a successful course of lectures. It puts it in the power of the students to understand the lecture if they be at the requisite pains, and gives them a means of clearing up their difficulties, when any such occur. I do not hesitate to say that a course of chemical lectures is twice as valuable when the students are furnished with a good textbook, as when they are left to interpret the lectures by their own unassisted exertions. Soon after, he undertook the establishment of a manufacture of saltpetre upon a large scale. For this he received the thanks of M. Necker, who was at that time Minister of Finance, in the name of the King of France. This manufactory he afterwards gave up to M. Courtois, whose son still carries it on, and is advantageously known to the public as the discoverer of iodine. His next object was to make a collection of minerals, and to make himself acquainted with the science of mineralogy. All this was soon accomplished. In 1777 he was charged to examine the slate quarries and the coal mines of Burgundy, for which purpose he performed a mineralogical tour through the province. In 1779 he discovered a lead mine in that country, and a few years afterwards, when the attention of chemists had been drawn to sulphate of barytes and its base by the Swedish chemists, he sought for it in Burgundy, and found it in considerable quantity at Thote. This enabled him to draw up a description of the mineral, and to determine the characters of the base, to which he gave the name baryte, afterwards altered to that of barytes. This paper was published in the 3rd volume of the Memoir of the Dijon Academy. In this paper he describes his method of decomposing sulphate of barytes by heating it with charcoal, a method now very frequently followed. In the year 1779 he was applied to by Pencook, who meditated the great project of the Encyclopédie Méthodique, to undertake the chemical articles in that immense dictionary, and the demand was supported by a letter from Buffon, whose request he did not think he would with propriety refuse. The engagement was signed between them in September 1780. The first half volume of the chemical part of this encyclopedia did not appear till 1786, and Morveau must have been employed during the interval in the necessary study and researches. Indeed, it is obvious, from the many of the articles, that he had spent a good deal of time in experiments of research. The state of the chemical nomenclature was at that period peculiarly barbarous and defective. He found himself stopped at every corner for want of words to express his meaning. This state of things he resolved to correct, and accordingly in 1782 published his first essay on a new chemical nomenclature. No sooner did this essay appear than it was attacked by almost all chemists of Paris, and by none more zealously than by the chemical members of the Academy. Undismayed by the violence of his antagonists, and satisfied with the rectitude of his views and the necessity of the reform, he went directly to Paris to answer the objections in person. He not only succeeded in convincing his antagonists of the necessity of reform, but a few years afterwards prevailed upon the most eminent chemical members of the Academy, Lavoisier, Berthollet, and Fourcroy, to unite with him in rendering the reform still more complete and successful. He drew up a memoir, exhibiting a plan of a methodical chemical nomenclature, which was read at a meeting of the Academy of Sciences in 1787. Morveau, then, was in reality the author of the new chemical nomenclature, if we except a few terms which had been already employed by Lavoisier. Had he done nothing more for the science than this, it would deservedly have immortalized his name. For everyone must be sensible how much the new nomenclature contributed to the subsequent rapid extension of chemical science. It was during the repeated conferences held with Lavoisier and the two other associates that Morveau became satisfied of the truth of Lavoisier's new doctrine, and that he was induced to abandon the phlogistic theory. We do not know the methods employed to convert him. Doubtless both reasoning and experiment were made use of for the purpose. It was during this period that Morveau published a French translation of the Opuscula of Bergman. A society of friends, under his encouragement, translated the chemical memoirs of Scheele and many other foreign books of importance, which by their means were made known to the men of science in France. In 1783, in consequence of a favorable report by Marquer, Morveau obtained permission to establish a manufactory of carbonate of soda, the first of the kind ever attempted in France. It was during the same year he published his collections of pleadings at the bar, among which we find his Discours sur le Bonhomme, delivered at the opening of the sessions at Dijon, with which he took leave of his fellow magistrates, surrendering the insignia of the office, as he had determined to quit the profession of the law. On the 25th of April, 1784, Morveau, accompanied by President Virly, ascended from Dijon in a balloon which he had himself constructed, and repeated the ascent on the 12th of June following, with a view of ascertaining the possibility of directing these aerostatic machines by an apparatus of his own contrivance. The capacity of the balloon was 10,498,074 French cubic feet. The effect produced by this bold undertaking by two of the most distinguished characters in the town was beyond description. Such ascents were then quite new, and looked upon with a kind of reverential awe. Though Morveau failed in his attempts to direct these aerial vessels, yet his method was ingenious and exceedingly plausible. In 1786, Dr. Murray, secretary to the Dijon Academy, having fallen a victim to an epidemic disease, which he had in vain attempted to arrest, Morveau was appointed perpetual secretary and chancellor of the institution. Soon after this, the first half-volume of the chemical part of the Encyclopædia Méthodique made its appearance, and drew the attention of every person interested in the science of chemistry. No chemical treatise had hitherto appeared worthy of being compared to it. The article acid, which occupies a considerable part, is truly admirable, and whether we consider the historical details, the completeness of the accounts, the accuracy of the description of the experiments, or the elegance of the style, constitutes a complete model of what such a work should be. I may perhaps be partial, as it was from this book that I imbibed my own first notions in chemistry, but I never perused any book with more delight, and when I compared it with the best chemical books of the time, whether German, French, or English, its superiority became still more striking. In the article Acier, Morveau had come to the very same conclusions with respect to the nature of steel as had been come to by Berthollet, Mongre, and Vandermonde in their celebrated paper on the subject, just published in the Memoirs of the Academy. His own article had been printed, though not published, before the appearance of the Memoir of the Academicians. This induced him to send an explanation to Berthollet, which was speedily published in the Journal de Physique. In September 1787, he received a visit from Lavoisier, Berthollet, Fourcroy, Monge, and Vandermonde. Dr. Beddoes, who was travelling through France at the time, and happened to be in Dijon, joined the party. The object of the meeting was to discuss several experiments explanatory of the new doctrine. In 1789, an attempt was made to get him admitted as a member of the Academy of Sciences, but it failed, notwithstanding the strenuous exertions of Berthollet and his other chemical friends. The French Revolution had now broken out, occasioned by the wants of the state on one hand, and the resolute determination of the clergy and the nobility, on the other, not to submit to bear any share in the public burdens. During the early part of this revolution, Morveau took no part whatever in politics. In 1790, when France was divided into departments, he was named one of a commission by the National Assembly for the formation of the department of the Côte d'Or. On the 25th of August, 1791, he received from the Academy of Sciences the annual prize of 2,000 francs, for the most useful work published in the course of the year. This was decreed for him for his Dictionary of Chemistry in the Encyclopædia Méthodique. Aware of the pressing necessities of the state, Morveau seized the opportunity of showing his desire of contributing towards its relief by making a patriotic offering of the whole amount of his prize. When the election of the Second Constitutional Assembly took place, he was nominated a member by the Electoral College of his department. A few months before, his name had appeared among the list of members proposed by the Assembly for the election of a governor for the heir apparent. All this, together with the dignity of Solicitor General of the department, to which he had recently been raised, not permitting him to continue his chemical lectures at Dijon, of which he had already delivered 15 gratuitous courses, he resigned his chair in favor of Dr. Chaussier, afterwards a distinguished professor at the Faculty of Medicine of Paris, and, bidding adieu to his native city, proceeded to Paris. On the ever-memorable 16th of January, 1793, he voted with the majority of his deputies. He was therefore, in consequence of this vote, a regicide. During the same year he resigned, in favor of the Republic, his pension of 2,000 francs, together with the arrears of that pension. In 1794 he received from the government different commissions to act with the French armies in the Low Countries. Charged with the direction of a great aerostatic machine for warlike purposes, he superintended that one in which the chief of the staff of General Jourdan and himself ascended during the battle of Fleurus, and which so materially contributed to the success of the French arms on that day. On his return from his various missions, he received from the 3 committees of the executive government an invitation to cooperate with several learned men in the instruction of the central schools, and was named Professor of Chemistry at École Centrale des Travaux Publics, since better known under the name of the Polytechnic School. In 1795 he was re-elected member of the Council of 500 by the electoral assemblies of Sarthe and Ille-et-Vilaine. The executive government at this time decreed the formation of the National Institute, and named him one of the 48 members chosen by government to form the nucleus of that scientific body. In 1797 he resigned all his public situations, and once more attached himself exclusively to science, and to the establishments for public instruction. In 1798 he was appointed a provisional director of the Polytechnic School, to supply the place of Monge, who was then in Egypt. He continued to exercise its duties during 18 months, to the complete satisfaction of every person connected with that establishment. With much delicacy and disinterestedness, he declined accepting the salary of 2,000 francs attached to this situation, which he thought belonged to the proper director, though absent from his duties. In 1799 Bonaparte appointed him one of the administrators general of the Mint, and the year following he was made director of the Polytechnic School. In 1803 he received the Cross of the Legion of Honor, then recently instituted, and in 1805 was made an officer of the same order. These honors were intended as a reward for the advantage which had accrued from the mineral acid fumigations which he had first suggested. In 1811 he was created a baron of the French Empire. After having taught in the École Polytechnique for 16 years, he obtained leave, on applying to the proper authorities, to withdraw into the retired station of private life, crowned with years and reputation, and followed with the blessings of the numerous pupils whom he had brought up in the career of science. In this situation he continued about 3 years, during which he witnessed the downfall of Bonaparte and the restoration of the Bourbons. On the 21st of December, 1815, he was seized with a total exhaustion of strength, and after an illness of 3 days only, expired in the arms of his disconsolate wife, and a few trusty friends, having nearly completed the 80th year of his age. On the 3rd of January, 1816, his remains were followed to the grave by the members of the Institute and many other distinguished men, and Berthollet, one of his colleagues, pronounced a short but impressive funeral oration on his departed friend. Morveau had married Madame Picardet, the widow of a Dijon academician, who had distinguished himself by numerous scientific translations from the Swedish, German, and English languages. The marriage took place after they were both advanced in life, and he left no children behind him. His publications on chemical subjects were exceedingly numerous, and he contributed as much as any of his contemporaries to the extension of the science. But he was not the author of any striking chemical discoveries. It would be tedious to give a catalogue of his numerous productions, which were scattered through the Dijon Memoirs, the Journal de Physique, and the Annales de Chimie. End of section 54. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com.
Section 55 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 4, Progress of Analytical Chemistry. Analysis, or the art of determining the constituents of which every compound is composed, constitutes the essence of chemistry. It was therefore attempted as soon as the science put on anything like a systematic form. At first with very little success, but as knowledge became more and more general, chemists became more expert, and something like regular analysis began to appear. Thus Brandt showed that white vitriol is a compound of sulfuric acid and oxide of zinc, and Marggraf that selenite or gypsum is a compound of sulfuric acid and lime. Dr. Black made analyses of several of the salts of magnesia, so far at least as to determine the nature of the constituents, for hardly any attempt was made in that early period of the art to determine the weight of the respective constituents. The first person who attempted to lay down rules for the regular analysis of minerals, and to reduce these rules to practice, was Bergman. This he did in his papers De Docimasia Minerarum Humida, De Terra Gemmarum, and De Terra Tourmalini, published between the years 1777 and 1780. To analyze a mineral, or to separate it into its constituent parts, it is necessary in the first place to be able to dissolve it in an acid. Bergman showed that most minerals become soluble in muriatic acid if they be reduced to a very fine powder and then heated to redness, or fused with an alkaline carbonate. After obtaining a solution in this way, he pointed out methods by which the different constituents may be separated one after another, and their relative quantities determined. The fusion with an alkaline carbonate required a strong red heat. An earthenware crucible could not be employed, because at a fusing temperature it would be corroded by the alkaline carbonate, and thus the mineral under analysis would be contaminated by the addition of a quantity of foreign matter. Bergman employed an iron crucible. This effectually prevented the addition of any earthy matter, but at a red heat the iron crucible itself is apt to be corroded by the action of the alkali, and thus the mineral under analysis becomes contaminated with a quantity of that metal. This iron might easily be separated again by known methods, and would therefore be of comparatively small consequence, provided we were sure that the mineral under examination contained no iron. But when that happens, and it is a very frequent occurrence, an error is occasioned which we cannot obviate. Klaproth made a vast improvement in the art of analysis by substituting crucibles of fine silver for the iron crucibles of Bergman. The only difficulty attending their use was, that they were apt to melt unless great caution was used in heating them. Dr. Wollaston introduced crucibles of platinum about the beginning of the present century. It is from that period that we may date the commencement of accurate analyzing. Bergman's processes, as might have been expected, were rude and imperfect. It was Klaproth who first systematized chemical analysis, and brought the art to such a state that the processes followed could be imitated by others with nearly the same results, thus offering a guarantee for the accuracy of the process. Martin Henry Klaproth, to whom chemistry lies under so many and such deep obligations, was born at Wernigerode on the 1st of December, 1743. His father had the misfortune to lose his whole goods by a great fire on the 30th of June, 1751, so that he was able to do little or nothing for the education of his children. Martin was the second of three brothers, the eldest of whom became a clergyman, and the youngest private secretary at war, and keeper of the archives of the cabinet of Berlin. Martin survived both his brothers. He procured such meagre instruction in the Latin language as the school of Wernigerode afforded, and he was obliged to procure his small school fees by singing as one of the church choir. It was at first his intention to study theology, but the unmerited hard treatment with which he met at school so disinclined him to study that he determined in his 16th year to learn the trade of an apothecary. 5 years which he was forced to spend as an apprentice, and 2 as an assistant in the public laboratory in Quedlinburg, furnished him with but little scientific information, and gave him little else than a certain mechanical adroitness in the most common pharmaceutical preparations. He always regarded as the epoch of his scientific instruction the 2 years which he spent in the public laboratory at Hanover, from Easter 1766 till the same time in 1768. It was there that he first met with some chemical books of merit, especially those of Spielmann and Karthauser, in which a higher scientific spirit already breathed. He was now anxious to go to Berlin, of which he had formed a high idea from the works of Pott, Henkel, Rose, and Marggraf. An opportunity presenting itself about Easter 1768, he was placed as assistant in the laboratory of Wendland, at the sign of the Golden Angel, in the street of the Moors. Here he employed all the time which a conscientious discharge of the duties of his station left him in completing his own scientific education, and as he considered a profounder acquaintance with the ancient languages than he had been able to pick up at the school of Wernigerode, indispensable for a complete scientific education, he applied himself with great zeal to the study of the Greek and Latin languages, and was assisted in his studies by Mr. Poppelborn, at that time a preacher. About Michaelmas, 1770, he went to Danzig as assistant in the public laboratory, but in March of the following year he returned to Berlin as assistant in the office of the elder Valentine Rose, who was one of the most distinguished chemists of his day. But this connection did not continue long, for Rose died in 1771. On his deathbed he requested Klaproth to undertake the superintendence of his office. Klaproth not only superintended this office for 9 years with the most exemplary fidelity and conscientiousness, but undertook the education of the 2 sons of Rose, as if he had been their father. The younger died before reaching the age of manhood. The elder became his intimate friend, and the associate of all his scientific researches. For several years before the death of Rose, which happened in 1808, they wrought together, and Klaproth was seldom satisfied with the results of his experiments till they had been repeated by Rose. In the year 1780, Klaproth went through his trials for the office of apothecary with distinguished applause. His thesis on phosphorus and distilled waters was printed in the Berlin Miscellanies for 1782. Soon after this, Klaproth bought what had formerly been the Fleming Laboratory in Spandau Street, and he married Sophia Christiana Lechmann, with whom he lived till 1803, when she died, in a happy state. They had 3 daughters and a son, who survived their parents. He continued in possession of this laboratory, in which he had arranged a small workroom of his own, till the year 1800, when he purchased the room of the academical chemists, in which he was enabled, at the expense of the Academy, to furnish a better and more spacious apartment for his labours, for his mineralogical and chemical collection, and for his lectures. As soon as he had brought the first arrangements of his office to perfection, an office which, under his inspection and management, became the model of a laboratory, conducted upon the most excellent principles, and governed with the most conscientious integrity, he published in the various periodical works of Germany, such as Krell's Chemical Annals, the Writings of the Society for the Promotion of Natural Knowledge, Sell's Contribution to the Science of Nature and Medicine, Kohler's Journal, etc., a multitude of papers which soon drew the attention of chemists, for example, his Essay on Copal, on the elastic stone, on Proust's sel perlé, on the green lead spar of Chopow, on the best method of preparing ammonia, on the carbonate of barytes, on the wolfram of Cornwall, on wood tin, on the violet schorl, on the celebrated aerial gold, on apatite, etc. All these papers, which secured him a high reputation as a chemist, appeared before 1788, when he was chosen an ordinary member of the physical class of the Royal Berlin Academy of Sciences. The Royal Academy of Arts had elected him a member a year earlier. From this time, every volume of the Memoirs of the Academy, and many other periodical works besides, contain numerous papers by this accomplished chemist, and there is not one of them which does not furnish us with a more exact knowledge of some one of the productions of nature or art. He has either corrected false representations, or extended views that were before partially known, or has revealed the composition and mixture of the parts of bodies, and has made us acquainted with a variety of new elementary substances. Amidst all these labours, it is difficult to say whether we should most admire the fortunate genius, which, in all cases, readily and easily divined the point where anything of importance lay concealed, or the acuteness which enabled him to find the best means of accomplishing his object, or the unceasing labour and incomparable exactness with which he developed it, or the pure scientific feeling under which he acted, and which was removed at the utmost possible distance from every selfish, every avaricious, and every contentious purpose. In the year 1795 he began to collect his chemical works which lay scattered among so many periodical publications, and gave them to the world under the title Beiträge zur chemischen Kenntnis der Mineralkörper, Contributions to the Chemical Knowledge of Mineral Bodies. Of this work, which consists of 6 volumes, the last was published in 1815, about a year before the author's death. It contains no fewer than 207 treatises, the most valuable part of all that Klaproth has done for chemistry and mineralogy. It is a pity that the sale of this work did not permit the publication of a 7th volume, which would have included the rest of his papers, which he had not collected, and given us a good index to the whole work, which would have been of great importance to the practical chemist. There is indeed an index to the first 5 volumes, but it is meagre and defective, containing little else than the names of the substances on which his experiments were made. Besides his own works, the interest which he took in the labours of others deserves to be noticed. He superintended a new edition of Gren's Manual of Chemistry, remarkable not so much for what he added as for what he took away and corrected. The part which he took in Wolff's Chemical Dictionary was of great importance. The composition of every particular treatise was by Professor Wolff, but Klaproth read over every important article before it was printed, and assisted the editor on all occasions with the treasures of his experience and knowledge. Nor was he less useful to Fischer in his translation of Berthollet on affinity and on chemical statics. These meritorious services, and the lustre which his character and discoveries conferred on his country, were duly appreciated by his sovereign. In 1782 he had been made assessor in the Supreme College of Medicine and of Health, which then existed. At a more recent period, he enjoyed the same rank in the Supreme Council of Medicine and of Health, and when this college was subverted, in 1810, he became a member of the medical deputation attached to the Ministry of the Interior. He was also a member of the Perpetual Court Commission for Medicines. His lectures, too, procured for him several municipal situations. As soon as the public became acquainted with his great chemical acquirements, he was permitted to give yearly 2 private courses of lectures on chemistry, one for the officers of the Royal Artillery Corps, the other for officers not connected with the army, who wished to accomplish themselves for some practical employment. Both of these lectures assumed afterwards a municipal character. The former led to his appointment as professor of the Artillery Academy instituted at Tempelhof, and after its dissolution to his situation as professor in the Royal War School. The other lecture procured for him the professorship of chemistry in the Royal Mining Institute. On the establishment of the university, Klaproth's lectures became those of the university, and he himself was appointed ordinary professor of chemistry and member of the academical senate. From 1797 to 1810, he was an active member of a small scientific society, which met yearly during a few weeks for the purpose of discussing the more recondite mysteries of the science. In the year 1811, the King of Prussia added to all his other honors the Order of the Red Eagle of the 3rd class. Klaproth spent the whole of a long life in the most active and conscientious discharge of all the duties of his station, and in an uninterrupted course of experimental investigations. He died at Berlin on the 1st of January, 1817, in the 70th year of his age. Among the remarkable traits in his character was his incorruptible regard for everything that he believed to be true, honorable, and good, his pure love of science, with no reference whatever to any selfish, ambitious, and avaricious feeling, his rare modesty, undebased by the slightest vainglory or boasting. He was benevolently disposed toward all men, and never did a slighting or contemptuous word respecting any person fall from him. When forced to blame, he did it briefly and without bitterness, for his blame always applied to actions, not to persons. His friendship was never the result of selfish calculation, but was founded on his opinion of the personal worth of the individual. Amidst all the unpleasant accidents of his life, which were far from few, he evinced the greatest firmness of mind. In his common behavior he was pleasant and composed, and was indeed rather inclined to a joke. To all this may be added a true religious feeling, so uncommon among men of science of his day. His religion consisted not in words and forms, not in positive doctrines, nor in ecclesiastical observances, which, however, he believed to be necessary and honorable, but in a zealous and conscientious discharge of all his duties, not only of those which are imposed by the laws of men, but of those holy duties of love and charity, which no human law, but only that of God, can command, and without which the most enlightened of men is but a sounding brass or a tinkling cymbal. He early showed this religious feeling by the honorable care which he bestowed on the education of the children of Valentine Rose. Nor did he show less care at an after period toward his assistants and apprentices, to whom he refused no instruction, and in whose success he took the most active concern. He took a pleasure in everything that was good and excellent, and felt a lively interest in every undertaking which he believed to be of general utility. He was equally removed from the superstition and infidelity of his age, and carried the principles of religion, not on his lips, but in the inmost feelings of his heart, from whence they emanated in actions which pervaded and ennobled his whole being and conduct. End of section 55. Section number 56 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 4, Part 2. When we take a view of the benefits which Klaproth conferred upon chemistry, we must not look so much at the new elementary substances which he discovered, though they must not be forgotten, as at the new analytical methods which he introduced, the precision and neatness and order and regularity with which his analyses were conducted, and the scrupulous fidelity with which everything was faithfully stated as he found it. 1. When a mineral is subjected to analysis, whatever care we take to collect all the constituents and to weigh them without losing any portion whatever, it is generally found that the sum of the constituents obtained fall a little short of the weight of the mineral employed in the analysis. Thus, if we take 100 grains of any mineral and analyze it, the weights of all the constituents obtained added together will rarely make up 100 grains, but generally somewhat less, perhaps only 99 or even 98 grains. But some cases occur when the analysis of 100 grains of a mineral gives us constituents that weigh, when added together, more than 100 grains, perhaps 105, or in some rare cases as much as 110. It was the custom with Bergman and other analysts of his time to consider this deficiency or surplus as owing to errors in the analysis, and therefore to slur it over in the statement of the analysis, by bringing the weight of the constituents, by calculation, to amount exactly to 100 grains. Klaproth introduced the method of stating the results exactly as he got them. He gives the weight of mineral employed in all of his analyses, and the weight of each constituent extracted. These weights, added together, generally show a loss, varying from 2% to 0.5%. This improvement may appear, at first sight, trifling, yet I am persuaded that to it we are indebted for most of the subsequent improvements introduced into analytical chemistry. If the loss sustained was too great, it was obvious either that the analysis had been badly performed, or that the mineral contains some constituent which had been overlooked and not obtained. This laid him under the necessity of repeating the analysis, and if the loss continued, he naturally looked out for some constituent which his analysis had not enabled him to obtain. It was in this way that he discovered the presence of potash in minerals, and Dr. Kennedy afterwards, by following out his processes, discovered soda as a constituent. It was in this way that water, phosphoric acid, arsenic acid, fluoric acid, boracic acid, etc., were also found to exist as constituents in various mineral bodies, which, but for the accurate mode of notation introduced by Klaproth, would have been overlooked and neglected. 2. When Klaproth first began to analyze mineral bodies, he found it extremely difficult to bring them into a state capable of being dissolved in acids, without which an accurate analysis was impossible. Accordingly, corundum, adamantine spar, and the zircon or hyacinth baffled his attempts for a considerable time, and induced him to consider the earth of corundum as of a peculiar nature. He obviated this difficulty by reducing the mineral to an extremely fine powder, and, after digesting it in caustic potash ley till all the water was dissipated, raising the temperature and bringing the whole into a state of fusion. This fusion must be performed in a silver crucible. Corundum and every other mineral which had remained insoluble after fusion with an alkaline carbonate was found to yield to this new process. This was an improvement of considerable importance. All those stony minerals which contain a notable proportion of silica, in general become soluble after having been kept for some time in a state of ignition with twice their weight of carbonate of soda. At that temperature, the silica of the mineral unites with the soda, and the carbonic acid is expelled. But when the quantity of silica is small, or when it is totally absent, heating with carbonate of soda does not answer so well. With such minerals, caustic potash or soda may be substituted with advantage, and there are some of them that cannot be analyzed without having recourse to that agent. I have succeeded in analyzing corundum and chrysoberyl, neither of which, when pure, contain any silica, by simply heating them in carbonate of soda. But the process does not succeed unless the minerals be reduced to an exceedingly minute powder. 3. When Klaproth discovered potash in the idocrase and in some other minerals, it became obvious that the old mode of rendering minerals soluble in acids by heating them with caustic potash or an alkaline carbonate could answer only for determining the quantity of silica and of earths or oxides which the mineral contained, but that it could not be used when the object was to determine its potash. This led him to substitute carbonate of barytes instead of potash or soda or their carbonates. After having ascertained the quantity of silica and of earths and metallic oxides which the mineral contained, his last process to determine the potash in it was conducted in this way. A portion of the mineral reduced to a fine powder was mixed with 4 or 5 times its weight of carbonate of barytes, and kept for some time in a platinum crucible in a red heat. By this process, the whole becomes soluble in muriatic acid. The muriatic acid solution is freed from silica, and afterwards from barytes and all the earths and oxides which it contains, by means of carbonate of ammonia. The liquid, thus freed from everything but the alkali, which is held in solution by the muriatic acid, and the ammonia, used as a precipitant, is evaporated to dryness, and the dry mass, cautiously heated in a platinum crucible till the ammoniacal salts are driven off. Nothing now remains but the potash, or soda, in combination with muriatic acid. The addition of muriate of platinum enables us to determine whether the alkali be potash or soda. If it be potash, it occasions a yellow precipitate, but nothing falls if the alkali be soda. This method of analyzing minerals containing potash or soda is commonly ascribed to Rose. Fescher, in his elegy of Klaproth, informs us that Klaproth said to him, more than once, that he was not quite sure whether he himself or Rose had the greatest share in bringing this method to a state of perfection. From this, I think it not unlikely that the original suggestion might have been owing to Rose, but that it was Klaproth who first put it to the test of experiment. The objection to this mode of analyzing is the high price of the carbonate of barytes. This is partially obviated by recovering the barytes in the state of carbonate, and this, in general, may be done without much loss. Berthier has proposed to substitute oxide of lead for carbonate of barytes. It answers very well, is sufficiently cheap, and does not injure the crucible, provided the oxide of lead be mixed previously with a little nitrate of lead to oxidize any fragments of metallic lead which it may happen to contain. Berthier's mode, therefore, in point of cheapness, is preferable to that of Klaproth. It is equally efficacious and equally accurate. There are some other processes which I myself prefer to either of these, because I find them equally easy and still less expensive than either carbonate of barytes or oxide of lead. Davy's method with boracic acid is exceptionable on account of the difficulty of separating the boracic acid completely again. 4. The mode of separating iron and manganese from each other employed by Bergman was so defective that no confidence whatever can be placed in his results. Even the methods suggested by Vauquelin, though better, are still defective. But the process followed by Klaproth is susceptible of very great precision. He has, we shall suppose, the mixture of iron and manganese to be separated from each other, in solution, in muriatic acid. The first step of the process is to convert the protoxide of iron, should it be in that state, into peroxide. For this purpose, a little nitric acid is added to the solution, and the whole heated for some time. The liquid is now to be rendered as neutral as possible, first by driving off as much of the excess of acid as possible, by concentrating the liquid, and then by completing the neutralization, by adding very dilute ammonia, till no more can be added without occasioning a permanent precipitation. Into the liquid thus neutralized, succinate or benzoate of ammonia is dropped, as long as any precipitate appears. By this mean, the whole peroxide of iron is thrown down in combination with succinic or benzoic acid, while the whole manganese remains in solution. The liquid being filtered, to separate the benzoate of iron, the manganese may now, if nothing else be in the liquid, be thrown down by an alkaline carbonate, or, if the liquid contain magnesia or any other earthy matter, by hydrosulphuret of ammonia, or chloride of lime. This process was the contrivance of Galen, but it was made known to the public by Klaproth, who ever after employed it in his analyses. Galen employed succinate of ammonia, but Heisinger afterwards showed that benzoate of ammonia might be substituted without any diminution of the accuracy of the separation. This last salt, being much cheaper than succinate of ammonia, answers better in this country. In Germany, the succinic acid is the cheaper of the two, and therefore the best. 5. But it was not by new processes alone that Klaproth improved the mode of analysis, though they were numerous and important. The improvements in the apparatus contributed not less essentially to the success of his experiments. When he had to do with very hard minerals, he employed a mortar of flint, or rather of agate. This mortar he, in the first place, analyzed to determine exactly the nature of the constituents. He then weighed it. When a very hard body is pounded in such a mortar, a portion of the mortar is rubbed off and mixed with the pounded mineral. What the quantity thus abraded was, he determined by weighing the mortar at the end of the process. The loss of weight gave the portion of the mortar abraded, and this portion must be mixed with the pounded mineral. When a hard stone is pounded in an agate mortar, it is scarcely possible to avoid losing a little of it. The best method of proceeding is to mix the matter to be pounded, previously reduced to a coarse powder in a diamond mortar, with a little water. This both facilitates the trituration and prevents any of the dust from flying away, and not more than a couple of grains of the mineral should be pounded at once. Still, owing to very obvious causes, a little of the mineral is sure to be lost during the pounding. When the process is finished, the whole powder is to be exposed to a red heat in a platinum crucible and weighed. Supposing no loss, the weight should be equal to the quantity of the mineral pounded, together with the portion abraded from the mortar. But almost always the weight will be found less than this. Suppose the original weight of the mineral before pounding was A, and the quantity abraded from the mortar 1. Then if nothing were lost, the weight should be A plus 1. But we actually find it only B, a quantity less than A plus 1. To determine the weight of matter abraded from the mortar contained in this powder, we say the ratio of A plus 1 to B is proportional to the ratio of 1 to X, the quantity from the mortar in our powder, and X equal B divided by A plus 1. In performing the analysis, Klaproth attended to this quantity, which was silica, and subtracted it. Such minute attention may appear, at first sight, superfluous, but it is not so. In analyzing sapphire, chrysoberyl, and some other very hard minerals, the quantity of silica abraded from the mortar sometimes amounts to 5% of the weight of the mineral, and if we were not to attend to the way in which this silica has been introduced into the powder, we should give an erroneous view of the constitution of the mineral under analysis. All the analyses of chrysoberyl hitherto published give a considerable quantity of silica as a constituent of it. This silica, if really found by the analyst, must have been introduced from the mortar, for pure chrysoberyl contains no silica whatever, but is a definite compound of glucina, alumina, and oxide of iron. When Klaproth operated with fire, he always selected his vessels, whether of earthenware, glass, plumbago, iron, silver, or platinum, upon fixed principles, and showed more distinctly than chemists had previously been aware of what an effect the vessel frequently has upon the result. He also prepared his reagents with great care, to ensure their purity, for obtaining several of which in their most perfect state, he invented several efficient methods. It is to the extreme care with which he selected his minerals for analysis, and to the purity of his reagents, and the fitness of his vessels for the objects in view, that the great accuracy of his analyses is to be, in a great measure, ascribed. He must also have possessed considerable dexterity in operating, for when he had in view to determine any particular point with accuracy, his results came, in general, exceedingly near the truth. I may notice, as an example of this, his analysis of sulfate of barytes, which was within about 1.5% of absolute correctness. When we consider the looseness of the data which chemists were then obliged to use, we cannot but be surprised at the smallness of the error. Berzelius, in possession of better data and possessed of much dexterity and a good apparatus, when he analyzed this salt many years afterwards, committed an error of 0.5%. Klaproth, during a very laborious life, wholly devoted to analytical chemistry, entirely altered the face of mineralogy. When he began his labors, chemists were not acquainted with the true composition of a single mineral. He analyzed above 200 species, and the greater number of them with so much accuracy that his successors have, in most cases, confirmed the results which he obtained. The analyses least to be depended on are those of minerals which contain both lime and magnesia, for his process for separating lime and magnesia from each other was not a good one. Nor am I sure that he always succeeded completely in separating silica and magnesia from each other. This branch of analysis was first properly elucidated by Mr. Chenevix. 6. Analytical chemistry was, in fact, systematized by Klaproth, and it is by studying his numerous and varied analyses that modern chemists have learned this very essential but somewhat difficult art, and have been able, by means of still more accurate data than he possessed, to bring it to a still greater degree of perfection. But it must not be forgotten that Klaproth was in reality the creator of this art, and that on that account the greatest part of the credit due to the progress that has been made in it belongs to him. It would be invidious to point out the particular analyses which are least exact. Perhaps they ought rather to be ascribed to an unfortunate selection of specimens, than to any want of care or skill in the operator. But during his analytical processes, he discovered a variety of new elementary substances, which it may be proper to enumerate. In 1789, he examined a mineral called pitchblende, and found in it the oxide of a new metal, to which he gave the name of uranium. He determined its characters, reduced it to the metallic state, and described its properties. It was afterwards examined by Richter, Buchholz, Arfvedson, and Berzelius. It was in the same year, 1789, that he published his analysis of the zircon. He showed it to be a compound of silica and a new earth, to which he gave the name of zirconia. He determined the properties of this new earth, and showed how it might be separated from other bodies and obtained in a state of purity. It has been since ascertained that it is a metallic oxide, and the metallic basis of it is now distinguished by the name of zirconium. In 1795 he showed that the hyacinth is composed of the same ingredients as the zircon, and that both in fact constitute only one species. This last analysis was repeated by Morveau, and has been often confirmed by modern analytical chemists. It was in 1795 that he analyzed what was at that time called red schorl, and now titanite. He showed that it was the oxide of a new metallic body, to which he gave the name of titanium. He described the properties of this new body, and pointed out its distinctive characters. It must not be omitted, however, that he did not succeed in obtaining oxide of titanium, or titanic acid, as it is now called, in a state of purity. He was not able to separate a quantity of oxide of iron with which it was united, and which gave it a reddish color. It was first obtained pure by H. Rose, the son of his friend and pupil, who took so considerable a part in his scientific investigations. Titanium in the metallic state was some years ago discovered by Dr. Wollaston in the slag at the bottom of the iron furnace at Merthyr Tydvil in Wales. It is a yellow-colored, brittle, but very hard metal, possessed of considerable beauty, but not yet applied to any useful purpose. In 1797 he examined the menachanite, a black sand from Cornwall, which had been subjected to a chemical analysis by Gregor in 1791, who had extracted from it a new metallic substance, which Kirwan distinguished by the name of menachine. Klaproth ascertained that the new metal of Gregor was the very same as his own titanium, and that menachanite is a compound of titanic acid and oxide of iron. Thus Mr. Gregor had anticipated him in the discovery of titanium, though he was not aware of the circumstance till 2 years after his own experiments had been published. In the year 1793 he published a comparative set of experiments on the nature of carbonates of barytes and strontian, showing that their bases are two different earths, and not the same, as had been hitherto supposed in Germany. This was the first publication on strontian which appeared on the continent, and Klaproth seems to have been ignorant of what had already been done on it in Great Britain. At least, he takes no notice of it in his paper, and it was not his character to slur over the labors of other chemists, when they were known to him. Strontian was first mentioned as a peculiar earth by Dr. Crawford in his paper on the medicinal properties of the muriate of baryates, published in 1790. The experiments on which he founded his opinions were made, he informs us, by Mr. Cruikshanks. A paper on the same subject by Dr. Hope was read to the Royal Society of Edinburgh in 1793, but they had been begun in 1791. In this paper Dr. Hope establishes the peculiar characters of strontian and describes its salts with much precision. Klaproth had been again anticipated in his experiments on strontian, but he could not have become aware of this till afterwards, for his own experiments were given to the public before those of Dr. Hope. On the 25th of January, 1798, his paper on the gold ores of Transylvania was read at a meeting of the Academy of Sciences at Berlin. During his analysis of these ores, he detected a new white metal, to which he gave the name of tellurium. Of this metal he describes the properties and points out its distinguishing characters. These ores had been examined by Miller of Richtenstein in the year 1782, and he had extracted from them a metal which he considered as differing from every other. Not putting full confidence in his own skill, he sent a specimen of his new metal to Bergman, requesting him to examine it and give his opinion respecting its nature. All that Bergman did was to show that the metallic body which he had got was not antimony, to which alone of all known metals it bore any resemblance. It might be inferred from this that Miller's metal was new, but the subject was lost sight of till the publication of Klaproth's experiments in 1802 recalled it to the recollection of chemists. Indeed, Klaproth relates all that Miller had done with the most perfect fairness. In the year 1804 he published the analysis of a red-colored mineral from Basnas in Sweden, which had been at one time confounded with tungsten, but which the Elwarts had shown to contain none of that metal. Klaproth showed that it contained a new substance as one of its constituents, which he considered as a new earth, and which he called ochroita, because it forms colored salts with acids. 2 years after, another analysis of the same mineral was published by Berzelius and Hisinger. They considered the new substance which the mineral contained as a metallic oxide, and to the unknown metallic base they gave the name of cerium, which has been adopted by chemists in preference to Klaproth's name. The characters of oxide of cerium given by Berzelius and Hisinger agree with those given by Klaproth to ochroita in all the essential circumstances. Of course, Klaproth must be considered as the discoverer of this new body. The distinction between earth and metallic oxide is now known to be an imaginary one. All the substances formerly called earths are, in fact, metallic oxides. Besides these new substances, which he detected by his own labors, he repeated the analyses of others, and confirmed and extended the discoveries they had made. Thus, when Vauquelin discovered the new earth glucina in the emerald and beryl, he repeated the analysis of these minerals, confirmed the discovery of Vauquelin, and gave a detailed account of the characters and properties of glucina. Gadolin had discovered another new earth in the mineral called gadolinite. This discovery was confirmed by the analysis of Ekberg, who distinguished the new earth by the name of yttria. Klaproth immediately repeated the analysis of the gadolinite, confirmed the results of Ekberg's analysis, and examined and described the properties of yttria. End of section 56. Section 57 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 4, Part 3. When Dr. Kennedy discovered soda in basalt, Klaproth repeated the analysis of this mineral and confirmed the results obtained by the Edinburgh analyst. But it would occupy too much room if I were to enumerate every example of such conduct. Whoever will take the trouble to examine the different volumes of the Beiträge will find several others not less striking or less useful. The service which Klaproth performed for mineralogy in Germany was performed equally in France by the important labors of M. Vauquelin. It was in France, in consequence of the exertions of Romée de Lisle and the mathematical investigations of the Abbé Hauy respecting the structure of crystals, which were gradually extended over the whole mineral kingdom, that the reform in mineralogy, which has now become in some measure general, originated. Hauy laid it down as a first principle that every mineral species is composed of the same constituents, united in the same proportion. He therefore considered it as an object of great importance to procure an exact chemical analysis of every mineral species. Hitherto no exact analysis of minerals had been performed by French chemists, for Sage, who was the chemical mineralogist connected with the Academy, satisfied himself with ascertaining the nature of the constituents of minerals without determining their proportions. But Vauquelin soon displayed a knowledge of the mode of analysis and a dexterity in the use of the apparatus which he employed, little less remarkable than that of Klaproth himself. Of Vauquelin's history I can give but a very imperfect account, as I have not yet had an opportunity of seeing any particulars of his life. He was a peasant boy of Normandy, with whom Fourcroy accidentally met. He was pleased with his quickness and parts, and delighted with the honesty and integrity of his character. He took him with him to Paris, and gave him the superintendence of his laboratory. His chemical knowledge speedily became great, and his practice in experimenting gave him skill and dexterity. He seems to have performed all the analytical experiments which Fourcroy was in the habit of publishing. He speedily became known by his publications and discoveries. When the scientific institutions were restored or established after the death of Robespierre, Vauquelin became a member of the Institute and chemist to the School of Mines. He was made also assay master of the Mint. He was a professor of chemistry in Paris, and delivered likewise private lectures, and took in practical pupils into his laboratory. His laboratory was of considerable size, and he was in the habit of preparing both medicines and chemical reagents for sale. It was he chiefly that supplied the French chemists with phosphorus, etc., which cannot be conveniently prepared in a laboratory fitted up solely for scientific purposes. Vauquelin was by far the most industrious of all the French chemists, and has published more papers, consisting of mineral, vegetable, and animal analyses, than any other chemist without exception. When he had the charge of the laboratory of the School of Mines, Hauy was in the habit of giving him specimens of all the different minerals which he wished analyzed. The analyses were conducted with consummate skill, and we owe to him a great number of improvements in the methods of analysis. He is not entitled to the same credit as Klaproth, because he had the advantage of many analyses of Klaproth to serve him as a guide. But he had no model before him in France, and both the apparatus used by him and the reagents which he employed were of his own contrivance and preparation. I have sometimes suspected that his reagents were not always very pure, but I believe the true reason of the unsatisfactory nature of many of his analyses is the bad choice made of the specimens selected for analysis. It is obvious from his papers that Vauquelin was not a mineralogist, for he never attempts a description of the mineral which he subjects to analysis, satisfying himself with the specimen put into his hands by Hauy. Where that specimen was pure, as was the case with emerald and beryl, his analysis is very good. But when the specimen was impure or ill-chosen, then the result obtained could not convey a just notion of the constituents of the mineral. That Hauy would not be very difficult to please in his selection of specimens, I think myself entitled to infer from the specimens of minerals contained in his own cabinet, many of which were by no means well selected. I think, therefore, that the numerous analyses published by Vauquelin, in which the constituents assigned by him are not those, or at least not in the same proportions as have been found by succeeding analysts, are to be ascribed not to errors in the analysis, which, on the contrary, he always performed carefully and with the requisite attention to precision, but to the bad selection of specimens put into his hand by Hauy, or those other individuals who furnished him with the specimens which he employed in his analyses. This circumstance is very much to be deplored, because it puts it out of our power to confide in the analysis of Vauquelin till it has been repeated and confirmed by somebody else. Vauquelin not only improved the analytical methods and reduced the art to a greater degree of simplicity and precision, but he discovered likewise new elementary bodies. The red lead ore of Siberia had early drawn the attention of chemists on account of its beauty, and various attempts had been made to analyze it. Among others, Vauquelin tried his skill upon it, in 1789, in concert with M. Maquart, who had brought specimens of it from Siberia, but at that time he did not succeed in determining the nature of the acid with which the oxide of lead was combined in it. He examined it again in 1797, and now succeeded in separating an acid to which, from the beautiful colored salts which it forms, he gave the name of chromic. He determined the properties of this acid, and showed that its basis was a new metal to which he gave the name of chromium. He succeeded in obtaining this metal in a separate state, and showed that its protoxide is an exceedingly beautiful green powder. This discovery has been of great importance to the different branches of manufacture in this country. The green oxide is used pretty extensively in painting green on porcelain. It constitutes an exceedingly beautiful green pigment, very permanent and easily applied. The chromic acid, when combined with oxide of lead, forms either a yellow or an orange color upon cotton cloth, both very fixed and exceedingly beautiful colors. In that way it is extensively used by the calico printers, and the bichromate of potash is prepared, in a crystalline form, to a very considerable amount, both in Glasgow and Lancashire, and doubtless in other places. Vauquelin was requested by Hauy to analyze the beryl, a beautiful light green mineral, crystallized in six-sided prisms, which occurs not unfrequently in granite rocks, especially in Siberia. He found it to consist chiefly of silica, united to alumina, and to another earthly body, very like alumina in many of its properties, but differing in others. To this new earth he gave the name of glucina, on account of the sweet taste of its salts, a name not very appropriate, as alumina, yttria, lead, protoxide of chromium, and even protoxide of iron, form salts which are distinguished by a sweet taste likewise. This discovery of glucina confers honor on Vauquelin, as it shows the care with which his analysis must have been conducted. A careless experimenter might easily have confounded glucina with alumina. Vauquelin's mode of distinguishing them was to add sulphate of potash to their solution in sulphuric acid. If the earth in solution was alumina, crystals of alum would form in the course of a short time, but if the earth was glucina, no such crystals would make their appearance, alumina being the basis of alum and not glucina. He showed, too, that glucina is easily dissolved in a solution of carbonate of ammonia, while alumina is not sensibly taken up by that solution. Vauquelin died in 1829 after having reached a good old age. His character was of the very best kind, and his conduct had always been most exemplary. He never interfered with politics, and steered his way through the bloody period of the Revolution, uncontaminated by the vices or violence of any party, and respected and esteemed by every person. Mr. Chenevix deserves also to be mentioned as an improver of analytical chemistry. He was an Irish gentleman who happened to be in Paris during the Reign of Terror, and was thrown into prison and put into the same apartment with several French chemists, whose whole conversation turned upon chemical subjects. He caught the infection, and, after getting out of prison, began to study the subject with much energy and success, and soon distinguished himself as an analytical chemist. His analysis of corundum and sapphire, and his observations on the affinity between magnesia and silica are valuable, and led to considerable improvements in the method of analysis. His analyses of the arseniates of copper, though he demonstrated that several species exist, are not so much to be depended on, because his method of separating and estimating the quantity of arsenic acid is not good. This difficult branch of analysis was not fully understood till afterwards. Chenevix was for several years a most laborious and meritorious chemical experimenter. It is much to be regretted that he should have been induced, in consequence of the mistake into which he fell respecting palladium, to abandon chemistry altogether. Palladium was originally made known to the public by an anonymous handbill which was circulated in London, announcing that palladium, or new silver, was on sale at Mrs. Forster's, and describing its properties. Chenevix, in consequence of the unusual way in which the discovery was announced, naturally considered it as an imposition on the public. He went to Mrs. Forster's and purchased the whole palladium in her possession, and set about examining it, prepossessed with the idea that it was an alloy of some two known metals. After a laborious set of experiments, he considered that he had ascertained it to be a compound of platinum and mercury, or an amalgam of platinum, made in a peculiar way, which he describes. This paper was read at a meeting of the Royal Society by Dr. Wollaston, who was secretary, and afterwards published in their Transactions. Soon after this publication, another anonymous handbill was circulated, offering a considerable price for every grain of palladium made by Mr. Chenevix's process, or by any other process whatever. No person appearing to claim the money thus offered, Dr. Wollaston, about a year after, in a paper read to the Royal Society, acknowledged himself to have been the discoverer of palladium, and related the process by which he had obtained it from the solution of crude platina in aqua regia. There could be no doubt after this that palladium was a peculiar metal, and that Chenevix in his experiments had fallen into some mistake, probably by inadvertently employing a solution of palladium instead of a solution of his amalgam of platinum, and thus giving the properties of the one solution to the other. It is very much to be regretted that Dr. Wollaston allowed Mr. Chenevix's paper to be printed without informing him in the first place of the true history of palladium, and I think that if he had been aware of the bad consequences that were to follow, and that it would ultimately occasion the loss of Mr. Chenevix to the science, he would have acted in a different manner. I have more than once conversed with Dr. Wollaston on the subject, and he assured me that he did everything he could do, short of betraying his secret, to prevent Mr. Chenevix from publishing his paper, that he had called upon and assured him that he himself had attempted his process without being able to succeed, and that he was satisfied that he had fallen into some mistake. As Mr. Chenevix still persisted in his conviction of the accuracy of his own experiments after repeated warnings, perhaps it is not very surprising that Dr. Wollaston allowed him to publish his paper, though, had he been aware of the consequences to their full extent, I am persuaded that he would not have done so. It comes to be a question whether, had Dr. Wollaston informed him of the whole secret, Mr. Chenevix would have been convinced. Another chemist to whom the art of analyzing minerals lies under great obligations is Dr. Frederick Stromeyer, professor of chemistry and pharmacy in the University of Göttingen. He was originally a botanist, and only turned his attention to chemistry when he had the offer of the chemical chair at Göttingen. Then he went to Paris and studied practical chemistry for some years in Vauquelin's laboratory. He has devoted most of his attention to the analysis of minerals, and in the year 1821 published a volume of analyses under the title of Untersuchungen über die Mischung der Mineralkörper und anderer damit verwandten Substanzen. It contains 30 analyses which constitute perfect models of analytical sagacity and accuracy. After Klaproth's Betrage, no book can be named more highly deserving the study of the analytical chemist than Strohmeyer's Untersuchungen. The first paper in this work contains the analysis of aragonite. Chemists had not been able to discover any difference in the chemical constitution of aragonite and calcareous spar, both being compounds of lime, 3.5, and carbonic acid, 2.75. Yet the minerals differ from each other in their hardness, specific gravity, and in the shape of their crystals. Many attempts had been made to account for this difference in characters between these two minerals, but in vain. Mr. Holmes showed that aragonite contained about 1% of water, which is wanting in calcareous spar, and that when aragonite is heated, it crumbles into powder, which is not the case with calcareous spar. But it is not easy to conceive how the addition of 1% of water should increase the specific gravity and the hardness, and quite alter the shape of the crystals of calcareous spar. Strohmeyer made a vast number of experiments upon aragonite with very great care, and the result was that the aragonite from Basthines, near Dax, in the department of Landis, and likewise that from Molina in Aragon, was a compound of 96 carbonate of lime, 4 carbonate of strontian. This amounts to about 35 atoms of carbonate of lime and 1 atom of carbonate of strontian. Now, as the hardness and specific gravity of carbonate of strontian is greater than that of carbonate of lime, we can see a reason why aragonite should be heavier and harder than calcareous spar. More late researches upon different varieties of aragonite enabled him to ascertain that this mineral exists with different proportions of carbonate of strontian. Some varieties contain only 2%, some only 1%, and some only 0.75 or even 0.5%. But he found no specimen among the great number which he analyzed totally destitute of carbonate of strontian. It is true that Vauquelin afterwards examined several varieties in which he could detect no strontian whatever, but as Vauquelin's mineralogical knowledge was very deficient, it comes to be a question whether the minerals analyzed by him were really aragonites or only varieties of the calcareous spar. To Professor Strohmeyer we are likewise indebted for the discovery of the new metal called cadmium, and the discovery does great credit to his sagacity and analytical skill. He is Inspector General of the Apothecaries for the Kingdom of Hanover. While discharging the duties of his office at Hildesheim in the year 1817, he found that the carbonate of zinc had been substituted for the oxide of zinc, ordered in the Hanoverian Pharmacopoeia. This carbonate of zinc was manufactured as Salzgitter. On inquiry, he learned from Mr. Jost, who managed that manufactory, that they had been obliged to substitute the carbonate for the oxide of zinc, because the oxide had a yellow color which rendered it unsaleable. On examining this oxide, Strohmeyer found that it owed its yellow color to the presence of a small quantity of the oxide of a new metal, which he separated, reduced, and examined, and to which he gave the name of cadmium, because it occurs usually associated with zinc. The quantity of cadmium which he was able to obtain from this oxide of zinc was but small. A fortunate circumstance, however, supplied him with an additional quantity, and enabled him to carry his examination of cadmium to a still greater length. During the apothecary's visitation in the state of Magdeburg, there was found, in the possession of several apothecaries, a preparation of zinc from Silesia, made in Hermann's laboratory at Schonbeck, which was confiscated on the supposition that it contained arsenic, because its solution gave a yellow precipitate with sulphuretted hydrogen, which was considered an orpiment. This statement could not be indifferent to Mr. Hermann, as it affected the credit of his manufactory, especially as the medicinal counsellor, Roloff, who had assisted at the visitation, had drawn up a statement of the circumstances which occasioned the confiscation and caused it to be published in Holophan's Medical Journal. He subjected the suspected oxide to a careful examination, but he could not succeed in detecting any arsenic in it. He then requested Roloff to repeat his experiments. This he did, and now perceived that the precipitate, which he had taken for an orpiment, was not so in reality, but owed its existence to the presence of another metallic oxide, different from arsenic, and probably new. Specimens of this oxide of zinc and of the yellow precipitate were sent to Stromeyer for examination, who readily recognized the presence of cadmium, and was able to extract from it a considerable quantity of that metal. End of section 57. Section number 58 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 4, Part 4. It is now 9 years since the first volume of the Untersuchungen was published. All those who are interested in analytical chemistry are anxious for the continuance of that admirable work. By this time he must have collected ample materials for an additional volume, and it could not but add considerably to a reputation already deservedly high. There is no living chemist to whom analytical chemistry lies under greater obligations than to Berzelius, whether we consider the number or the exactness of the analyses which he has made. Jacob Berzelius was educated at Upsala, when Professor Afzelius, a nephew of Bergman, filled the chemical chair, and Ekberg was magister docens in chemistry. Afzelius began his chemical career with considerable éclat, his paper on sulfate of barytes being possessed of very considerable merit. But he is said to have soon lost his health, and to have sunk, in consequence, into listless inactivity. Andrew Gustavus Ekberg was born in Stockholm on the 16th of January, 1767. His father was a captain in the Swedish Navy. He was educated at Kalmar, and in 1784 went to Uppsala, where he devoted himself chiefly to the study of mathematics. He took his degree in 1788, when he wrote a thesis De Olieis Seminum Expressis. In 1789 he went to Berlin, and on his return in 1790 he gave a specimen of his poetical talents by publishing a poem entitled Tal over Freden emallen Sverige och Ryssland, Discourse about the peace between Sweden and Russia. After this he turned his attention to chemistry, and in 1794 was made chemiae docens. In this situation he continued till 1813, when he died on the 11th of February. He had been in such bad health for some time before his death as to be quite unable to discharge the duties of his situation. He published but little, and that little consisted almost entirely of chemical analyses. His first attempt was on phosphate of lime. Then he wrote a paper on the analysis of the topaz, the object of which was to explain Klaproth's method of dissolving hard stony bodies. He made an analysis of gadolinite, and determined the chemical properties of yttria. During these experiments he discovered the new metal to which he gave the name of tantalum, and which Dr. Wollaston afterwards showed to be the same with the columbium of Mr. Hatchett. He also published an analysis of the automolite, of an ore of titanium, and of the mineral water of Medivy. In this last analysis he was assisted by Berzelius, who was then quite unknown to the chemical world. Berzelius has been much more industrious than his chemical contemporaries at Upsala. His first publication was a work in 2 volumes on animal chemistry, chiefly a compilation, with the exception of his experiments on the analysis of blood, which constitute an introduction to the second volume. This book was published in 1806 and 1808. In the year 1806, he and Heisinger began a periodical work entitled Aufhandlingar I Physik, Chemie och Mineralogie, of which 6 volumes in all were published, the last in 1818. In this work there occur 47 papers by Berzelius, some of them of great length and importance, which will be noticed afterwards, but by far the greatest part of them consist of mineral analyses. We have the analysis of cerium by Heisinger and Berzelius, together with an account of the chemical characters of the 2 oxides of cerium. In the 4th volume he gives us a new chemical arrangement of minerals, founded on the supposition that they are all chemical compounds in definite proportions. Mr. Smithson had thrown out the opinion that silica is an acid, which opinion was taken up by Berzelius, who showed, by decisive experiments, that it enters into definite combinations with most of the bases. This happy idea enabled him to show that most of the stony minerals are definite compounds of silica, with certain earths or metallic oxides. This system has undergone several modifications since he first gave it to the world, and I think it more than doubtful whether his last correction of it, published in the Memoirs of the Stockholm Academy for 1824, be quite as good as the first, which he published in 1815. The first arrangement was founded on the bases, the last upon the acids with which the bases are united. He was induced to alter his arrangement in consequence of Mitscherlich's doctrine of isomorphism. But I conceive that the alterations which exist in the constitution of pyroxene, amphibole, garnet, and a few other minerals might be explained in a very simple way without admitting this doctrine of isomorphism, which, if it do not, like Berthollet's hypothesis of indefinite combinations, overturn the whole principles of chemistry, seems scarcely consistent with what we know respecting chemical combination. In the same volume we have a set of experiments on columbium and its characters when reduced to the metallic state, together with an analysis of all the minerals containing columbium that were known in the year 1815. We have also a new examination of the properties of yttria, together with the analysis of a number of minerals containing both cerium and yttria, and the mode of separating these 2 substances from each other by means of sulfate of potash. In the 6th volume we have his discovery of selenium, with an account of selenic acid, and the different compounds which it forms. Since the year 1818 his papers have been all published in the Memoirs of the Stockholm Academy, but he has taken care to have translations of them inserted into Pogensdorf's Annalen and the Annales de Chimie et de Physique. In the Stockholm Memoirs for 1819 we have his analysis of wavellite, showing that this mineral is a hydrous phosphate of alumina. The same analysis and discovery had been made by Fuchs, who published his results in 1818, but probably Berzelius had not seen the paper. At least he takes no notice of it. We have also in the same volume his analysis of euclase, of silicate of zinc, and his paper on the prussiates. In the Memoirs for 1820 we have, besides 3 others, his paper on the mode of analyzing the ores of nickel. In the Memoirs for 1821 we have his paper on the alkaline sulphurates, and his analysis of achmite. The specimen selected for this analysis was probably impure, for 2 successive analyses of it, made in my laboratory by Captain Lehunt, gave a considerable difference in the proportion of the constituents, and a different formula for the composition than that resulting from the constituents found by Berzelius. In the Memoirs for 1822 we have his analysis of the mineral waters of Carlsbad. In 1823 he published his experiments on uranium, which were meant as a confirmation and extension of the examination of this substance previously made by Arvidson. In the same year appeared his experiments on fluoric acid and its combinations, constituting one of the most curious and important of all the numerous additions which he has made to analytical chemistry. In 1824 we have his analysis of phosphate of yttria, a mineral found in Norway; of poligmonite, a mineral from the neighborhood of Christiania, where it occurs in the zircon saonite, and remarkable for the great number of bases which it contains united to titanic acid, namely zirconia, oxide of iron, lime, oxide of manganese, oxide of cerium, and yttria. We have also his analysis of arseniate of iron, from Brazil and from Cornwall, and of chabasite from Ferro. In this last analysis he mentions chabasites from Scotland containing soda instead of lime. The only chabasites in Scotland that I know of occur in the neighbourhood of Glasgow, and in none of these have I found any soda. But I have found soda instead of lime in chabasites from the north of Ireland, always crystallized in the form to which Hauy has given the name of trirhomboidal. I think, therefore, that the chabasites analyzed by Arvidson, to which Berzelius refers, must have been from Ireland and not from Scotland, and I think it may be a question whether this form of crystal, if it should always be found to contain soda instead of lime, ought not to constitute a peculiar species. In 1826 we have his very elaborate and valuable paper on sulfur salts. In this paper he shows that sulfur is capable of combining with bodies in the same way as oxygen, and of converting the acidifiable bases into acids and the alkalifiable bases into alkalis. These sulfur acids and alkalis unite with each other and form a new class of saline bodies, which may be distinguished by the name of sulfur salts. This subject has been since carried a good deal further by M.H. Rose, who has by means of it thrown much light on some mineral species hitherto quite inexplicable. Thus, what is called nickel glance is a sulfur salt of nickel. The acid is a compound of sulfur and arsenic, the base a compound of sulfur and nickel. Its composition may be represented thus: 1 atom disulfide of arsenic, 1 atom disulfide of nickel. In like manner, glance cobalt is 1 atom disulfide of arsenic, 1 atom disulfide of nickel. Zinkenite is composed of 3 atoms sulfide of antimony, 1 atom sulfide of lead, and jamesonite of 2½ atoms sulfide of antimony, 1 atom sulfide of lead. Feather ore of antimony, hitherto confounded with sulphuret of antimony, is a compound of 5 atoms sulfide of antimony, 3 atoms sulfide of lead. Gray copper ore, which has hitherto appeared so difficult to be reduced to anything like regularity, is composed of 1 atom sulfide of antimony or arsenic, 2 atoms sulfide of copper or silver. Dark red silver ore is composed of 1 atom sulfide of antimony, 1 atom sulfide of silver, and light red silver ore of 2 atoms sesquisulfide of arsenic, 3 atoms sulfide of silver. These specimens show how much light the doctrine of sulfur salts has thrown on the mineral kingdom. In 1828, he published his experimental investigation of the characters and compounds of palladium, rhodium, osmium, and iridium, and upon the mode of analyzing the different ores of platinum. One of the greatest improvements which Berzelius has introduced into analytical chemistry is his mode of separating those bodies which become acid when united to oxygen, as sulfur, selenium, arsenic, etc., from those that become alkaline, as copper, lead, silver, etc. His method is to put the alloy or ore to be analyzed into a glass tube, and to pass over it a current of dry chlorine gas, while the powder in the tube is heated by lamp. The acidifiable bodies are volatile, and pass over along the tube into a vessel of water placed to receive them, while the alkalifiable bodies remain fixed in the tube. This mode of analysis has been considerably improved by Rose, who availed himself of it in his analysis of gray copper ore and other similar compounds. Analytical chemistry lies under obligations to Berzelius, not merely for what he has done himself, but for what has been done by those pupils who were educated in his laboratory. Bonsdorf, Nordenskjöld, C. G. Gmelin, Rose, Wohler, Arvidsson have given us some of the finest examples of analytical investigations with which the science is furnished. P. A. von Bonsdorf was a professor of Abo, and after that university was burnt down, he moved to the new locality in which it was planted by the Russian government. His analysis of the minerals which crystallize in the form of the amphibole constitutes a model for the young analyst to study. Whether we consider the precision of the analyses, or the methods by which the different constituents were separated and estimated. His analysis of red-silver ore first demonstrated that the metals in it were not in the state of oxides. The nature of the combination was first completely explained by Rose, after Berzelius's paper on the sulfur salts had made its appearance. His paper on the acid properties of several of the chlorides has served considerably to extend and to rectify the views first proposed by Berzelius respecting the different classes of salts. Niels Nordenskjöld is superintendent of the mines in Finland. His Bidrag till närmare kännedom of Finlands mineralia och geonosi was published in 1820. It contains a description and analysis of 14 species of Lapland minerals, several of them new and all of them interesting. The analyses were conducted in Berzelius's laboratory and are excellent. In 1827 he published a tabular view of the mineral species, arranged chemically, in which he gives the crystalline form, hardness, and specific gravity, together with the chemical formulas for the composition. C.G. Gmelin is professor of chemistry at Tübingen. He has devoted the whole of his attention to chemical analysis, and has published a great number of excellent ones, particularly in Schweiger's journal. His analysis of helvine and of the tourmaline may be specified as particularly valuable. In this last mineral, he demonstrated the presence of boracic acid. Leopold Gmelin, professor of chemistry at Heidelberg, has also distinguished himself as an analytical chemist. His System of Chemistry, which is at present publishing, promises to be the best and most perfect which Germany has produced. Henry Rose, of Berlin, is the son of that M. Rose who was educated by Klaproth, and afterwards became the intimate friend and fellow laborer of that illustrious chemist. He has devoted himself to analytical chemistry with indefatigable zeal, and has favored us with a prodigious number of new and admirably conducted analyses. His analyses of pyroxenes, of the ores of titanium, of gray copper ore, of silver glance, of red silver ore, miragerite, polybasite, etc., may be mentioned as examples. In 1829 he published a volume on analytical chemistry, which is by far the most complete and valuable work of the kind that has hitherto appeared, and ought to be carefully studied by all those who wish to make themselves masters of the difficult but necessary art of analyzing compound bodies. Wohler is professor of chemistry in the Polytechnic School of Berlin. He does not appear to have turned his attention to analytical chemistry, but rather towards extending our knowledge of the compounds which the different simple bodies are capable of forming with each other. His discovery of cyanic acid may be mentioned as a specimen. He is active and young. Much, therefore, may be expected from him. Augustus Arvidsson has distinguished himself by the discovery of the new fixed alkali, lithia, in petalite and spodumene. It has been lately ascertained at Moscow by M. R. Hermann, and the experiments have been repeated and confirmed by Berzelius, that lithia is a much lighter substance than it was found to be by Arvidsson, its atomic weight being only 1.75. We have from Arvidsson an important set of experiments on uranium and its oxides, and on the action of hydrogen on the metallic sulphurets. He has likewise analyzed a considerable number of minerals with great care, but of late years he seems to have lost his activity. His analysis of chrysoberyl does not possess the accuracy of the rest. By some inadvertence he has taken a compound of glucina and alumina for silica. I ought to have included Walmstedt and Trolle Walkmeister among the Swedish chemists who have contributed important papers towards the progress of analytical chemistry, the memoirs of the former on chrysolite, and of the latter on the garnets, being peculiarly valuable. But it would extend this work to an almost interminable length if I were to particularize every meritorious experimenter. This must plead my excuse for having omitted the names of Buchholz, Galen, Fuchs, Dumasnil, Dobreiner, Kupfer, and various other meritorious chemists who have contributed so much to the perfecting of the chemical analysis of the mineral kingdom. But it would be unpardonable to leave out the name of M. Mitscherlich, professor of chemistry in Berlin, and successor of Klaproth, who was also a pupil of Berzelius. He has opened a new branch of chemistry to our consideration. His papers on isomorphous bodies, on the crystalline forms of various sets of salts, on the artificial formation of various minerals, do him immortal honor, and will hand him down to posterity as a fit successor of his illustrious predecessors in the chemical chair of Berlin, a city in which an uninterrupted series of first-rate chemists have followed each other for more than a century, and where, thanks to the fostering care of the Prussian government, the number was never greater than at the present moment. The most eminent analytical chemists at present in France are Laugier, a nephew and successor of Fourcroy, as professor of chemistry in the Jardin du Roi, and Berthier, who has long had the superintendence of the laboratory of the School of Mines. Laugier has not published many analyses to the world, but those with which he has favored us appear to have been made with great care, and are in general very accurate. Berthier is a much more active man, and has not merely given us many analyses, but has made various important improvements in the analytical processes. His mode of separating arsenic acid and determining its weight is now generally followed, and I can state from experience that his method of fusing minerals with oxide of lead when the object is to detect an alkali is both accurate and easy. Berthier is young and active and zealous. We may therefore expect a great deal from him hereafter. End of section 58. Section 59 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas Thompson, Volume 2, Chapter 4, Part 5. The chemists in Great Britain have never hitherto distinguished themselves much in analytical chemistry. This I conceive is owing to the mode of education which has been hitherto unhappily followed. Till within these very few years, practical chemistry has been nowhere taught. The consequence has been that every chemist must discover processes for himself, and a long time elapses before he acquires the requisite dexterity and skill. About the beginning of the present century, Dr. Kennedy of Edinburgh was an enthusiastic and dexterous analyst, but unfortunately he was lost to the science by a premature death, after giving a very few, but these masterly, analyses to the public. About the same time, Charles Hatchett, Esquire, was an active chemist, and published not a very few excellent analyses, but unfortunately this most amiable and accomplished man has been lost to science for more than a quarter of a century, the baneful effects of wealth and the cares of a lucrative and extensive business having completely weaned him from scientific pursuits. Mr. Gregor of Cornwall was an accurate man, and attended only to analytical chemistry. His analyses were not numerous, but they were in general excellent. Unfortunately, the science was deprived of his services by a premature death. The same observation applies equally to Mr. Edward Howard, whose analyses of meteoric stones form an era in this branch of chemistry. He was not only a skillful chemist, but was possessed of a persevering industry which peculiarly fitted him for making a figure as a practical chemist. Of modern British analytical chemists, undoubtedly the first is Mr. Richard Phillips, to whom we are indebted for not a few analyses, conducted with great chemical skill and performed with great accuracy. Unfortunately, of late years he has done little, having been withdrawn from science by the necessity of providing for a large family, which can hardly be done, in this country, except by turning one's attention to trade or manufactures. The same remark applies to Dr. Henry, who has contributed so much to our knowledge of gaseous bodies, and whose analytical skill, had it been wholly devoted to scientific investigations, would have raised his reputation as a discoverer much higher than it has attained, although the celebrity of Dr. Henry, even under the disadvantages of being a manufacturing chemist, is deservedly very high. Of the young chemists who have but recently started in the path of analytical investigation, we expect the most from Dr. Turner of the London University. His analyses of the ores of manganese are admirable specimens of skill and accuracy, and have completely elucidated a branch of mineralogy which, before his experiments and the descriptions of Heidinger appeared, was buried in impenetrable darkness. No man that Great Britain has produced was better fitted to have figured as an analytical chemist, both by his uncommon chemical skill and the powers of his mind, which were of the highest order, than Mr. Smithson Tennant, had he not been in some measure prevented by a delicate frame of body, which produced in him a state of indolence somewhat similar to that of Dr. Black. His discovery of osmium and iridium, and his analysis of emery and magnesian limestone, may be mentioned as proofs of what he could have accomplished had his health allowed him a greater degree of exertion. His experiments on the diamond first demonstrated that it was composed of pure carbon, while his discovery of phosphoret of lime has furnished lecturers on chemistry with one of the most brilliant and beautiful of those exhibitions which they are in the habit of making to attract the attention of their students. Smithson Tennant was the only child of the Reverend Calvert Tennant, youngest son of a respectable family in Wensleydale, near Richmond, in Yorkshire, and vicar of Selby in that county. He was born on the 30th of November, 1761. He had the misfortune to lose his father when he was only 9 years of age, and before he attained the age of manhood he was deprived likewise of his mother by a very unfortunate accident. She was thrown from her horse while riding with her son, and killed on the spot. His education, after his father's death, was irregular and apparently neglected. He was sent successively to different schools in Yorkshire, at Scorton, Tadcaster, and Beverley. He gave many proofs while young of a particular turn for chemistry and natural philosophy, both by reading all books of that description which fell in his way, and by making various little experiments which the perusal of these books suggested. His first experiment was made at 9 years of age, when he prepared a quantity of gunpowder for fireworks, according to directions contained in some scientific book to which he had access. In the choice of a profession, his attention was naturally directed towards medicine, as being more nearly allied to his philosophical pursuits. He went accordingly to Edinburgh, about the year 1781, where he laid the foundation of his chemical knowledge under Dr. Black. In 1782 he was entered a member of Christ's College, Cambridge, where he began from that time to reside. He was first entered as a pensioner, but disliking the ordinary discipline and routine of an academical life, he obtained an exemption from those restraints by becoming a fellow commoner. During his residence at Cambridge, his chief attention was bestowed on chemistry and botany, though he made himself also acquainted with the elementary parts of mathematics, and had mastered the most important parts of Newton's Principia. In 1784 he travelled into Denmark and Sweden, chiefly with the view of becoming personally acquainted with Scheele, for whom he had imbibed a high admiration. He was much gratified by what he saw of this extraordinary man, and was particularly struck with the simplicity of the apparatus with which his great experiments had been performed. On his return to England, he took great pleasure in showing his friends at Cambridge various mineralogical specimens, which had been presented to him by Scheele, and in exhibiting several interesting experiments which he had learned from that great chemist. A year or two afterwards he went to France, to become personally acquainted with the most eminent of the French chemists. Thence he went to Holland and the Netherlands, at that time in a state of insurrection against Joseph II. In 1786 he left Christ College along with Professor Hermann, and removed with him to Emmanuel College. In 1788 he took his first degree as Bachelor of Physic, and soon after acquitted Cambridge and came to reside in London. In 1791 he made his celebrated analysis of carbonic acid, which fully confirmed the opinions previously stated by Lavoisier respecting the constituents of this substance. His mode was to pass phosphorus through red-hot carbonate of lime. The phosphorus was acidified and charcoal deposited. It was during these experiments that he discovered phosphuret of lime. In 1792 he again visited Paris, but from circumstances, being afraid of a convulsion, he was fortunate enough to leave that city the day before the memorable 10th of August. He traveled through Italy, and then passed through part of Germany. On his return to Paris, in the beginning of 1793, he was deeply impressed with the gloom and desolation arising from the system of terror then beginning to prevail in that capital. On calling in the house of M. Delametherie, of whose simplicity and moderation he had a high opinion, he found the doors and windows closed, as if the owner were absent. Being at length admitted, he found his friends sitting in a back room, by candlelight, with the shutters closed in the middle of the day. On his departure, after a hurried and anxious conversation, his friend conjured him not to come again, as the knowledge of his being there might be attended with serious consequences to them both. To the honor of Delametherie, it deserves to be stated that through all the inquisitions of the Revolution, he preserved for his friend property of considerable value, which Mr. Tennant had entrusted to his care. On his return from the Continent, he took lodgings in the Temple, where he continued to reside during the rest of his life. He still continued the study of medicine, and attended the hospitals, but became more indifferent about entering into practice. He took, however, a doctor's degree at Cambridge in 1796, but resolved, as his fortune was independent, to relinquish all idea of practice, as not likely to contribute to his happiness. Exquisite sensibility was a striking feature in his character, and it would, as he very properly conceived, have made him peculiarly unfit for the exercise of the medical profession. It may be worth while to relate an example of his practical benevolence which happened about this time. He had a steward in the country, in whom he had long placed implicit confidence, and who was considerably indebted to him. In consequence of this man's becoming embarrassed in his circumstances, Mr. Tennant went into the country to examine his accounts. A time and place were appointed for him to produce his books and show the extent of the deficiency, but the unfortunate steward felt himself unequal to the task of such an explanation, and in a fit of despair put an end to his existence. Touched by this melancholy event, Mr. Tennant used his utmost exertions for the relief and protection of the family whom he had left, and not only forgave them the debt, but afforded them pecuniary assistance, and continued ever afterwards to be their friend and benefactor. During the year 1796, he made his experiments to prove that the diamond is pure carbon. His method was to heat it in a gold tube with saltpeter. The diamond was converted into carbonic acid gas, which combined with the potash from the saltpeter, and by the evolution of which the quantity of carbon in a given weight of diamond might be estimated. A characteristic trait of Mr. Tennant occurred during the course of this experiment, which I relate on the authority of Dr. Wollaston, who was present as an assistant, and who related the fact to me. Mr. Tennant was in the habit of taking a ride on horseback every day at a certain hour. The tube containing the diamond and saltpeter were actually heating, and the experiment considerably advanced, when, suddenly recollecting that his hour for riding was come, he left the completion of the process to Dr. Wollaston, and went out as usual to take his ride. In the year 1797, in consequence of a visit to a friend in Lincolnshire, where he witnessed the activity with which improvements in farming operations were at that time going on, he was induced to purchase some land in that country, in order to commence farming operations. In 1799, he bought a considerable tract of waste land in Somersetshire, near the village of Cheddar, where he built a small house, in which, during the remainder of his life, he was in the habit of spending some months every summer, besides occasional visits at other times of the year. These farming speculations, as might have been anticipated from the indolent and careless habits of Mr. Tennant, were not very successful. Yet it appears from the papers which he left behind him that he paid considerable attention to agriculture, that he had read the best books on the subject, and collected many facts on it during his different journeys through various parts of England. In the course of these inquiries he had discovered that there were two kinds of limestone known in the Midland countries of England, one of which yielded a lime injurious to vegetation. He showed in 1799 that the presence of carbonate of magnesia is the cause of the bad qualities of this latter kind of limestone. He found that the magnesian limestone forms an extensive stratum in the Midland counties, and that it occurs also in primitive districts under the name of dolomite. He infers from the slow solubility of this limestone in acids that it is a double salt composed of carbonate of lime and carbonate of magnesia in chemical combination. He found that grain would scarcely germinate, and that it soon perished in moistened carbonate of magnesia. Hence he concluded that magnesia is really injurious to vegetation. Upon this principle he accounted for the injurious effects of the magnesian limestone when employed as a manure. In 1802 he showed that emery is merely a variety of corundum, or of the precious stone known by the name of sapphire. During the same year, while endeavoring to make an alloy of lead with the powder which remains after treating crude platinum with aqua regia, he observed remarkable properties in this powder, and found that it contained a new metal. While he was engaged in the investigation, Descoutils had turned his attention to the same powder, and had discovered that it contained a metal which gives a red color to the ammoniacal precipitate of platinum. Soon after, Vauquelin, having treated the powder with alkali, obtained a volatile metallic oxide, which he considered as the same metal that had been observed by Descoutils. In 1804, Mr. Tennant showed that this powder contains two new metals, to which he gave the name of osmium and iridium. Mr. Tennant's health by this time had become delicate, and he seldom went to bed without a certain quantity of fever, which often obliged him to get up during the night and expose himself to the cold air. To keep himself in any degree in health, he found it necessary to take a great deal of exercise on horseback. He was always an awkward and a bad horseman, so that these rides were sometimes a little hazardous, and I have more than once heard him say that a fall from his horse would some day prove fatal to him. In 1809 he was thrown from his horse near Brighton and had his collarbone broken. In the year 1812 he was prevailed upon to deliver a few lectures on the principles of mineralogy to a number of his friends, among whom were many ladies, and a considerable number of men of science and information. These lectures were completely successful, and raised his reputation very much among his friends as a lecturer. He particularly excelled in the investigation of minerals by the blowpipe, and I have heard him repeatedly say that he was indebted for the first knowledge of the mode of using that valuable instrument to Assessor Gagne Fallon. In 1813, a vacancy occurring in the chemical professorship at Cambridge, he was solicited to become a candidate. His friends exerted themselves in his favor with unexampled energy, and all opposition being withdrawn, he was elected professor in May 1813. After the general pacification in 1814, he went to France and repaired to the southern provinces of that kingdom. He visited Lyons, Nîmes, Avignon, Marseille, and Montpellier. He returned to Paris in November, much gratified by his southern tour. He was to have returned to England about the latter end of the year, but he continued to linger on till the February following. On the 15th of that month he went to Calais, but the wind blew directly into Calais harbor, and continued unfavorable for several days. After waiting till the 20th, he went to Boulogne, in order to take the chance of a better passage from that port. He embarked on board a vessel on the 22nd, but the wind was still adverse, and blew so violently that the vessel was obliged to put back. When Mr. Tennant came ashore, he said that it was in vain to struggle with the elements, and that he was not yet tired of life. It was determined, in case the wind should abate, to make another trial in the evening. During the interval, Mr. Tennant proposed to his fellow traveller, Baron Bülow, that they should hire horses and take a ride. They rode at first along the seaside, but on Mr. Tennant's suggestion they went afterwards to Bonaparte's pillar, which stands on an eminence about a league from the seashore, and which, having been to see it the day before, he was desirous of showing to Baron Bülow. On their return from thence they deviated a little from the road, in order to look at a small fort near the pillar, the entrance to which was over a fosse 20 feet deep. On the side toward them there was a standing bridge for some way, till it joined a drawbridge, which turned on a pivot. The end next the fort rested on the ground. On the side next to them it was usually fastened by a bolt, but the bolt had been stolen about a fortnight before, and was not replaced. As the bridge was too narrow for them to go abreast, the Baron said he would go first, and attempted to ride over it, but perceiving that it was beginning to sink, he made an effort to pass the centre, and called out to warn his companion of his danger. But it was too late. They were both precipitated into the trench. The Baron, though much stunned, fortunately escaped without any serious hurt, but on recovering his senses, and looking round for Mr. Tennant, he found him lying under his horse, nearly lifeless. He was taken, however, to the civil hospital, as the nearest place ready to receive him. After a short interval, he seemed in some slight degree to recover his senses, and made an effort to speak, but without effect, and died within the hour. His remains were interred a few days after in the public cemetery at Boulogne, being attended to the grave by most of the English residents. End of section 59. Section 60 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lisa McCleskey. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 4, Part 6. There is another branch of investigation intimately connected with analytical chemistry, the improvements in which have been attended with great advantage, both to mineralogists and chemists. I mean the use of the blowpipe, to make a kind of miniature analysis of minerals in the dry way, so far, at least, as to determine the nature of the constituents of the mineral under examination. This is attended with many advantages, as a preliminary to a rigid analysis by solution. By informing us of the nature of the constituents, it enables us to form a plan of the analysis beforehand, which, in many cases, saves the trouble and the tediousness of two separate analytical investigations. For when we set about analyzing a mineral, of the nature of which we are entirely ignorant, two separate sets of experiments are in most cases indispensable. We must examine the mineral in the first place to determine the nature of its constituents. These being known, we can form a plan of an analysis, by means of which we can separate and estimate in succession the amount of each constituent of the mineral. Now, a judicious use of the blowpipe often enables us to determine the nature of the constituents in a few minutes, and thus saves the trouble of the preliminary analysis. The blowpipe is a tube employed by goldsmiths in soldering. By means of it, they force the flame of a candle or lamp against any particular point which they wish to heat. This enables them to solder trinkets of various kinds, without affecting any other part, except the portion which is required to be heated. Cronstedt and Angstrom first thought of applying this little instrument to the examination of minerals. A small fragment of the mineral to be examined, not nearly so large as the head of a pin, was put upon a piece of charcoal, and the flame of a candle was made to play upon it by means of a blowpipe, so as to raise it to a white heat. They observed whether it decrepitated, or was dissipated, or melted, and whatever the effect produced was, they were enabled from it to draw consequences respecting the nature of the mineral under examination. The importance of this instrument struck Bergman, and induced him to wish for a complete examination of the action of the heat of the blowpipe upon all different minerals, either tried per se upon charcoal, or mixed with various fluxes. For 3 different substances had been chosen as fluxes, namely carbonate of soda, borax, and biphosphate of soda, or at least what was in fact an equivalent for this last substance, ammoniaphosphate of soda, or microcosmic alt, at that time extracted from urine. This salt is a compound of 1 integrant particle of phosphate of soda and 1 integrant particle of phosphate of ammonia. When heated before the blowpipe, it fuses, and the water of crystallization, together with the ammonia, are gradually dissipated, so that at last nothing remains but biphosphate of soda. These fluxes have been found to act with considerable energy on most minerals. The carbonate of soda readily fuses with those that contain much silica, while the borax and biphosphate of soda act most powerfully on the bases, not sensibly affecting the silica, which remains unaltered in the fused bead. A mixture of borax and carbonate of soda upon charcoal, in general, enables us to reduce the metallic oxides to the state of metals, provided we understand the way of applying the flame properly. Bergman employed Gahn, who was at that time his pupil, and whose skill he was well acquainted with, to make the requisite experiments. The result of these experiments was drawn up into a paper which Bergman sent to Baron Born in 1777, and they were published by him at Vienna in 1779. This valuable publication threw a new light upon the application of the blowpipe to the assaying of minerals, and for everything new which it contained Bergman was indebted to Gahn, who had made the experiments. John Gottlieb Gahn, the intimate friend of Bergman and of Scheele, was one of the best informed men, and one whose manners were the most simple, unaffected, and pleasing of all the men of science with whom I ever came in contact. I spent a few days with him at Fallon in 1812, and they were some of the most delightful days that I ever passed in my life. His fund of information was inexhaustible, and was only excelled by the charming simplicity of his manners, and by the benevolence and goodness of heart which beamed in his countenance. He was born on the 17th of August, 1745, at the Waxna Iron Works in South Helsingland, where his father, Hans Jacob Gahn, was treasurer to the government of Stora Kopparberg. His grandfather, or great-grandfather, he told me, had emigrated from Scotland, and he mentioned several families in Scotland to which he was related. After completing his school education at Westeros, he went in the year 1760 to the University of Uppsala. He had already shown a decided bias toward the study of chemistry, mineralogy, and natural philosophy, and like most men of science in Sweden, where philosophical instrument makers are scarcely to be found, he had accustomed himself to handle the different tools, and to supply himself in that manner with all the different pieces of apparatus which he required for his investigations. He seems to have spent nearly 10 years at Uppsala, during which time he acquired a very profound knowledge in chemistry, and made various important discoveries which his modesty or his indifference to fame made him allow others to pass as their own. The discovery of the rhomboidal nucleus of carbonate of lime in a 6-sided prism of that mineral, which he let fall, and which was accidentally broken, constitutes the foundation of Hauy's system of crystallization. He communicated the fact to Bergman, who published it as his own in the 2nd volume of his Opuscula, without any mention of Gahn's name. The earth of Bones had been considered as a peculiar simple earth, but Gahn ascertained by analysis that it was a compound of phosphoric acid and lime, and this discovery he communicated to Scheele, who, in his paper on fluorspar, published in 1771, observed, in the 17th section in which he is describing the effect of phosphoric acid on fluorspar, "It has lately been discovered that the earth of bones or of horns is calcareous earth combined with phosphoric acid." In consequence of this remark, in which the name of Gahn does not appear, it was long supposed that Scheele and not Gahn was the author of this important discovery. It was during this period that he demonstrated the metallic nature of manganese, and examined the properties of the metal. This discovery was announced as his, at the time, by Bergman, and was almost the only one of the immense number of new facts which he had ascertained that was publicly known to be his. On the death of his father, he was left in rather narrow circumstances, which obliged him to turn his immediate attention to mining and metallurgy. To acquire a practical knowledge of mining, he associated with the common miners, and continued to work like them till he had acquired all the practical dexterity and knowledge which actual labor could give. In 1770 he was commissioned by the College of Mines to institute a course of experiments, with a view to improve the method of smelting copper at Fallon. The consequence of this investigation was a complete regeneration of the whole system, so as to save a great deal both of time and fuel. Some time after, he became a partner in some extensive works at Stora Kopparberg, where he settled as a superintendent. From 1770, when he first settled at Fallon, down to 1785, he took a deep interest in the improvement of the chemical works in that place and neighborhood. He established manufactories of sulfur, sulfuric acid, and red ochre. In 1780, the Royal College of Mines, as a testimony of their sense of the value of Gahn's improvements, presented him with a gold medal of merit. In 1782, he received a royal patent as mining master. In 1784, he was appointed assessor in the Royal College of Mines, in which capacity he officiated as often as his other vocations permitted him to reside in Stockholm. The same year he married Anna Maria Bergstrom, with whom he enjoyed for 31 years a life of uninterrupted happiness. By his wife he had a son and 2 daughters. In the year 1773, he had been elected chemical stipendiary to the Royal College of Mines, and he continued to hold this appointment till the year 1814. During the whole of this period, the solution of almost every difficult problem remitted to the college devolved upon him. In 1795, he was chosen a member of the committee for directing the general affairs of the kingdom. In 1810, he was made one of the committee for the general maintenance of the poor. In 1812, he was elected an active associate of the Royal Academy for Agriculture, and in 1816, he became a member of the committee for organizing the plan of a mining institute. In 1818, he was chosen a member of the Committee of the Mint, but from this situation he was shortly after, at his own request, permitted to withdraw. His wife died in 1815, and from that period his health, which had never been robust, visibly declined. Nature occasionally made an effort to shake off the disease, but it constantly returned with increasing strength, until, in the autumn of 1818, the decay became more rapid in its progress, and more decided in its character. He became gradually weaker, and on the 8th of December, 1818, died without a struggle, and seemingly without pain. Ever after the experiments on the blowpipe which Gahn performed at the request of Bergman, his attention had been turned to that piece of apparatus, and during the course of a long life he had introduced so many improvements that he was enabled, by means of the blowpipe, to determine in a few minutes the constituents of almost any mineral. He had gone over almost all the mineral kingdom, and determined the behavior of almost every mineral before the blowpipe, both by itself and when mixed with the different fluxes and reagents which he had invented for the purpose of detecting the different constituents. but from his characteristic unwillingness to commit his observations and experiments to writing, or to draw them up into a regular memoir, had not Berzelius offered himself as an assistant, they would probably have been lost. By his means, a short treatise on the blowpipe, with minute directions how to use the different contrivances which he had invented, was drawn up and inserted into the second volume of Berzelius's Chemistry. Berzelius and he afterwards examined all the minerals known, or at least which they could procure, before the blowpipe, and the result of the whole constituted the materials of Berzelius's treatise on the blowpipe, which has been translated into German, French, and English. It may be considered as containing the sum of all the improvements which Gahn had made on the use of the blowpipe, together with all the facts that he had collected respecting the phenomena exhibited by minerals before the blowpipe. It constitutes an exceedingly useful and valuable book, and ought to make a part of the library of every analytical chemist. Dr. Wollaston had paid as much attention to the blowpipe as Gahn, and had introduced so many improvements into its use, that he was able, by means of it, to determine the nature of the constituents of any mineral in the course of a few minutes. He was fond of such analytical experiments, and was generally applied to by every person who thought himself possessed of a new mineral, in order to be enabled to state what its constituents were. The London mineralogist, if the race be not extinct, must sorely feel the want of the man to whom they were in the habit of applying on all occasions, and to whom they never applied in vain. Dr. William Hyde Wollaston was the son of the Reverend Dr. Wollaston, a clergyman of some rank in the Church of England, and possessed of a competent fortune. He was a man of abilities, and rather eminent as an astronomer. His grandfather was the celebrated author of The Religion of Nature Delineated. Dr. William Hyde Wollaston was born about the year 1767, and was one of 15 children, who all reached the age of manhood. His constitution was naturally feeble, but by leading a life of the strictest sobriety and abstemiousness, he kept himself in a state fit for mental exertion. He was educated at Cambridge, where he was at one time a fellow. After studying medicine, by attending the hospitals and lectures in London, and taking his degree of doctor at Cambridge, he settled at Bury St. Edmunds, where he practised as a physician for some years. He then went to London, became a fellow of the Royal College of Physicians, and commenced practitioner in the metropolis. A vacancy occurring in St. George's Hospital, he offered himself for the place of physician to that institution, but another individual, whom he considered his inferior in knowledge and science, having been preferred before him, he threw up the profession of medicine altogether, and devoted the rest of his life to scientific pursuits. His income, in consequence of the large family of his father, was of necessity small. In order to improve it, he turned his thoughts to the manufacture of platinum, in which he succeeded so well that he must have, by means of it, realized considerable sums. It was he who first succeeded in reducing it into ingots in a state of purity and fit for every kind of use. It was employed, in consequence, for making vessels for chemical purposes, and it is to its introduction that we are to ascribe the present accuracy of chemical investigations. It has been gradually introduced into the sulphuric acid manufactories as a substitute for glass retorts. Dr. Wollaston had a particular turn for contriving pieces of apparatus for scientific purposes. His reflecting goniometer was a most valuable present to mineralogists, and it is by its means that crystallography has acquired the great degree of perfection which it has recently exhibited. He contrived a very simple apparatus for ascertaining the power of various bodies to refract light. His camera lucida furnished those who were ignorant of drawing with a convenient method of delineating natural objects. His periscopic glasses must have been found useful, for they sold rather extensively, and his sliding rule for chemical equivalents furnished a ready method for calculating the proportions of one substance necessary to decompose a given weight of another. Dr. Wollaston's knowledge was more varied and his taste less exclusive than any other philosopher of his time, except Mr. Cavendish. But optics and chemistry are the two sciences which lie under the greatest obligations to him. His first chemical paper on urinary calculi at once added a vast deal to what had been previously known. He first pointed out the constituents of the mulberry calculi, showing them to be composed of oxalate of lime and animal matter. He first distinguished the nature of the triple phosphates. It was he who first ascertained the nature of the cystic oxides and of the chalkstones, which appear occasionally in the joints of gouty patients. To him we owe the first demonstration of the identity of galvanism and common electricity, and the first explanation of the cause of the different phenomena exhibited by galvanic and common electricity. To him we are indebted for the discovery of palladium and rhodium, and the first account of the properties and characters of these two metals. He first showed that oxalic acid and potash unite in 3 different proportions, constituting oxalate, binoxalate, and quadroxalate of potash. Many other chemical facts, first ascertained by him, are to be found in the numerous papers of his scattered over the last 40 volumes of the Philosophical Transactions, and perhaps not the least valuable of them is his description of the mode of reducing platinum from the raw state and bringing it into the state of an ingot. Dr. Wollaston died in the month of January, 1829, in consequence of a tumor formed in the brain, near, if I remember right, the thalami nervosum opticorum. There is reason to suspect that this tumor had been some time in forming. He had, without exception, the sharpest eye that I have ever seen. He could write with a diamond upon glass in a character so small that nothing could be distinguished by the naked eye but a ragged line. Yet when the letters were viewed through a microscope, they were beautifully regular and quite legible. He retained his senses to almost the last moment of his life. When he lay apparently senseless, and his friends were anxiously solicitous whether he still retained his understanding, he informed them, by writing, that his senses were still perfectly entire. Few individuals ever enjoyed a greater share of general respect and confidence, or had fewer enemies, than Dr. Wollaston. He was at first shy and distant, and remarkably circumspect, but he grew insensibly more and more agreeable as you got better acquainted with him, till at last you formed for him the most sincere friendship, and your acquaintance ended in the warmest and closest attachment. End of section 60.
Section 61 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 5, of Electro-chemistry, Part 1. Electricity, like chemistry, is a modern science, for it can scarcely claim an older origin than the termination of the first quarter of the preceding century. And during the last half of that century, and a small portion of the present, it participated with chemistry in the zeal and activity with which it was cultivated by the philosophers of Europe and America. For many years, it was not suspected that any connection existed between chemistry and electricity, though some of the meteorological phenomena, especially the production of clouds and the formation of rain, which are obviously connected with chemistry, seem likewise to claim some connection with the agency of electricity. The discovery of the intimate relation between chemistry and electricity was one of the consequences of a controversy carried on about the year 1790 between Galvani and Volta, 2 Italian philosophers, whose discoveries will render their names immortal. Galvani, who was a professor of anatomy, was engaged in speculations respecting muscular motion. He was of opinion that a peculiar fluid was secreted in the brain, which was sent along the nerves to all the different parts of the body. This nervous fluid possessed many characters analogous to those of electricity. The muscles were capable of being charged with it somewhat like a Leyden vial, and it was by the discharge of this accumulation, by the voluntary power of the nerves, that muscular motion was produced. He accidentally discovered that if the crural nerve going into the muscles of a frog, and the crural muscles, be laid bare immediately after death, and a piece of zinc be placed in contact with the nerve, and a piece of silver or copper with the muscle, when these two pieces of metal are made to touch each other, violent convulsions are produced in the muscle, which cause the limb to move. He conceived that these convulsions were produced by the discharge of the nervous energy from the muscles, in consequence of the conducting power of the metals. Volta, who repeated these experiments, explained them in a different manner. According to him, the convulsions were produced by the passage of a current of common electricity through the limb of the frog, which was thrown into a state of convulsion merely in consequence of its irritability. This irritability vanishes after the death of the muscle. Accordingly, it is only while the principle of life remains that the convulsions can be produced. Every metallic conductor, according to him, possesses a certain electricity which is peculiar to it, either positive or negative, though the quantity is so small as to be imperceptible in the common state of the metal. But if a metal, naturally positive, be placed in contact, while insulated, with a metal naturally negative, the charge of electricity in both is increased by induction, and becomes perceptible when the two metals are separated and presented to a sufficiently delicate electrometer. Thus zinc is naturally positive, and copper and silver naturally negative. If we take two discs of copper and zinc, to the center of each of which a varnished glass handle is cemented, and after keeping them for a short time in contact, separate them by the handles, and apply each to a sufficiently delicate electrometer, we shall find that the zinc is positive and the silver or copper disc negative. When the silver and copper are placed in contact while lying on the nerve and muscles of the leg of a frog, the zinc becomes positive and the silver negative by induction. But as the animal substance is a conductor, this state cannot continue. The two electricities pass through the conducting muscles and nerve, and neutralize one another, and it is this current which occasions the convulsions. Such was Volta's simple explanation of the convulsions produced in galvanic experiments in the limb of a frog. Galvani was far from allowing the accuracy of it, and, in order to obviate the objection to his reasoning advanced by Volta from the necessity of employing two metals, he showed that the convulsions might, in certain cases, be produced by one metal. Volta showed that a very small quantity of one metal, either alloyed with, or merely in contact with another, were capable of inducing the two electricities. But in order to prove in the most unanswerable manner that the two electricities were induced when two different metals were placed in contact, he contrived the following piece of apparatus. He procured a number, say 50, of pieces of zinc, about the size of a crown piece, and as many pieces of copper, and thirdly, the same number of pieces of card of the same size. The cards were steeped in a solution of salt, so as to be moist. He lays upon the table a piece of zinc, places over it a piece of copper, and then a piece of moist card. Over the card is placed a second piece of zinc, then a piece of copper, then a piece of wet card. In this way all the pieces are piled upon each other in exactly the same order, namely zinc, copper, card, zinc, copper, card, zinc, copper, card, so that the lowest plate is zinc and the uppermost is copper, for the last wet card may be omitted. In this way there are 50 pairs of zinc and copper plates in contact, each separated by a piece of wet card, which is a conductor of electricity. If you now moisten a finger of each hand with water, and apply one wet finger to the lowest zinc plate, and the other to the highest copper plate, the moment the fingers come in contact with the plates, an electric shock is felt, the intensity of which increases with the number of pairs of plates in the pile. This is what is called the galvanic, or rather the voltaic pile. It was made known to the public in a paper by Volta, inserted in the Philosophical Transactions for 1800. This pile was gradually improved by substituting troughs, first of baked wood, and afterwards of porcelain, divided into as many cells as there were pairs of plates. The size of the plates was increased, they were made square, and instead of all being in contact, it was found sufficient if they were soldered together by means of metallic slips rising from one side of each square. The two plates thus soldered were slipped over the diaphragm separating the contiguous cells, so that the zinc plate was in one cell, and the copper in the other. Care was taken that the pairs were introduced all looking one way, so that a copper plate had always a zinc plate immediately opposite to it. The cells were filled with conducting liquid, brine, or a solution of salt and vinegar, or dilute muriatic, sulfuric, or nitric acid might be employed. But dilute nitric acid was found to answer best, and the energy of the battery is directly proportional to the strength of the nitric acid employed. Messrs. Nicholson and Carlisle were the first persons who repeated Volta's experiments with this apparatus, which speedily drew the attention of all Europe. They ascertained that the zinc end of the pile was positive, and the copper end negative. Happening to put a drop of water on the uppermost plate, and to put into it the extremity of a gold wire connected with the undermost plate, they observed an extrication of air bubbles from the wire. This led them to suspect that the water was decomposed. To determine the point, they collected a little of the gas extricated and found it hydrogen. They then attached a gold wire to the zinc end of the pile, and another gold wire to the copper end, and plunged the two wires into a glass of water, taking care not to allow them to touch each other. Gas was extricated from both wires. On collecting that from the wire attached to the zinc end, it was found to be oxygen gas, while that from the copper end was hydrogen gas. The volume of hydrogen gas extricated was just double that of the oxygen gas, and the two gases being mixed, and an electric spark passed through them, they burnt with an explosion and were completely converted into water. Thus it was demonstrated that water was decomposed by the action of the pile, and that the oxygen was extricated from the positive pile and the hydrogen from the negative. This held when the communicating wires were gold or platinum, but if they were of copper, silver, iron, lead, tin, or zinc, then only hydrogen gas was extricated from the negative wire. The positive wire extricated little or no gas, but it was rapidly oxidized. Thus, the connection between chemical decompositions and electrical currents was first established. It was soon after observed by Henry, Haldane, Davy, and other experimenters, that other chemical compounds were decomposed by the electrical currents as well as water. Ammonia, for example, nitric acid, and various salts were decomposed by it. In the year 1803, an important set of experiments was published by Berzelius and Hisinger. They decomposed 11 different salts, by exposing them to the action of a current of electricity. The salts were dissolved in water, and iron or silver wires from the 2 poles of the pile were plunged into the solution. In every one of these decompositions, the acid was deposited round the positive wire, and the base of the salt round the negative wire. When ammonia was decomposed by the action of galvanic electricity, the azotic gas separated from the positive wire, and the hydrogen gas from the negative. But it was Davy that first completely elucidated the chemical decompositions produced by galvanic electricity, who first explained the laws by which these decompositions were regulated, and who employed galvanism as an instrument for decomposing various compounds, which had hitherto resisted all the efforts of chemists to reduce them to their elements. These discoveries threw a blaze of light upon the obscurest parts of chemistry, and secured for the author of them an immortal reputation. Humphrey Davy, to whom these splendid discoveries were owing, was born at Penzance in Cornwall in the year 1778. He displayed from his very infancy a spirit of research, and a brilliancy of fancy, which augured, even at that early period, what he was one day to be. When very young, he was bound apprentice to an apothecary in his native town. Even at that time, his scientific acquirements were so great that they drew the attention of Mr. Davis Gilbert, the late distinguished president of the Royal Society. It was by his advice that he resolved to devote himself to chemistry, as the pursuit best calculated to procure him celebrity. About this time, Mr. Gregory Watt, youngest son of the celebrated improver of the steam engine, happening to be at Penzance, met with young Davy, and was delighted with the uncommon knowledge which he displayed, at the brilliancy of his fancy, and the great dexterity and ardour with which, under circumstances the most unfavourable, he was prosecuting his scientific investigations. These circumstances made an indelible impression on his mind, and led him to recommend Davy as the best person to superintend the Bristol institution for trying the medicinal effects of the gases. After the discovery of the different gases, and the investigation of their properties by Dr. Priestley, it occurred to various individuals, nearly about the same time, that the employment of certain gases, or at least of mixtures of certain gases, with common air in respiration instead of common air, might be powerful means of curing diseases. Dr. Beddoes, at that time professor of chemistry at Oxford, was one of the keenest supporters of these opinions. Mr. Watt of Birmingham and Mr. Wedgwood entertained similar sentiments. About the beginning of the present century, a sum of money was raised by subscription to put these opinions to the test of experiment, and as Dr. Beddoes had settled as a physician in Bristol, it was agreed upon that the experimental investigation should take place at Bristol. But Dr. Beddoes was not qualified to superintend an institution of the kind. It was necessary to procure a young man of zeal and genius, who would take such an interest in the investigation as would compensate for the badness of the apparatus and the defects of the arrangements. The greatest part of the money had been subscribed by Mr. Wedgwood and Mr. Watt. Their influence, of course, would be greatest in recommending a proper superintendent. Gregory Watt thought of Mr. Davy, whom he had lately been so highly pleased with, and recommended him with much zeal to superintend the undertaking. This recommendation being seconded by that of Mr. Davis Gilbert, who was so well acquainted with the scientific acquirements and genius of Davy, proved successful, and Davy accordingly got the appointment. At Bristol he was employed about a year in investigating the effects of the gases when employed in respiration. But he did not by any means confine himself to this, which was the primary object of the institution, but investigated the properties and determined the composition of nitric acid, ammonia, protoxide of azote, and deutoxide of azote. The fruit of his investigations was published in 1800, in a volume entitled Researches, Chemical and Philosophical, chiefly concerning nitrous oxide, or dephlogisticated nitrous air, and its respiration. This work gave him at once a high reputation as a chemist, and was really a wonderful performance when the circumstances under which it was produced are taken into consideration. He had discovered the intoxicating effects which protoxide of azote, nitrous oxide, produces when breathed, and had tried their effects upon a great number of individuals. This fortunate discovery perhaps contributed more to his celebrity and to his subsequent success than all the sterling merit of the rest of his researches. So great is the effect of display upon the greater part of mankind. End of section 61. Section 62 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 5, of Electro-chemistry, Part 2. A few years before, a philosophical institution had been established in London, under the auspices of Count Rumford, which had received the name of the Royal Institution. Lectures on chemistry and natural philosophy were delivered in this institution, a laboratory was provided, and a library established. The first professor appointed to this institution, Dr. Garnet, had been induced, in consequence of some disagreement between him and Count Rumford, to throw up his situation. Many candidates started for it, but Davy, in consequence of the celebrity which he had acquired by his researches, or perhaps by the intoxicating effects of protoxide of azote, which he had discovered, was, fortunately for the institution and for the reputation of England, preferred to them all. He was appointed Professor of Chemistry, and Dr. Thomas Young Professor of Natural Philosophy, in the year 1801. Davy, either from the more popular nature of his subject, or from his greater oratorical powers, became at once a popular lecturer, and always lectured to a crowded room, while Dr. Young, though both a profound and clear lecturer, could scarcely command an audience of a dozen. It was here that Davy laboured with unwearied industry during 11 years, and acquired by his discoveries the highest reputation of any chemist in Europe. In 1811 he was knighted, and soon after married Mrs. Apreece, a widow lady, daughter of Mr. Kerr, who had been secretary to Lord Rodney and had made a fortune in the West Indies. He was soon after created a baronet. About this time he resigned his situation as professor of chemistry in the Royal Institution, and went to the Continent. He remained for some years in France and Italy. In the year 1821, when Sir Joseph Banks died, a very considerable number of the fellows offered their votes to Dr. Wollaston, but he declined standing as a candidate for the president's chair. Sir Humphrey Davy, on the other hand, was anxious to obtain that honourable situation, and was, accordingly, elected president by a very great majority of votes on the 30th of November, 1821. This honourable situation he filled about 7 years, but his health declining, He was induced to resign in 1828 and to go to Italy. Here he continued till 1829, when, feeling himself getting worse, and wishing to draw his last breath in his own country, he began to turn his way homewards. But at Geneva he felt himself so ill that he was unable to proceed further. Here he took to his bed, and here he died on the 29th of May, 1829. It was his celebrated paper on some chemical agencies of electricity, inserted in the Philosophical Transactions for 1807, that laid the foundation of the high reputation which he so deservedly acquired. I consider this paper not merely as the best of all his own productions, but as the finest and completest specimen of inductive reasoning which appeared during the age in which he lived. It had been already observed that when two platinum wires from the two poles of a galvanic pile are plunged each into a vessel of water, and the two vessels united by means of wet asbestos, or any other conducting substance, an acid appeared round the positive wire, and an alkali round the negative wire. The alkali was said by some to be soda, by others to be ammonia. The acid was variously stated to be nitric acid, muriatic acid, or even chlorine. Davy demonstrated by decisive experiments that in all cases the acid and alkali are derived from the decomposition of some salt, contained either in the water or in the vessel containing the water. Most commonly, the salt decomposed is common salt, because it exists in water and in agate, basalt, and various other stony bodies, which he employed as vessels. When the same agate cup was used in successive experiments, the quantity of acid and alkali evolved diminished each time, and at last no appreciable quantity could be perceived. When glass vessels were used, soda was disengaged at the expense of the glass, which was sensibly corroded. When the water into which the wires were dipped was perfectly pure, and when the vessel containing it was free from every trace of saline matter, no acid or alkali made its appearance, and nothing was evolved except the constituents of water, namely oxygen and hydrogen, the oxygen appearing round the positive wire, and the hydrogen round the negative wire. When a salt was put into the vessel in which the positive wire dipped, the vessel into which the negative wire dipped being filled with pure water, and the two vessels being united by means of a slip of moistened asbestos, the acid of the salt made its appearance round the positive wire, and the alkali round the negative wire, before it could be detected in the intermediate space. But if an intermediate vessel, containing a substance for which the alkali has a strong affinity, be placed between these two vessels, the whole being united by means of slips of asbestos, then great part, or even the whole of the alkali, was stopped in this intermediate vessel. Thus, if the salt was nitrate of barytes, and sulphuric acid was placed in the intermediate vessel, much sulphate of barytes was deposited in the intermediate vessel, and very little or even no barytes made its appearance round the negative wire. Upon this subject a most minute, extensive, and satisfactory series of experiments was made by Davy, leaving no doubt whatever of the accuracy of the fact. The conclusions which he drew from these experiments are, that all substances which have a chemical affinity for each other are in different states of electricity, and that the degree of affinity is proportional to the intensity of these opposite states. When such a compound body is placed in contact with the poles of a galvanic battery, the positive pole attracts the constituent, which is negative, and repels the positive. The negative acts in the opposite way, attracting the positive constituent and repelling the negative. The more powerful the battery, the greater is the force of these attractions and repulsions. We may, therefore, by increasing the energy of a battery sufficiently, enable it to decompose any compound whatever, the negative constituent being attracted by the positive pole, and the positive constituent by the negative pole. Oxygen, chlorine, bromine, iodine, cyanogen, and acids are negative bodies, for they always appear round the positive pole of the battery, and are therefore attracted to it, while hydrogen, azote, carbon, selenium, metals, alkalis, earths, and oxide bases are deposited round the negative pole, and consequently are positive. According to this view of the subject, chemical affinity is merely a case of the attractions exerted by bodies in different states of electricity. Volta first broached the idea that every body possesses naturally a certain state of electricity. Davy went a step further, and concluded that the attractions which exist between the atoms of different bodies are merely the consequence of these different states of electricity. The proof of this opinion is founded on the fact that if we present to a compound sufficiently strong electrical poles, it will be separated into its constituents, and one of these constituents will invariably make its way to the positive, and the other to the negative pole. Now bodies in a state of electrical excitement always attract those that are in the opposite state. If electricity be considered as consisting of two distinct fluids, which attract each other with a force inversely as the square of the distance, while the particles of each fluid repel each other with a force varying according to the same law, then we must conclude that the atoms of each body are covered externally with a coating of some one electric fluid to a greater or smaller extent. Oxygen and the other supporters of combustion are covered with a coating of negative electricity, while hydrogen, carbon, and the metals are covered with a coating of positive electricity. What is the cause of the adherence of the electricity to these atoms? We cannot explain. It is not owing to an attraction similar to gravitation, for electricity never penetrates into the interior of bodies, but spreads itself only on the surface, and the quantity of it which can accumulate is not proportional to the quantity of matter, but to the extent of surface. But whatever be the cause, the adherence is strong, and seemingly cannot be overcome. If we were to suppose an atom of any body, of oxygen for example, to remain uncombined with any other body, but surrounded by electricity, it is obvious that the coating of negative electricity on its surface would be gradually neutralized by its attracting and combining with positive electricity. But let us suppose an atom of oxygen and an atom of hydrogen to be united together. It is obvious that the positive electricity of the one atom would powerfully attract the negative electricity of the other, and vice versa. And if these respective electricities cannot leave the atoms, the two atoms will remain firmly united, and the opposite electrical intensities will in some measure neutralize each other, and thus prevent them from being neutralized by electricity from any other quarter. But a current of the opposite electricities passing through such a compound might neutralize the electricity in each, and, thus putting an end to their attractions, occasion decomposition. Such is a very imperfect outline of the electrical theory of affinity first proposed by Davy to account for the decompositions produced by electricity. It has been universally adopted by chemists, and some progress has been made in explaining and accounting for the different phenomena. It would be improper, in a work of this kind, to enter further into the subject. Those who are interested in such discussions will find a good deal of information in the first volume of Berzelius's Treatise on Chemistry, in the introduction to the Traité de Chimie appliquée aux Arts by Dumas, or in the introduction to my System of Chemistry, at present in the press. Davy having thus got possession of an engine, by means of which the compounds, whose constituents adhered to each other might be separated, immediately applied it to the decomposition of potash and soda, bodies which were admitted to be compounds, though all attempts to analyze them had hitherto failed. His attempt was successful. When a platinum wire from the negative pole of a strong battery in full action was applied to a lump of potash slightly moistened, and lying on a platinum tray attached to the positive pole of the battery, small globules of a white metal soon appeared at its extremity. This white metal he speedily proved to be the basis of potash. He gave it the name of potassium, and very soon proved that potash is a compound of 5 parts by weight of this metal and 1 part of oxygen. Potash, then, is a metallic oxide. He proved soon after that soda is a compound of oxygen and another white metal, to which he gave the name of sodium. Lime is a compound of calcium and oxygen, magnesia of magnesium and oxygen, barytes of barium and oxygen, and strontian of strontium and oxygen. In short, the fixed alkalis and alkaline earths are metallic oxides. When lithia was afterwards discovered by Arfvedson, Davy succeeded in decomposing it also by the galvanic battery, and resolving it into oxygen and a white metal, to which the name of lithium was given. Davy did not succeed so well in decomposing alumina, glucina, yttria, and zirconia by the galvanic battery. They were not sufficiently good conductors of electricity, but nobody entertained any doubt that they also were metallic oxides. They have been all at length decomposed, and their bases obtained by the joint action of chlorine and potassium, and it has been demonstrated that they also are metallic oxides. Thus it has been ascertained, in consequence of Davy's original discovery of the powers of the galvanic battery, that all the bases formerly distinguished into the 4 classes of alkalis, alkaline earths, earths proper, and metallic oxides, belong in fact only to one class, and are all metallic oxides. Important as these discoveries are, and sufficient as they would have been to immortalize the author of them, they are not the only ones for which we are indebted to Sir Humphry Davy. His experiments on chlorine are not less interesting or less important in their consequences. I have already mentioned in a former chapter that Berthollet made a set of experiments on chlorine, from which he had drawn as a conclusion that it is a compound of oxygen and muriatic acid, in consequence of which it got the name of oxymuriatic acid. This opinion of Berthollet had been universally adopted by chemists, and admitted by them as a fundamental principle, till Gay-Lussac and Thénard endeavoured, unsuccessfully, to decompose this gas, or to resolve it into muriatic acid and chlorine. They showed in the clearest manner that such a resolution was impossible, and that no direct evidence could be adduced to prove that oxygen was one of its constituents. The conclusion to which they came was, that muriatic acid gas contained water as an essential constituent, and they succeeded by this hypothesis in accounting for all the different phenomena which they had observed. They even made an experiment to determine the quantity of water thus combined. They passed muriatic acid through hot litharge, protoxide of lead. Muriate of lead was formed, and abundance of water made its appearance and was collected. They did not attempt to determine the proportions. but we can now easily calculate the quantity of water which would be deposited when a given weight of muriatic acid gas is absorbed by a given weight of litharge. Suppose we have 14 parts of oxide of lead. To convert it into muriate of lead, 4 625,000 parts, by weight, of muriatic acid would be necessary, and during the formation of the muriate of lead, there would be deposited 1 125,000 parts of water, so that from this experiment it might be concluded that about 1/4 of the weight of muriatic acid gas is water. The very curious and important facts respecting chlorine and muriatic acid gas which they had ascertained were made known by Gay-Lussac and Thénard to the Institute on the 27th of February 1809, and an abstract of them was published in the second volume of the Mémoires d'Alchemy. There can be little doubt that it was in consequence of these curious and important experiments of the French chemists that Davy's attention was again turned to muriatic acid gas. He had already, in 1808, shown that when potassium is heated in muriatic acid gas, muriate of potash is formed, and a quantity of hydrogen gas evolved, amounting to more than 1/3 of the muriatic acid gas employed. And he had shown that in no case can muriatic acid be obtained from chlorine unless water or its elements be present. This last conclusion had been amply confirmed by the new investigations of Gay-Lussac and Thénard. In 1810 Davy again resumed the examination of the subject, and in July of that year read a paper to the Royal Society, to prove that chlorine is a simple substance, and that muriatic acid is a compound of chlorine and hydrogen. This was introducing an alteration in chemical theory of the same kind, and nearly as important, as was introduced by Lavoisier, with respect to the action of oxygen in the processes of combustion and calcination. It had been previously supposed that sulfur, phosphorus, charcoal, and metals were compounds, one of the constituents of which was phlogiston, and the other the acids or oxides which remained after the combustion or calcination had taken place. Lavoisier showed that the sulfur, phosphorus, charcoal, and metals were simple substances, and that the acids or calces formed were compounds of these simple bodies and oxygen. In like manner, Davy showed that chlorine, instead of being a compound of muriatic acid and oxygen, was, in fact, a simple substance, and muriatic acid a compound of chlorine and hydrogen. This new doctrine immediately overturned the Lavoisierian hypothesis respecting oxygen as the acidifying principle, and altered all the previously received notions respecting the muriates. What had been called muriates were, in fact, combinations of chlorine with the combustible or metal, and were analogous to oxides. Thus, when muriatic acid gas was made to act upon hot litharge, a double decomposition took place. The chlorine united to the lead, while the hydrogen of the muriatic acid united with the oxygen of the litharge, and formed water. Hence the reason of the appearance of water in this case, and hence it was obvious that what had been called muriate of lead was, in reality, a compound of chlorine and metallic lead. It ought, therefore, to be called, not muriate of lead, but chloride of lead. It was not likely that this new opinion of Davy should be adopted by chemists in general, without a struggle to support the old opinions. But the feebleness of the controversy which ensued affords a striking proof how much chemistry had advanced since the days of Lavoisier, and how free from prejudices chemists had become. One would have expected that the French chemists would have made the greatest resistance to the admission of these new opinions, because they had a direct tendency to diminish the reputation of two of their most eminent chemists, Lavoisier and Berthollet. But the fact was not so. The French chemists showed a degree of candour and liberality which redounds highly to their credit. Berthollet did not enter at all into the controversy. Gay-Lussac and Thénard, in their Recherches physico-chimiques, published in 1811, state their reasons for preferring the old hypothesis to the new, but with great modesty and fairness, and, within less than a year after, they both adopted the opinion of Davy, that chlorine is a simple substance, and muriatic acid a compound of hydrogen and chlorine. End of section 62. Section 63 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 5, of Electro-chemistry, Part 3. The only opponents to the new doctrine who appeared against it were Dr. John Murray of Edinburgh and Professor Berzelius of Stockholm. Dr. Murray was a man of excellent abilities and a very zealous cultivator of chemistry, but his health had been always very delicate, which had prevented him from dedicating so much of his time to experimenting as he otherwise would have been inclined to do. The only experimental investigations into which he entered was the analysis of some mineral waters. His powers of elocution were great. He was, in consequence, a popular and very useful lecturer. He published animadversions upon the new doctrine respecting chlorine in Nicholson's journal, and his observations were answered by Dr. John Davy. Dr. John Davy was the brother of Sir Humphrey, and had shown, by his paper on fluoric acid and on the chlorides, that he possessed the same dexterity and the same powers of inductive reasoning which had given so much celebrity to his brother. The controversy between him and Dr. Murray was carried on for some time with much spirit and ingenuity on both sides, and was productive of some advantage to the science of chemistry, by the discovery of phosgene gas or chlorocarbonic acid, which was made by Dr. Davy. It is needless to say to what side the victory fell. The whole chemical world has for several years unanimously adopted the theory of Davy, showing sufficiently the opinion entertained respecting the arguments advanced by either party. Berzelius supported the old opinion respecting the compound nature of chlorine, in a paper which he published in the Annals of Philosophy. No person thought it worth while to answer his arguments, though Sir Humphrey Davy made a few animadversions upon one or two of his experiments. The discovery of iodine, which took place almost immediately after, afforded so close an analogy with chlorine, and the nature of the compounds which it forms was so obvious and so well made out, that chemists were immediately satisfied, and they furnished so satisfactory an answer to all the objections of Berzelius, that I am not aware of any person, either in Great Britain or in France, who adopted his opinions. I have not the same means of knowing the impression which his paper made upon the chemists of Germany and Sweden. Berzelius continued for several years a very zealous opponent to the new doctrine, that chlorine is a simple substance. But he became, at last, satisfied of the futility of his own objections, and the inaccuracy of his reasoning. About the year 1820 he embraced the opinion of Davy, and is now one of its most zealous defenders. Dr. Murray has been dead for many years, and Berzelius has renounced his notion that muriatic acid is a compound of oxygen and an unknown combustible basis. We may say then, I believe with justice, that at present all the chemical world adopts the notion that chlorine is a simple substance, and muriatic acid a compound of chlorine and hydrogen. The recent discovery of bromine by Bellard has added another strong analogy in favour of Davy's theory, as has likewise the discovery by Gay-Lussac respecting prussic acid. At present, then, not reckoning sulphuretted and tellurietted hydrogen gas, we are acquainted with 4 acids which contain no oxygen, but are compounds of hydrogen with another negative body. These are muriatic acid, composed of chlorine and hydrogen; hydriodic acid, composed of iodine and hydrogen; hydrobromic acid, composed of bromine and hydrogen; prussic acid, composed of cyanogen and hydrogen. So that even if we were to leave out of view the chlorine acids, the sulphur acids, etc., no doubt can be entertained that many acids exist which contain no oxygen. Acids are compounds of electronegative bodies and a base, and in them all the electronegative electricity continues to predominate. Next to Sir Humphry Davy, the 2 chemists who have most advanced electrochemistry are Gay-Lussac and Thénard. About the year 1808, when the attention of men of science was particularly drawn towards the galvanic battery, in consequence of the splendid discoveries of Sir Humphry Davy, Bonaparte, who was at that time Emperor of France, consigned a sufficient sum of money to Count Cessac, governor of the Polytechnic School, to construct a powerful galvanic battery, and Gay-Lussac and Thénard were appointed to make the requisite experiments with this battery. It was impossible that a better choice could have been made. These gentlemen undertook a most elaborate and extensive set of experiments, the result of which was published in 1811, in 2 octavo volumes, under the title of Recherches physico-chimiques faites sur la pile, sur la préparation chimique et les propriétés du potassium et du sodium, sur la décomposition de l'acide boracique, sur les acides fluoriques, muriatiques et muriatique oxygène, sur l'action chimique de la lumière, sur les analyses végétales et animales, etc. It would be difficult to name any chemical book that contains a greater number of new facts, or which contains so great a collection of important information, or which has contributed more to the advancement of chemical science. The first part contains a very minute and interesting examination of the galvanic battery, and upon what circumstances its energy depends. They tried the effect of various liquid conductors, varied the strength of the acids and of the saline solutions. This division of their labours contains much valuable information for the practical electrochemist, though it would be inconsistent with the plan of this work to enter into details. The next division of the work relates to potassium. Davy had hitherto produced that metal only in minute quantities by the action of the galvanic battery upon potash. But Gay-Lussac and Thénard contrived a process by which it can be prepared on a large scale by chemical decomposition. Their method was to put into a bent gun barrel, well coated externally with clay, and passed through a furnace, a quantity of clean iron filings. To one extremity of this barrel was fitted a tube containing a quantity of caustic potash. This tube was either shut at one end by a stopper, or by a glass tube luted to it, and plunged under the surface of mercury. To the other extremity of the gun barrel was also luted a tube, which plunged into a vessel containing mercury. Heat was applied to the gun barrel till it was heated to whiteness. Then, by means of a choffer, the caustic potash was melted and made to trickle slowly into the white-hot iron filings. At this temperature, the potash undergoes decomposition, the iron uniting with its oxygen. The potassium is disengaged, and being volatile, is deposited at a distance from the hot part of the tube, where it is collected after the process is finished. Being thus in possession both of potassium and sodium in considerable quantities, they were enabled to examine its properties more in detail than Davy had done. But such was the care and industry with which Davy's experiments had been made that very little remained to be done. The specific gravity of the two metals was determined with more precision than it was possible for Davy to do. They determined the action of these metals on water, and measured the quantity of hydrogen gas given out with more precision than Davy could. They discovered also, by heating these metals in oxygen gas, that they were capable of uniting with an additional dose of oxygen, and of forming peroxides of potassium and sodium. These oxides have a yellow color, and give out the surplus oxygen, and are brought back to the state of potash and soda when they are plunged into water. They exposed a great variety of substances to the action of potassium, and brought to light a vast number of curious and important facts, tending to throw new light on the properties and characters of that curious metallic substance. By heating together anhydrous boracic acid and potassium in a copper tube, they succeeded in decomposing the acid, and in showing it to be a compound of oxygen and a black matter like charcoal, to which the name of boron has been given. They examined the properties of boron in detail, but did not succeed in determining with exactness the proportions of the constituents of boracic acid. The subsequent experiments of Davy, though not exact, come a good deal nearer the truth. Their experiments on fluoric acid are exceedingly valuable. They first obtained that acid in a state of purity, and ascertained its properties. Their attempts to decompose it, as well as those of Davy, ended in disappointment. But Ampere conceived the idea that this acid, like muriatic acid, is a compound of hydrogen with an unknown supporter of combustion, to which the name fluorine was given. This opinion was adopted by Davy, and his experiments, though they do not absolutely prove the truth of the opinion, give it at least considerable probability, and have disposed chemists in general to adopt it. The subsequent researches of Berzelius, while they have added a great deal to our former knowledge respecting fluoric acid and its compounds, have all tended to confirm and establish the doctrine that it is a hydracid, and similar in its nature to the other hydracids. But such is the tendency of fluorine to combine with every substance, that hitherto it has been impossible to obtain it in an insulated state. We want, therefore, still a decisive proof of the accuracy of the opinion. To the experiments of Gay-Lussac and Thénard on chlorine and muriatic acid, I have already alluded in a former part of this chapter. It was during their investigations connected with this subject that they discovered fluoboric acid gas, which certainly adds considerably to the probability of the theory of Ampere respecting the nature of fluoric acid. I pass over a vast number of other new and important facts and observations contained in this admirable work, which ought to be studied with minute attention by every person who aspires at becoming a chemist. Besides the numerous discoveries contained in the Recherches physico-chimiques, Gay-Lussac is the author of two of so much importance that it would be wrong to omit them. He showed that cyanogen is one of the constituents of prussic acid, succeeded in determining the composition of cyanogen, and showing it to be a compound of 2 atoms of carbon and 1 atom of azote. Prussic acid is a compound of 1 atom of hydrogen and 1 atom of cyanogen. Sulfocyanic acid, discovered by Mr. Porret, is a compound of 1 atom sulfuric and 1 atom cyanogen. Chlorocyanic acid, discovered by Berthollet, is a compound of 1 atom chlorine and 1 atom cyanogen, while cyanic acid, discovered by Wohler, is a compound of 1 atom oxygen and 1 atom cyanogen. I take no notice of the fulminic acid, because, although Gay-Lussac's experiments are exceedingly ingenious, and his reasoning very plausible, it is not quite convincing, especially as the results obtained by Mr. Edmund Davy, and detailed by him in his late interesting memoir on this subject, are somewhat different. The other discovery of Gay-Lussac is his demonstration of the peculiar nature of iodine, his account of iodic and hydriodic acids, and of many other compounds into which that curious substance enters as a constituent. Sir H. Davy was occupied with iodine at the same time with Gay-Lussac, and his sagacity and inventive powers were too great to allow him to work upon such a substance without discovering many new and interesting facts. To M. Thénard we are indebted for the discovery of the important fact that hydrogen is capable of combining with twice as much oxygen as exists in water, and determining the properties of this curious liquid, which has been called deutoxide of hydrogen. It possesses bleaching properties in perfection, and I think it likely that chlorine owes its bleaching powers to the formation of a little deutoxide of hydrogen in consequence of its action on water. The mantle of Davy seems in some measure to have descended on Mr. Faraday, who occupies his old place at the Royal Institution. He has shown equal industry, much sagacity, and great powers of invention. The most important discovery connected with electromagnetism, next to the great fact, for which we are indebted to Professor Ørsted of Copenhagen, is due to Mr. Faraday. I mean the rotation of the electric wires round the magnet. To him we owe the knowledge of the fact that several of the gases can be condensed into liquids by the united action of pressure and cold, which has removed the barrier that separated gaseous bodies from vapors, and shown us that all owe their elasticity to the same cause. To him also we owe the knowledge of the important fact that chlorine is capable of combining with carbon. This has considerably improved the history of chlorine, and served still further to throw new light on the analogy which exists between all the supporters of combustion. They are doubtless, all of them, capable of combining with every one of the other simple bodies, and of forming compounds with them, for they are all negative bodies, while the other simple substances without exception, when compared to them, possess positive properties. We must therefore view the history of chemistry as incomplete, till we have become acquainted with the compounds of every supporter with every simple base. End of section 63.
Section 64 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in August 2015. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 6 of the Atomic Theory, Part 1. I come now to the last improvement which chemistry has received, an improvement which has given a degree of accuracy to chemical experimenting almost approaching to mathematical precision, which has simplified prodigiously our views respecting chemical combinations, which has enabled manufacturers to introduce theoretical improvements into their processes, and to regulate with almost perfect precision the relative quantities of the various constituents necessary to produce the intended effects. The consequence of this is, that nothing is wasted, nothing is thrown away. Chemical products have become not only better in quality, but more abundant and much cheaper. I allude to the atomic theory, still only in its infancy, but already productive of the most important benefits. It is destined one day to produce still more wonderful effects, and to render chemistry not only the most delightful, but the most useful and indispensable of all the sciences. Like all other great improvements in science, the atomic theory developed itself by degrees, and several of the older chemists ascertained facts which might, had they been aware of their importance, have led them to conclusions similar to those of the moderns. The very attempt to analyze the salts was an acknowledgment that bodies united with each other in definite proportions, and these definite proportions, had they been followed out, would have led ultimately to the doctrine of atoms. For how could it be that 6 parts of potash were always saturated by 5 parts of sulphuric acid and 6.75 parts of nitric acid? How came it that 5 of sulphuric acid always went as far in saturating potash as 6.75 of nitric acid? It was known that in chemical combinations it was the ultimate particles of matter that combined. The simple explanation, therefore, would have been that the weight of an ultimate particle of sulphuric acid was only 5, while that of an ultimate particle of nitric acid was 6.75. Had such an inference been drawn, it would have led directly to the atomic theory. The atomic theory in chemistry has many points of resemblance to the fluxionary calculus in mathematics. Both give us the ratios of quantities. Both reduce investigations that would be otherwise extremely difficult, or almost impossible, to the utmost simplicity. And what is still more curious, both have been subjected to the same kind of ridicule by those who have not put themselves to the trouble of studying them with such attention as to understand them completely. The minute philosopher of Berkeley, mutatis mutandis, might be applied to the atomic theory with as much justice as to the fluxionary calculus, and I have heard more than one individual attempt to throw ridicule upon the atomic theory by nearly the same kind of arguments. The first chemists, then, who attempted to analyze the salts may be considered as contributing towards laying the foundation of the atomic theory, though they were not themselves aware of the importance of the structure, which might have been raised upon their experiments, had they been made with the requisite precision. Bergman was the first chemist who attempted regular analysis of salts. It was he that first tried to establish regular formulas for the analysis of mineral waters, stones, and ores, by the means of solution and precipitation. Hence a knowledge of the constituents of the salts was necessary, before his formulas could be applied to practice. It was to supply this requisite information that he set about analyzing the salts, and his results were long considered by chemists as exact, and employed by them to determine the results of their analysis. We now know that these analytical results of Bergman are far from accurate, that they have accordingly been laid aside as useless, but this knowledge has been derived from the progress of the atomic theory. The first accurate set of experiments to analyze the salts was made by Wenzel and published by him in 1777, in a small volume entitled Lehre von der Verwandtschaft der Körper, or Theory of the Affinities of Bodies. These analyses of Wenzel are infinitely more accurate than those of Bergman, and indeed in many cases are equally precise with the best which we have even at the present day. Yet the book fell almost dead born from the press, Wenzel's results never obtained the confidence of chemists, nor is his name ever quoted as an authority. Wenzel was struck with a phenomenon which had indeed been noticed by preceding chemists, but they had not drawn the advantages from it which it was capable of affording. There are several saline solutions which, when mixed with each other, completely decompose each other, so that two new salts are produced. Thus, if we mix together solutions of nitrate of lead and sulphate of soda in the requisite proportions, the sulphuric acid of the latter salt will combine with the oxide of lead of the former, and will form with it sulphate of lead, which will precipitate to the bottom in the state of an insoluble powder, while the nitric acid formerly united to the oxide of lead will combine with the soda formerly in union with the sulphuric acid, and form nitrate of soda, which being soluble will remain in solution in the liquid. Thus, instead of the two old salts, sulphate of soda, nitrate of lead, we obtain the two new salts, sulphate of lead, nitrate of soda. If we mix the two salts in the requisite proportions, the decomposition will be complete, but if there be an excess of one of the salts, that excess will still remain in solution without affecting the result. If we suppose the two salts anhydrous, then the proportions necessary for complete decomposition are sulphate of soda 9, nitrate of lead 20.75, total 29.75, and the quantities of the new salts formed will be sulphate of lead 19, nitrate of soda 10.75, total 29.75. We see that the absolute weights of the two sets of salts are the same. All that has happened is that both the acids and both the bases have exchanged situations. Now if, instead of mixing these two salts together in the preceding proportions, we employ sulphate of soda 9, nitrate of lead 25.75, that is to say, if we employ 5 parts of nitrate of lead more than is sufficient for the purpose, we shall have exactly the same decompositions as before, but the 5 of excess of nitrate of lead will remain in solution mixed with the nitrate of soda. There will be precipitated as before sulphate of lead 19, and there will remain in solution a mixture of nitrate of soda 10.75, nitrate of lead 5. The phenomena are precisely the same as before. The additional 5 of nitrate of lead have occasioned no alteration. The decomposition has gone on just as if they had not been present. Now, the phenomena which drew the particular attention of Wenzel is, that if the salts were neutral before being mixed, the neutrality was not affected by the decomposition which took place on their mixture. Footnote. This observation is not without exception. It does not hold when one of the salts is a phosphate or an arseniate, and this is the cause of the difficulty attending the analysis of these genera of salts. End footnote. A salt is said to be neutral when it neither possesses the characters of an acid or an alkali. Acids redden vegetable blues, while alkalis render them green. A neutral salt produces no effect whatever upon vegetable blues. This observation of Wenzel is very important. It is obvious that the salts, after their decomposition, could not have remained neutral unless the elements of the two salts had been such that the bases in each just saturated the acids in either of the salts. The constituents of the two salts are as follows. 9 sulphate of soda are 5 sulphuric acid, 4 soda. 20.75 nitrate of lead are 6.75 nitric acid, 14 oxide of lead. Now it is clear that, unless 5 sulphuric acid were just saturated by 4 soda and by 14 oxide of lead, and 6.75 of nitric acid by the same 4 soda and 14 oxide of lead, the salts, after their decomposition, could not have preserved their neutrality. Had 4 soda required only 5.75 of nitric acid, or had 14 oxide of lead required only 4 sulphuric acid to saturate them, the liquid after decomposition would have contained an excess of acid. As no such excess exists, it is clear that in saturating an acid, 4 soda goes exactly as far as 14 oxide of lead, and that in saturating a base, 5 sulphuric acid goes just as far as 6.75 nitric acid. Nothing can exhibit in a more striking point of view the almost despotic power of fashion and authority over the minds even of men of science, and the small number of them that venture to think for themselves, than the fact that this most important and luminous explanation of Wenzel, confirmed by much more accurate experience than any which chemistry has yet seen, is scarcely noticed by any of his contemporaries, and seems not to have attracted the smallest attention. In science it is as unfortunate for a man to get before the age in which he lives as to continue behind it. The admirable explanation of combustion by Hooke, and the important experiments on combustion and respiration by Mayow, were lost upon their contemporaries, and procured them little or no reputation whatever; while the same theory and the same experiments, advanced by Lavoisier and Priestley a century later, when the minds of men of science were prepared to receive them, raised them to the very first rank among philosophers, and produced a revolution in chemistry. So much concern has fortune, not merely in the success of kings and conquerors, but in the reputation acquired by men of science. In the year 1792 another laborer, in the same department of chemistry, appeared. This was Jeremiah Benjamin Richter, a Prussian chemist, of whose history I know nothing more than that his publications were printed and published in Breslau, from which I infer that he was a native of, or at least resided in, Silesia. He calls himself Assessor of the Royal Prussian Mines and Smelting Houses, and Arcanist of the Commission of Berlin Porcelain Manufacture. He died in the prime of life, on the 4th of May, 1807. In the year 1792 he published a work entitled Anfangsgründe der Stochiometrie oder Messkunst chemischer Elemente, Elements of Stoichiometry, or the Mathematics of the Chemical Elements. A second and third volume of this work appeared in 1793, and a fourth volume in 1794. The object of this book was a rigid analysis of the different salts, founded on the fact just mentioned, that when two salts decompose each other, the salts newly formed are neutral as well as those which have been decomposed. He took up the subject nearly in the same way as Wenzel had done, but carried the subject much further, and endeavored to determine the capacity of saturation of each acid and base, and to attach numbers to each, indicating the weights which mutually saturate each other. He gave the whole subject a mathematical dress, and endeavored to show that the same relation existed between the numbers representing the capacity of saturation of these bodies as does between certain classes of figure-8 numbers. When we strip the subject of the mystical form under which he presented it, the labors of Richter may be exhibited under the two following tables, which represent the capacity of saturation of the acids and bases according to his experiments. Table 1. Acids. Fluoric acid 427. Carbonic acid 577. Sebacic acid 706. Muriatic acid 712. Oxalic acid 755. Phosphoric acid 979. Formic acid 988. Sulphuric acid 1000. Succinic acid 1209. Nitric acid 1405. Acetic acid 1480. Citric acid 1683. Tartaric acid 1694. Table 2. Bases. Alumina 525, magnesia 615, ammonia 672, lime 793, soda 859, strontium 1329, potash 1605, barytes 2222. To understand this table, it is only necessary to observe that if we take the quantity of any of the acids placed after it in the table, that quantity will be exactly saturated by the weight of each base put after it in the second column. Thus 1000 of sulphuric acid will be just saturated by 525 alumina, 615 magnesia, 672 ammonia, 733 lime, and so on. On the other hand, the quantity of any base placed after its name in the second column will be just saturated by the weight of each acid placed after its name in the first column. Thus 793 parts of lime will be just saturated by 427 of fluoric acid, 577 of carbonic acid, 706 of sebacic acid, and so on. This work of Richter was followed by a periodical work entitled Über die neuen Gegenstände der Chemie, on the new objects of chemistry. This work was begun in the year 1792 and continued in 12 different numbers, or volumes, to the time of his death in 1807. Footnote: I have only seen 11 parts of this work, the last of which appeared in 1802, but I believe that the 12th part was published afterwards. End footnote. Richter's labors in this important field produced as little attention as those of Wenzel. Gehlen wrote a short panegyric upon him at his death, praising his views and pointing out their importance, but I am not aware of any individual, either in Germany or elsewhere, who adopted Richter's opinions during his lifetime, or even seemed aware of their importance, unless we are to accept Berthollet, who mentions them with approbation in his Chemical Statics. This inattention was partly owing to the great want of accuracy which it is impossible not to be sensible of in Richter's experiments. He operated upon too large quantities of matter, which indeed was the common defect of the times, and was first checked by Dr. Wollaston. The dispute between the phlogistians and the antiphlogistians, which was not fully settled in Richter's time, drew the attention of chemists to another branch of the subject. Richter in some measure went before the age in which he lived, and had his labors not been recalled to our recollection by the introduction of atomic theory, he would probably have been forgotten, like Hooke and Mayow, and only brought again under review after the new discoveries in the science had put it in the power of chemists in general to appreciate the value of his labors. It is to Mr. Dalton that we are indebted for the happy and simple idea from which the atomic theory originated. End of section 64. Section 65 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avahi in September 2015. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 6 of the Atomic Theory, Part 2. John Dalton, to whose lot it has fallen to produce such an alteration and improvement in chemistry, was born in Westmoreland, and belongs to that small and virtuous sect known in this country by the name of Quakers. When very young he lived with Mr. Gow of Kendal, a blind philosopher, to whom he read and whom he assisted in his philosophical investigation. It was here, probably, that he acquired a considerable part of his education, particularly his taste for mathematics. For Mr. Gow was remarkably fond of mathematical investigations, and has published several mathematical papers that do him credit. From Kendal Mr. Dalton went to Manchester about the beginning of the present century, and commenced teaching elementary mathematics to such young men as felt inclined to acquire some knowledge of that important subject. In this way, together with a few courses of lectures on chemistry, which he has occasionally given at the Royal Institution in London, at the Institution in Birmingham, in Manchester, and once in Edinburgh and in Glasgow, he has contrived to support himself for more than 30 years, if not in affluence, at least in perfect independence. And as his desires have always been of the most moderate kind, his income has always been equal to his wants. In a country like this, where so much wealth abounds, and where so handsome a yearly income was subscribed to enable Dr. Priestley to prosecute his investigations undisturbed and undistracted by the necessity of providing for the daily wants of his family, there is little doubt that Mr. Dalton, had he so chosen it, might, in point of pecuniary circumstances, have exhibited a much more brilliant figure. But he has displayed a much nobler mind by the career which he has chosen, equally regardless of riches as the most celebrated sages of antiquity, and as much respected and beloved by his friends, even in the rich commercial town of Manchester, as if he were one of the greatest and most influential men in the country. Towards the end of the last century, a literary and scientific society had been established in Manchester, of which Mr. Thomas Henry, the translator of Lavoisier's essays, and who distinguished himself so much in promoting the introduction of the new mode of bleaching into Lancashire, was long president. Mr. Dalton, who had already distinguished himself by his meteorological observations, and particularly by his account of the aurora borealis, soon became a member of the society, and in the 5th volume of their Memoirs, Part II, published in 1802, 6 papers of his were inserted, which lay the foundation of his future celebrity. These papers were chiefly connected with meteorological subjects, but by far the most important of them all was the one entitled Experimental Essays on the Constitution of Mixed Gases, on the force of steam or vapour from water and other liquids in different temperatures, both in a Torricellian vacuum and in air, on evaporation, and on the expansion of gases by heat. From a careful examination of all the circumstances, he considered himself as entitled to infer, that when two elastic fluids or gases, A and B, are mixed together, there is no mutual repulsion among their particles, that is, the particles of A do not repel those of B, as they do one another. Consequently, the pressure or whole weight upon any one particle arises solely from those of its own kind. This doctrine is of so startling a nature and so contrary to the opinions previously received, that chemists have not been much disposed to admit it. But at the same time it must be confessed that no one has hitherto been able completely to refute it. The consequences of admitting it are obvious. We should be able to account for a fact which has been long known, though no very satisfactory reason for it had been assigned, namely, that if two gases be placed in two separate vessels, communicating by a narrow orifice, and left at perfect rest in a place where the temperature never varies, if we examine them after a certain interval of time, we shall find both equally diffused through both vessels. If we fill a glass phial with hydrogen gas and another phial with common air or carbonic acid gas, and unite the two phials by a narrow glass tube 2 feet long, filled with common air, and place the phial containing the hydrogen gas uppermost, and the other perpendicularly below it, the hydrogen, though lightest, will not remain in the upper phial, nor the carbonic acid, though heaviest, in the undermost phial, but we shall find both gases equally diffused through both phials. But the second of these essays is by far the most important. In it he establishes, by the most unexceptionable evidence, that water, when it evaporates, is always converted into an elastic fluid, similar in its properties to air; but that the distance between the particles is greater the lower the temperature is at which the water evaporates. The elasticity of this vapor increases as the temperature increases. At 32 degrees it is capable of balancing a column of mercury about half an inch in height, and at 212 degrees it balances a column 30 inches high, or it is then equal to the pressure of the atmosphere. He determined the elasticity of vapor at all temperatures from 32 degrees to 212 degrees, pointed out the method of determining the quantity of vapor that at any time exists in the atmosphere, the effect which it has upon the volume of air, and the mode of determining its quantity. Finally, he determined, experimentally, the rate of evaporation from the surface of water at all temperatures from 32 degrees to 212 degrees. These investigations have been of infinite use to chemists in all their investigations respecting the specific gravity of gases, and have enabled them to resolve various interesting problems, both respecting specific gravity, evaporation, rain and respiration, which, had it not been for the principles laid down in this essay, would have eluded their grasp. In the last essay contained in this paper he has shown that all elastic fluids expend the same quantity by the same addition of heat, and this expansion is very nearly 1/480th part for every degree of Fahrenheit's thermometer. In this last branch of the subject Mr. Dalton was followed by Gay-Lussac, who, about half a year after the appearance of his essays, published a paper in the Annales de Chimie, showing that the expansion of all elastic fluids, when equally heated, is the same. Mr. Dalton concluded that the expansion of all elastic fluids by heat is equable. And this opinion has been since confirmed by the important experiments of Dulong and Petit, which have thrown much additional light on the subject. In the year 1804, on the 26th of August, I spent a day or two at Manchester, and was much with Mr. Dalton. At that time he explained to me his notions respecting the composition of bodies. I wrote down at the time the opinions which he offered, and the following account is taken literally from my journal of that date. The ultimate particles of all simple bodies are atoms incapable of further division. These atoms, at least viewed along with their atmospheres of heat, are all spheres, and are each of them possessed of particular weights, which may be denoted by numbers. For the greater clearness he represented the atoms of the simple bodies by symbols. The following are his symbols for 4 simple bodies, together with the numbers attached to them by him in 1804. Circle, oxygen, relative weight 6.5. Dotted circle, hydrogen, relative weight 1. Black disk, carbon, relative weight 5. Circle with line, azote, relative weight 5. The following symbols represent the way in which he thought these atoms were combined to form certain binary compounds, with the weight of an integrant particle of each compound. Circle, dotted circle, water, weight 7.5. Circle, circle with line, nitrous gas, weight 11.5. Black disk, dotted circle, olefiant gas, weight 6. Circle with line, dotted circle, ammonia, weight 6. Circle, black disk, carbonic oxide, weight 11.5. The following were the symbols by which he represented the composition of certain tertiary compounds. Circle, black disk, circle, carbonic acid, weight 18. Circle, circle with line, circle, nitrous oxide, weight 16.5. Black disk, dotted circle, black disk, ether, weight 11. Dotted circle, black disk, dotted circle, carburetted hydrogen, weight 7. Circle, circle with line, circle, nitric acid, weight 18. A quaternary compound, in 2 rows. First row, circle, circle with line, circle. Second row, empty, circle, empty. Oxynitric acid, weight 24.5. A quinquennary compound, in 4 columns. First column, circle with line. Second column, on top of each other, circle, circle. Third column, circle with line. Fourth column, circle. Nitrous acid, weight 29.5. A sexternary compound, in a 2x3 matrix. First row, black disk, circle, black disk. Second row, dotted circle, black disk, dotted circle. Alcohol, weight 23.5. These symbols are sufficient to give the reader an idea of the notions entertained by Dalton respecting the nature of compounds. Water is a compound of 1 atom oxygen and 1 atom hydrogen, as it is obvious from the symbol circle, dotted circle. Its weight 7.5 is that of an atom of oxygen and an atom of hydrogen united together. In the same way, carbonic oxide is a compound of 1 atom oxygen and 1 atom carbon. Its symbol is circle, black disk, and its weight 11.5 is equal to an atom of oxygen and an atom of carbon added together. Carbonic acid is a tertiary compound, or it consists of 3 atoms united together, namely 2 atoms of oxygen and 1 atom of carbon. Its symbol is circle, black disk, circle, and its weight 18. A bare inspection of the symbols and weights will make Mr. Dalton's notions respecting the constitution of every body in the table evident to every reader. It was this happy idea of representing the atoms and constitution of bodies by symbols that gave Mr. Dalton's opinions so much clearness. I was delighted with the new light which immediately struck my mind, and saw at a glance the immense importance of such a theory, when fully developed. Mr. Dalton informed me that the atomic theory first occurred to him during his investigations of olefiant gas and carburetted hydrogen gases, at that time imperfectly understood, and the constitution of which was first fully developed by Mr. Dalton himself. It was obvious from the experiments which he made upon them that the constituents of both were carbon and hydrogen, and nothing else. He found further that if we reckon the carbon in each the same, then carburetted hydrogen gas contains exactly twice as much hydrogen as olefiant gas does. This determined him to state the ratios of these constituents in numbers, and to consider the olefiant gas as a compound of 1 atom of carbon and 1 atom of hydrogen, and carburetted hydrogen of 1 atom of carbon and 2 atoms of hydrogen. The idea thus conceived was applied to carbonic oxide, water, ammonia, etc., and numbers representing the atomic weights of oxygen, azote, etc., deduced from the best analytical experiments which chemistry then possessed. Let not the reader suppose that this was an easy task. Chemistry at that time did not possess a single analysis which could be considered as even approaching to accuracy. A vast number of facts had been ascertained, and a fine foundation laid for future investigation, but nothing, as far as weight and measure were concerned, deserving the least confidence, existed. We need not be surprised, then, that Mr. Dalton's first numbers were not exact. It required infinite sagacity, and not a little labour, to come so near the truth as he did. How could accurate analyses of gases be made, when there was not a single gas whose specific gravity was known, with even an approach to accuracy? The preceding investigations of Dalton himself paved the way for accuracy in this indispensable department, but still accurate results had not yet been obtained. In the third edition of my System of Chemistry, published in 1807, I introduced a short sketch of Mr. Dalton's theory, and thus made it known to the chemical world. The same year a paper of mine on oxalic acid was published in the Philosophical Transactions, in which I showed that oxalic acid unites in 2 proportions with strontian, forming an oxalate and binoxalate, and that, supposing the strontian in both salts to be the same, the oxalic acid in the latter is exactly twice as much as in the former. About the same time Dr. Wollaston showed that bicarbonate of potash contains just twice the quantity of carbonic acid that exists in carbonate of potash, and that there are 3 oxalates of potash, viz., oxalate, binoxalate, and quadroxalate, the weight of acids in each of which are as the numbers 1, 2, 4. These facts gradually drew the attention of chemists to Mr. Dalton's views. There were, however, some of our most eminent chemists who were very hostile to the atomic theory. The most conspicuous of these was Sir Humphry Davy. In the autumn of 1807 I had a long conversation with him at the Royal Institution, but could not convince him that there was any truth in the hypothesis. A few days after I dined with him at the Royal Society Club, at the Crown and Anchor, in the Strand. Dr. Wollaston was present at the dinner. After dinner every member of the club left the tavern, except Dr. Wollaston, Mr. Davy, and myself, who stayed behind and had tea. We sat about an hour and a half together, and our whole conversation was about the atomic theory. Dr. Wollaston was a convert as well as myself, and we tried to convince Davy of the inaccuracy of his opinions. But, so far from being convinced, he went away, if possible, more prejudiced against it than ever. Soon after, Davy met Mr. Davis Gilbert, the late distinguished President of the Royal Society, and he amused him with a caricature description of the atomic theory, which he exhibited in so ridiculous a light that Mr. Gilbert was astonished how any man of sense or science could be taken in with such a tissue of absurdities. Mr. Gilbert called on Dr. Wollaston, probably to discover what could have induced a man of Dr. Wollaston's sagacity and caution to adopt such opinions, and was not sparing in laying the absurdities of the theory, such as they had been represented to him by Davy, in the broadest point of view. Dr. Wollaston begged Mr. Gilbert to sit down, and listen to a few facts which he would state to him. He then went over all the principal facts at that time known respecting the salts, mentioned the alkaline carbonates and bicarbonates, the oxalate, binoxalate, and quadroxalate of potash, carbonic oxide and carbonic acid, olefiant gas and carburetted hydrogen, and doubtless many other similar compounds, in which the proportion of one of the constituents increases in a regular ratio. Mr. Gilbert went away a convert to the truth of the atomic theory, and he had the merit of convincing Davy that his former opinions of the subject were wrong. What arguments he employed I do not know, but they must have been convincing ones, for Davy ever after became a strenuous supporter of the atomic theory. The only alteration which he made was to substitute proportion for Dalton's word atom. Dr. Wollaston substituted for it the term equivalent. The object of these substitutions was to avoid all theoretical enunciations. But, in fact, these terms, proportion, equivalent, are neither of them so convenient as the term atom, and unless we adopt the hypothesis with which Dalton set out, namely that the ultimate particles of bodies are atoms incapable of further division, and that chemical combination consists in the union of these atoms with each other, we lose all the new light which the atomic theory throws upon chemistry, and bring our notions back to the obscurity of the days of Bergman and of Berthollet. In the year 1808 Mr. Dalton published the first volume of his New System of Chemical Philosophy. This volume consists chiefly of 2 chapters. The first, on heat, occupies 140 pages. In it he treats of all the effects of heat, and shows the same sagacity and originality which characterize all his writings. Even when his opinions on a subject are not correct, his reasoning is so ingenious and original, and the new facts which he contrives to bring forward so important, that we are always pleased and always instructed. The second chapter, on the Constitution of Bodies, occupies 70 pages. The chief object of it is to combat the peculiar notions respecting elastic fluids which had been advanced by Berthollet and supported by Dr. Murray of Edinburgh. In the third chapter, on chemical synthesis, which occupies only a few pages, he gives us the outlines of the atomic theory, such as he had conceived it. In a plate at the end of the volume he exhibits the symbols and atomic weights of 37 bodies, 20 of which were then considered as simple, and the other 17 as compound. The following table shows the atomic weight of the simple bodies, as he at that time had determined them from the best analytical experience that had been made. Hydrogen, weight of atom, 1. Azote, weight of atom, 5. Carbon, weight of atom, 5. Oxygen, weight of atom, 7. Phosphorus, weight of atom, 9. Sulfur, weight of atom, 13. Magnesia, weight of atom, 20. Lime, weight of atom, 23. Soda, weight of atom, 28. Potash, weight of atom, 42. Strontian, weight of atom, 46. Barytes, weight of atom, 68. Iron, weight of atom, 38. Zinc, weight of atom, 56. Copper, weight of atom, 56. Lead, weight of atom, 95. Silver, weight of atom, 100. Platinum, weight of atom, 100. Gold, weight of atom, 140. Mercury, weight of atom, 167. He had made choice of hydrogen for unity, because it is the lightest of all bodies. He was of opinion that the atomic weights of all other bodies are multiples of hydrogen, and accordingly they are all expressed in whole numbers. He had raised the atomic weight of oxygen from 6.5 to 7, from a more careful examination of the experiments on the component parts of water. Davy, from a more accurate set of experiments, soon after raised the number for oxygen to 7.5, and Dr. Prout, from a still more careful investigation of the relative specific gravities of oxygen and hydrogen, showed that if the atom of hydrogen be 1, that of oxygen must be 8. Everything conspires to prove that this is the true ratio between the atomic weights of oxygen and hydrogen. In 1810 appeared the second volume of Mr. Dalton's New System of Chemical Philosophy. In it he examines the elementary principles or simple bodies, namely oxygen, hydrogen, azote, carbon, sulfur, phosphorus, and the metals, and the compounds consisting of 2 elements, namely the compounds of oxygen with hydrogen, azote, carbon, sulfur, phosphorus, of hydrogen with azote, carbon, sulfur, phosphorus. Finally, he treats of the fixed alkalis and earths. All these combinations are treated of with infinite sagacity, and he endeavors to determine the atomic weights of the different elementary substances. Nothing can exceed the ingenuity of his reasoning. But unfortunately at that time very few accurate chemical analyses existed, and in chemistry no reasoning, however ingenious, can compensate for this indispensable datum. Accordingly, his table of atomic weights at the end of this second volume, though much more complete than that at the end of the first volume, is still exceedingly defective. Indeed, no one number can be considered as perfectly correct. The third volume of the new system of chemical philosophy was only published in 1827, but the greatest part of it had been printed nearly 10 years before. It treats of the metallic oxides, the sulphurets, phosphorates, carburettes, and alloys. Doubtless many of the facts contained in it were new when the sheets were put to the press, but during the interval between the printing and publication almost the whole of them had not merely been anticipated, but the subject carried much further. By far the most important part of the volume is the appendix, consisting of about 90 pages, in which he discusses, with his usual sagacity, various important points connected with heat and vapor. In page 352 he gives a new table of the atomic weights of bodies, much more copious than those contained in the two preceding volumes, and into which he has introduced the corrections necessary from the numerous correct analyses which had been made in the interval. He still adheres to the ratio 1:7 as the correct difference between the weights of the atoms of hydrogen and oxygen. This shows very clearly that he has not attended to the new facts which have been brought forward on the subject. No person who has attended to the experiments made on the specific gravity of these two gases during the last 12 years could admit that these specific gravities are to each other as 1:14. If 1:16 be not the exact ratio, it will surely be admitted on all hands that it is infinitely near it. Mr. Dalton represented the weight of an atom of hydrogen by 1 because it is the lightest of bodies. In this he has been followed by the chemists of the Royal Institution, by Mr. Phillips, Dr. Henry, and Dr. Turner, and perhaps some others whose names I do not at present recollect. Dr. Wollaston, in his paper on chemical equivalents, represented the atomic weight of oxygen by 1, because it enters into a greater number of combinations than any other substance, and this plan has been adopted by Berzelius, by myself, and by the greater number, if not the whole, of the chemists on the continent. Perhaps the advantage which Dr. Wollaston assigned for making the atom of oxygen unity will ultimately disappear, for there is no reason for believing that the other supporters of combustion are not capable of entering into as many compounds as oxygen. But, from the constitution of the atmosphere, it is obvious that the compounds into which oxygen enters will always be of more importance to us than any others, and in this point of view it may be attended with considerable convenience to have oxygen represented by 1. In the present state of the atomic theory there is another reason for making the atom of oxygen unity, which I think of considerable importance. Chemists are not yet agreed about the atom of hydrogen. Some consider water a compound of 1 atom of oxygen and 2 atoms of hydrogen, others of 1 atom of oxygen and 1 atom of hydrogen. According to the first view, the atom of hydrogen is only 1/16 of the weight of an atom of oxygen; according to the second, it is 1/8. If, therefore, we were to represent the atom of hydrogen by 1, the consequence would be that 2 tables of atomic weights would be requisite, all the atoms in one being double the weight of the atoms in the other, whereas, if we make the atom of oxygen unity, it will be the atom of hydrogen only that will differ in the 2 tables. In the one table it will be 0.125. In the other it will be 0.0625, or, reckoning with Berzelius, the atom of oxygen equals 100, we have that of hydrogen equals 12.5 or 6.25, according as we view water to be a compound of one atom of oxygen with one or two atoms of hydrogen. End of section 65. Section 66 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in August 2015. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 6, of the Atomic Theory, Part 3. In the year 1809, Gay-Lussac published in the second volume of the Mémoires d'Arcueil a paper on the union of the gaseous substances with each other. In this paper he shows that the proportions in which the gases unite with each other are of the simplest kind. One volume of one gas either combining with one volume of another, or with two volumes, or with half a volume. The atomic theory of Dalton had been opposed with considerable keenness by Berthollet in his introduction to the French translation of my System of Chemistry. Nor was this opposition to be wondered at, because its admission would of course overturn all the opinions which Berthollet had labored to establish in his Chemical Statics. The object of Gay-Lussac's paper was to confirm and establish the new atomic theory by exhibiting it in a new point of view. Nothing can be more ingenious than his mode of treating the subject, or more complete than the proofs which he brings forward in support of it. It had been already established that water is formed by the union of one volume of oxygen and two volumes of hydrogen gas. Gay-Lussac found by experiment that one volume of muriatic acid gas is just saturated by one volume of ammoniacal gas. The product is sal ammoniac. Fluoroboric acid gas unites in two proportions with ammoniacal gas. The first compound consists of one volume of fluoroboric gas and one volume of ammoniacal, the second of one volume of the acid gas and two volumes of the alkaline. The first forms a neutral salt, the second an alkaline salt. He showed likewise that carbonic acid and ammoniacal gas could combine also in two proportions, namely, one volume of the acid gas with one or two volumes of the alkaline gas. M. Amédée Berthollet had proved that ammonia is a compound of one volume of azotic and three volumes of hydrogen gas. Gay-Lussac himself had shown that sulphuric acid is composed of one volume sulphurous acid gas and a half volume of oxygen gas. He showed further that the compounds of azote and oxygen were composed as follows: protoxide of azote, one volume azote plus one half volume oxygen; deutoxide of azote, one volume of azote plus one volume of oxygen; nitrous acid, one volume of azote plus two volumes of oxygen. He showed also that when the two gases after combining remained in the gaseous state, the diminution of volume was either 0, or 1/3, or 1/2. The constancy of these proportions left no doubt that the combinations of all gaseous bodies were definite. The theory of Dalton applied to them with great facility. We have only to consider a volume of gas to represent an atom, and then we see that in gases one atom of one gas combines either with one, two, or three atoms of another gas, and never with more. There is, indeed, a difficulty occasioned by the way in which we view the composition of water. If water be composed of one atom of oxygen and one atom of hydrogen, then it follows that a volume of oxygen contains twice as many atoms as a volume of hydrogen. Consequently, if a volume of hydrogen gas represent an atom, half a volume of oxygen gas must represent an atom. Dr. Prout soon after showed that there is an intimate connection between the atomic weight of a gas and its specific gravity. This indeed is obvious at once. I afterwards showed that the specific gravity of a gas is either equal to its atomic weight multiplied by 1.1111, etc., the specific gravity of oxygen gas, or by 0.55555, etc., half the specific gravity of oxygen gas, or by 0.27777, etc., one-fourth of the specific gravity of oxygen gas, these differences depending upon the relative condensation which the gases undergo when their elements unite. The following table exhibits the atoms and specific gravity of these three sets of gases. 1. Specific gravity equals atomic weight times 1.1111. Oxygen gas, atomic weight 1, specific gravity 1.1111. Fluorosilicic acid, atomic weight 3.25, specific gravity 3.6111. 2. Specific gravity equals atomic weight times 0.5555, etc. Hydrogen, atomic weight 0.125, specific gravity 0.0694. Azotic, atomic weight 1.75, specific gravity 0.0722. Chlorine, atomic weight 4.5, specific gravity 2.5. Carbon vapor, atomic weight 0.75, specific gravity 0.4166. Phosphorus vapor, atomic weight 2, specific gravity 1.1111. Sulfur vapor, atomic weight 2, specific gravity 1.1111. Tellurium vapor, atomic weight 4, specific gravity 2.2222. Arsenic vapor, atomic weight 4.75, specific gravity 2.6388. Selenium vapor, atomic weight 5, specific gravity 2.7777. Bromine vapor, atomic weight 10, specific gravity 5.5555. Iodine vapor, atomic weight 15.75, specific gravity 8.75. Steam, atomic weight 1.125, specific gravity 0.625. Carbonic oxide gas, atomic weight 1.75, specific gravity 0.9722. Carbonic acid, atomic weight 2.75, specific gravity 1.5277. Protoxide of azote, atomic weight 2.75, specific gravity 1.5277. Nitric acid vapor, atomic weight 6.75, specific gravity 3.75. Sulfurous acid, atomic weight 4, specific gravity 2.2222. Sulfuric acid vapor, atomic weight 5, specific gravity 2.7777. Cyanogen, atomic weight 3.25, specific gravity 1.8055. Fluoboric acid, atomic weight 4.25, specific gravity 2.3611. Bisulfurate of carbon, atomic weight 4.75, specific gravity 2.6388. Chlorocarbonic acid, atomic weight 6.25, specific gravity 3.4722. 3. Specific gravity equals atomic weight times 0.27777, etc. Ammoniacal gas, atomic weight 2.125, specific gravity 0.59027. Hydrocyanic acid, atomic weight 3.375, specific gravity 0.9375. Deutoxide of azote, atomic weight 3.75, specific gravity 1.0416. Muriatic acid, atomic weight 4.625, specific gravity 1.28472. Hydrobromic acid, atomic weight 10.125, specific gravity 2.8125. Hydriodic acid, atomic weight 15.875, specific gravity 4.40973. When Professor Berzelius of Stockholm thought of writing his elementary treatise on chemistry, the first volume of which was published in the year 1808, he prepared himself for the task by reading several chemical works which do not commonly fall under the eyes of those who compose elementary treatises. Among other books he read the Stoichiometry of Richter, and was much struck with the explanations there given of the composition of salts, and the precipitation of metals by each other. It followed from the researches of Richter that if we were in possession of good analysis of certain salts, we might by means of them calculate with accuracy the composition of all the rest. Berzelius formed immediately the project of analyzing a series of salts with the most minute attention to accuracy. While employed in putting this project in execution, Davy discovered the constituents of the alkalis and earths, Mr. Dalton gave to the world his notions respecting the atomic theory, and Gay-Lussac made known his theory of volumes. This greatly enlarged his views as he proceeded, and induced him to embrace a much wider field than he had originally contemplated. His first analyses were unsatisfactory, but by repeating them and varying the methods, he detected errors, improved his processes, and finally obtained results which agreed exceedingly well with the theoretical calculations. These laborious investigations occupied him several years. The first outline of his experiments appeared in the 77th volume of the Annales de Chimie in 1811, in a letter addressed by Berzelius to Berthollet. In this letter he gives an account of his methods of analysis together with the composition of 47 compound bodies. He shows that when a metallic protosulphuret is converted into a sulphate, the sulphate is neutral; that an atom of sulphur is twice as heavy as an atom of oxygen, and that when sulphide of barytes is converted into sulphate, the sulphide is neutral, there being no excess either of acid or base. From these and many other important facts he finally draws this conclusion: quote, "In a compound formed by the union of two oxides, the one which, when decomposed by the galvanic battery, attaches itself to the positive pole, the acid for example, contains 2, 3, 4, 5, etc., times as much oxygen as the one which attaches itself to the negative pole, the alkali, earth, or metallic oxide." Berzelius's essay itself appeared in the third volume of the Afhandlingar in 1810. It was almost immediately translated into German and published by Gilbert in his Annalen der Physik. But no English translation has ever appeared, the editors of our periodical works being in general unacquainted with the German and other northern languages. In 1815 Berzelius applied the atomic theory to the mineral kingdom, and showed with infinite ingenuity that minerals are chemical compounds in definite or atomic proportions, and by far the greater number of them combinations of acids and bases. He applied the theory also to the vegetable kingdom by analyzing several of the vegetable acids and showing their atomic constitution. But here a difficulty occurs, which in the present state of our knowledge we are unable to surmount. There are two acids, the acetic and succinic, that are composed of exactly the same number and same kind of atoms, and whose atomic weight is 6.25. The constituents of these two acids are 2 atoms hydrogen, atomic weight 0.25, 4 atoms carbon, atomic weight 3, 3 atoms oxygen, atomic weight 3. Total atomic weight 6.25. So that they consist of 9 atoms. Now, as these two acids are composed of the same number and the same kind of atoms, one would expect that their properties should be the same, but this is not the case. Acetic acid has a strong and aromatic smell, succinic acid has no smell whatever. Acetic acid is so soluble in water that it is difficult to obtain it in crystals, and it cannot be procured in a separate state free from water, for the crystals of acetic acid are composed of 1 atom of acid and 1 atom of water united together. But succinic acid is not only easily obtained free from water, but it is not even very soluble in that liquid. The nature of the salts formed by these two acids is quite different. The action of heat upon each is quite different. The specific gravity of each differs. In short, all their properties exhibit a striking contrast. Now, how are we to account for this? Undoubtedly by the different ways in which the atoms are arranged in each. If the electrochemical theory of combination be correct, we can only view atoms as combining 2 by 2. A substance, then, containing 9 atoms, such as acetic acid, must be of a very complex nature. And it is obvious enough that these 9 atoms might arrange themselves in a great variety of binary compounds, and the way in which these binary compounds unite may, and doubtless does, produce a considerable effect upon the nature of the compound formed. Thus, if we make use of Mr. Dalton's symbols to represent the atoms of hydrogen, carbon, and oxygen, we may suppose the 9 atoms constituting acetic and succinic acid to be arranged thus in a 3 by 3 matrix. First row, dotted circle, black disk, dotted circle. Second row, circle, circle, circle. Third row, black disk, black disk, black disk. Or thus in a 3 by 3 matrix. First row, black disk, dotted circle, black disk. Second row, circle, circle, circle. Third row, black disk, dotted circle, black disk. Now, undoubtedly these two arrangements would produce a great change in the nature of the compound. There is something in the vegetable acids quite different from the acids of the inorganic kingdom, and which would lead to the suspicion that the electrochemical theory will not apply to them as it does to the others. In the acids of carbon, sulfur, phosphorus, selenium, etc., we find one atom of a positive substance united to one, two, or three of a negative substance. We are not surprised, therefore, to find the acid formed negative also. But in acetic and succinic acids we find every atom of oxygen united with two electropositive atoms. The wonder then is that the acid should not only retain its electronegative properties, but that it should possess considerable power as an acid. In benzoic acid, for every atom of oxygen, there are present no fewer than 7 electropositive atoms. Berzelius has returned to these analytical experiments repeatedly, so that at last he has brought his results very near the truth indeed. It is to his labours chiefly that the great progress which the atomic theory has made is owing. In the year 1814 there appeared in the Philosophical Transactions a description of a synoptical scale of chemical equivalents by Dr. Wollaston. In this paper we have the equivalents or atomic weights of 73 different bodies, deduced chiefly from a sagacious comparison of the previous analytical experiments of others, and almost all of them very near the truth. These numbers are laid down upon a sliding rule, by means of a table of logarithms, and over against them the names of the substances. By means of this rule a great many important questions respecting the substances contained on the scale may be solved. Hence the scale is of great advantage to the practical chemist. It gives, by bare inspection, the constituents of all the salts contained on it, the quantity of any other ingredient necessary to decompose any salt, and the weights of the new constituents that will be formed. The contrivance of this scale, therefore, may be considered as an important addition to the atomic theory. It rendered that theory everywhere familiar to all those who employed it. To it chiefly we owe, I believe, the currency of that theory in Great Britain, and the prevalence of the mode which Dr. Wollaston introduced, namely, of representing the atom of oxygen by unity, or at least by 10, which comes nearly to the same thing. Perhaps the reader will excuse me if to the preceding historical details I add a few words to make him acquainted with my own attempts to render the atomic theory more accurate by new and careful analysis. I shall not say anything respecting the experiments which I undertook to determine the specific gravity of the gases, though they were performed with much care and at a considerable expense, and though I believe the results obtained approached accuracy as nearly as the present state of chemical apparatus enables us to go. In the year 1819 I began a set of experiments to determine the exact composition of the salts containing the different elementary bodies by means of double decomposition, as was done by Wenzel, conceiving that in that way the results would be very near the truth, while the experiments would be more easily made. My mode was to dissolve, for example, a certain weight of muriate of barytes in distilled water, and then to ascertain by repeated trials what weight of sulphate of soda must be added to precipitate the whole of the barytes without leaving any surplus of sulphuric acid in the liquid. To determine this I put into a watch-glass a few drops of the filtered liquor consisting of the mixture of solutions of the two salts. To this I added a drop of solution of sulphate of soda. If the liquid remained clear, it was a proof that it contained no sensible quantity of barytes. To another portion of the liquid, also in a watch-glass, I added a drop of muriate of barytes. If there was no precipitate, it was a proof that the liquid contained no sensible quantity of sulphuric acid. If there was a precipitate, on the addition of either of these solutions, it showed that there was an excess of one or other of the salts. I then mixed the two salts in another proportion, and proceeded in this way till I had found two quantities which when mixed exhibited no evidence of the residual liquid containing any sulphuric acid or barytes. I considered these two weights of the salts as the equivalent weights of the salt, or as weights proportional to an integrant particle of each salt. I made no attempt to collect the two new formed salts and to weigh them separately. I published the result of my numerous experiments in 1825 in a work entitled An Attempt to Establish the First Principles of Chemistry by Experiment. The most valuable part of this book is the account of the salts, about 300 of which I subjected to actual analysis. Of these the worst executed are the phosphates, for with respect to them I was sometimes misled by my method of double decomposition. I was not aware at first that in certain cases the proportion of acid in these salts varies, and the phosphate of soda which I employed gave me a wrong number for the atomic weight of phosphoric acid. End of section 66.
Section 67 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 7, of the Present State of Chemistry, Part 1. To finish this history, it will now be proper to lay before the reader a kind of map of the present state of chemistry, that he may be able to judge how much of the science has been already explored, and how much still remains untrodden ground. Leaving out of view light, heat, and electricity, respecting the nature of which only conjectures can be formed, we are at present acquainted with 53 simple bodies, which naturally divide themselves into 3 classes, namely, supporters, acidifiable bases, and alkalifiable bases. The supporters are oxygen, chlorine, bromine, iodine, and fluorine. They are all in a state of negative electricity, for when compounds containing them are decomposed by the voltaic battery, they all attach themselves to the positive pole. They have the property of uniting with every individual belonging to the other 2 classes. When they combine with the acidifiable bases in certain proportions, they constitute acids; when with the alkalifiable bases, alkalis. In certain proportions they constitute neutral bodies, which possess neither the properties of acids or alkalis. The acidifiable bases are 17 in number, namely, hydrogen, azote, carbon, boron, silicon, sulfur, selenium, tellurium, phosphorus, arsenic, antimony, chromium, uranium, molybdenum, tungsten, titanium, columbium. These bodies do not form acids with every supporter or in every proportion, but they constitute the bases of all the known acids, which form a numerous set of bodies, many of which are still imperfectly investigated. And indeed there are a good many of them that may be considered as unknown. These acidifiable bases are electropositive, but they differ in this respect considerably from each other, hydrogen and carbon being 2 of the most powerful, while titanium and columbium have the least energy. Sulfur and selenium, and probably some other bodies belonging to this class, are occasional electronegative bodies, as well as the supporters. Hence, when united to other acidifiable bases, they produce a new class of acids, analogous to those formed by the supporters. These have got the name of sulfur acids, selenium acids, etc. Sulfur forms acids with arsenic, antimony, molybdenum, and tungsten, and doubtless with several other bases. To distinguish such acids from alkaline bases, I have of late made an alteration in the termination of the old word sulphuret, employed to denote the combination of sulfur with a base. Thus, sulphide of arsenic means an acid formed by the union of sulfur and arsenic. Sulphuret of copper means an alkaline body formed by the union of sulfur and copper. The term sulphide implies an acid, the term sulphuret a base. This mode of naming has become necessary, as without it many of these new salts could not be described in an intelligible manner. The same mode will apply to the acid and alkaline compounds of selenium. Thus a selenide is an acid compound, and a selenet
an alkaline compound, into which selenium acts the part of a supporter or electronegative body. The same mode of naming might and doubtless will be extended to all the other similar compounds as soon as it becomes necessary. In order to form a systematic nomenclature, it will speedily be requisite to new model all the old names which denote acids and bases, because unless this is done, the names will become too numerous to be remembered. At present we denote the alkaline bodies formed by the union of manganese and oxygen by the name of oxides of manganese, and the acid compound of oxygen in the same metal by the name of manganesic acid. The word oxide applies to every compound of a base and oxygen, whether neutral or alkaline, but when the compound has acid qualities, this is denoted by adding the syllable "ic" to the name of the base. This mode of naming answered tolerably well as long as the acids and alkalis were all combinations of oxygen with a base. But now that we know the existence of 8 or 10 classes of acids and alkalis, consisting of as many supporters or acidifiable bases united to bases, it is needless to remark how very defective it has become. But this is not the place to dwell longer upon such a subject. The alkalifiable bases are 31 in number, namely, potassium, sodium, lithium, barium, strontium, calcium, magnesium, aluminum, glucinum, yttrium, cerium, zirconium, thorium, iron, manganese, nickel, cobalt, zinc, cadmium, lead, tin, bismuth, copper, mercury, silver, gold, platinum, palladium, rhodium, iridium, osmium. The compounds which these bodies form with oxygen and the other supporters constitute all the alkaline bases, or the substances capable of neutralizing the acids. Some of the acidifiable bases, when united to a certain portion of oxygen, constitute not acids but bases or alkalis. Thus the green oxides of chromium and uranium are alkalis, while, on the other hand, there is a compound of oxygen and manganese which possesses acid properties. In such cases it is always the compound containing the least oxygen which is an alkali, and that containing the most oxygen that is an acid. The opinion at present universally adopted by chemists is, that the ultimate particles of bodies consist of atoms, incapable of further division, and these atoms are of a size almost infinitely small. It can be demonstrated that the size of an atom of lead does not amount to so much as 1/888,492,000,000,000th of a cubic inch. But, notwithstanding this extreme minuteness, each of these atoms possesses a peculiar weight and a peculiar bulk which distinguish it from the atoms of every other body. We cannot determine the absolute weight of any of them, but merely the relative weights, and this is done by ascertaining the relative proportions in which they unite. When two bodies unite in only one proportion, it is reasonable to conclude that the compound consists of one atom of the one body, united to one atom of the other. Thus, oxide of bismuth is a compound of 1 oxygen and 9 bismuth, and, as the bodies unite in no other proportion, we conclude that an atom of bismuth is 9 times as heavy as an atom of oxygen. It is in this way that the atomic weights of the simple bodies have been attempted to be determined. The following table exhibits these weights referred to oxygen as unity, and deducted from the best data at present in our possession. Oxygen, atomic weight 1. Fluorine, atomic weight 2.25. Chlorine, atomic weight 4.5. Bromine, atomic weight 10. Calcium, atomic weight 2.5. Magnesium, atomic weight 1.5. Aluminum, atomic weight 1.25. Glucinum, atomic weight 2.25. Iodine, atomic weight 15.75. Hydrogen, atomic weight 0.125. Azote, atomic weight 1.75. Carbon, atomic weight 0.75. Boron, atomic weight 1. Silicon, atomic weight 1. Phosphorus, atomic weight 2. Sulfur, atomic weight 2. Selenium, atomic weight 5. Tellurium, atomic weight 4. Arsenic, atomic weight 4.75. Antimony, atomic weight 8. chromium, atomic weight 4, uranium, atomic weight 26, molybdenum, atomic weight 6, tungsten, atomic weight 12.5, titanium, atomic weight 3.25, columbium, atomic weight 22.75, potassium, atomic weight 5, sodium, atomic weight 3, lithium, atomic weight 0.75, barium, atomic weight 8.5, strontium, atomic weight 5.5, yttrium, atomic weight 4.25, zirconium, atomic weight 5, thorium, atomic weight 7.5, iron, atomic weight 3.5, manganese, atomic weight 3.5, nickel, atomic weight 3.25, cobalt, atomic weight 3.25, cerium, atomic weight 6.25, zinc, atomic weight 4.25, cadmium, atomic weight 7, lead, atomic weight 13, tin, atomic weight 7.25, bismuth, atomic weight 9, copper, atomic weight 4, mercury, atomic weight 12.5, silver, atomic weight 13.75, gold, atomic weight 12.5, platinum, atomic weight 12, palladium, atomic weight 6.75, rhodium, atomic weight 6.75, iridium, atomic weight 12.25, osmium, atomic weight 12.5. The atomic weights of these bodies, divided by their specific gravity, ought to give us the comparative size of the atoms. The following table, constructed in this way, exhibits the relative bulks of these atoms which belong to bodies whose specific gravity is known. Carbon, volume 1. Nickel and cobalt, volume 1.75. Manganese, copper, and iron, volume 2. Platinum and palladium, volume 2.6. Zinc, volume 2.75. Rhodium, tellurium, chromium, volume 3. Molybdenum, volume 3.25. Silica and titanium, volume 3.5. Cadmium, volume 3.75. Arsenic, phosphorus, and antimony, volume 4. Tungsten, bismuth, and mercury, volume 4.25. Tin and sulfur, volume 4.66. Selenium and lead, volume 5.4. Gold, silver, and osmium, volume 6. Oxygen, hydrogen, azote, and chlorine, volume 9.33. Uranium, volume 13.5. Columbium and sodium, volume 14. Bromine, volume 15.75. Iodine, volume 24. Potassium, volume 27. We have no data to enable us to determine the shape of these atoms. The most generally received opinion is, that they are spheres or spheroids, though there are difficulties in the way of admitting such an opinion, in the present state of our knowledge, nearly insurmountable. The probability is that all the supporters have the property of uniting with all the bases, in at least 3 proportions. But by far the greater number of these compounds still remain unknown. The greatest progress has been made in our knowledge of the compounds of oxygen, but even there much remains to be investigated, owing in a great measure to the scarcity of several of the bases which prevent chemists from subjecting them to the requisite number of experiments. The compounds of chlorine have also been a good deal investigated, but bromine and iodine have been known for so short a time that chemists have not yet had leisure to contrive the requisite processes for causing them to unite with bases. The acids at present known amount to a very great number. The oxygen acids have been most investigated. They consist of 2 sets, those consisting of oxygen united to a single base, and those in which it is united to two or more bases. The last set are derived from the animal and vegetable kingdoms. It does not seem likely that the electrochemical theory of Davy applies to them. They must derive their acid qualities from some electric principle not yet adverted to, for, from Davy's experiments, there can be little doubt that they are electronegative as well as the other acids. The acid compounds of oxygen and a single base are about 32 in number. Their names are hyponitrous acid, nitrous acid, nitric acid, carbonic acid, oxalic acid, boracic acid, silicic acid, hypophosphorus acid, phosphorus acid, phosphoric acid, hyposulfurous acid, subsulfurous acid, sulfurous acid, sulfuric acid, hyposulfuric acid, selenious acid, selenic acid, arsenious acid, arsenic acid, antimonious acid, antimonic acid, oxide of tellurium, chromic acid, uranic acid, molybdic acid, tungstic acid, titanic acid, columbic acid, manganesic acid, chloric acid, bromide acid, iodic acid. The acids from vegetables and animal kingdoms, not reckoning a considerable number which consist of combinations of sulfuric acid with a vegetable or an animal body, amount to about 43. So at present we are acquainted with very nearly 80 acids which contain oxygen as an essential constituent. The other classes of acids have been but imperfectly investigated. Hydrogen enters into combination and forms powerful acids with all the supporters except oxygen. These have been called hydroacids. They are muriatic acid or hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrofluoric acid or fluoric acid, hydrosulfuric acid, hydroselenic acid, hydrotelluric acid. These constitute, such of them as can be procured, some of the most useful and most powerful chemical reagents in use. There is also another compound body, cyanogen, similar in its characteristics to a supporter. It also forms various acids by uniting to hydrogen, chlorine, oxygen, sulfur, etc. Thus we have hydrocyanic acid, chlorocyanic acid, cyanic acid, sulfocyanic acid, etc. We know also fluosilicic acid and fluoboric acids. If to these we add fulminic acid and the various sulfur acids already investigated, we may state without risk of any excess that the number of acids at present known to chemists and capable of uniting to bases exceeds 100. The number of alkaline bases is not perhaps so great, but it must even at present exceed 70, and it will certainly be much augmented when chemists turn their attention to the subject. Now every base is capable of uniting with almost every acid, in all probability in at least 3 different proportions, so that the number of salts which they are capable of forming cannot be fewer than 21,000. Now scarcely 1,000 of these are at present known, or have been investigated with tolerable precision. What a prodigious field of investigation remains to be traversed must be obvious to the most careless reader. In such a number of salts, how many remain unknown that might be applied to useful purposes, either in medicine, or as mordants, or dyes, etc.? How much, in all probability, will be added to the resources of mankind by such investigations need not be observed. End of section 67. Section 68 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 7, of the Present State of Chemistry, Part 2. The animal and vegetable kingdoms present a still more tempting field of investigation. Animal and vegetable substances may be arranged under 3 classes: acids, alkalis, and neutrals. The class of acids presents many substances of great utility, either in the arts or for seasoning food. The alkalis contain almost all the powerful medicines that are drawn from the vegetable kingdom. The neutral bodies are important as articles of food, and are applied, too, to many other purposes of first-rate utility. All these bodies are composed, chiefly at least, of hydrogen, carbon, oxygen, and azote, substances easily procured abundantly at a cheap rate. Should chemists, in consequence of the knowledge acquired by future investigations, ever arrive at the knowledge of the mode of forming these principles from their elements at a cheap rate, the prodigious change which such a discovery would make upon the state of society must be at once evident. Mankind would be, in some measure, independent of climate and situation. Everything could be produced at pleasure in every part of the earth, and the inhabitants of the warmer regions would no longer be the exclusive possessors of comforts and conveniences to which those in less favored regions of the earth are strangers. Let the science advance for another century with the same rapidity that it has done during the last 50 years, and it will produce effects upon society of which the present race can form no adequate idea. Even already some of these effects are beginning to develop themselves. Our streets are now illuminated with gas drawn from the bowels of the earth, and the failure of the Greenland fishery during an unfortunate season like the last no longer fills us with dismay. What a change has been produced in the country by the introduction of steamboats, and what a still greater improvement is at present in progress, when steam carriages and railroads are gradually taking the place of horses and common roads. Distances will soon be reduced to one half of what they are at present, while the diminished force and increased rate of conveyance will contribute essentially to lower the rest of our manufactures, and enable us to enter into a successful competition with other nations. I must say a few words upon the application of chemistry to physiology before concluding this imperfect sketch of the present state of the science. The only functions of the living body upon which chemistry is calculated to throw light are the processes of digestion, assimilation, and secretion. The nervous system is regulated by laws seemingly quite unconnected with chemistry and mechanics, and in the present state of our knowledge, perfectly inscrutable. Even in the process of digestion, assimilation, and secretion, the nervous influence is important and essential. Hence, even of these functions, our notions are necessarily very imperfect, but the application of chemistry supplies us with some data at least, which are too important to be altogether neglected. The food of man consists of solids and liquids, and the quantity of each taken by different individuals is so various that no general average can be struck. I think that the drink will in most cases exceed the solid food in nearly the proportion of 4 to 3, but the solid food itself contains not less than 7/10 of its weight of water. In reality, then, the quantity of liquid taken into the stomach is to that of solid matter as 10 to 1. The food is introduced into the mouth, comminuted by the teeth, and mixed up with the saliva into a kind of pulp. The saliva is a liquid expressly secreted for this purpose, and the quantity certainly does not fall short of 10 ounces in the 24 hours. Indeed, I believe it exceeds that amount. It is a liquid almost as colorless as water, slightly viscid, and without taste or smell. It contains about 3/1000ths of its weight of a peculiar matter, which is transparent and soluble in water. It has suspended in it about 1.41 of its weight of mucus, and in solution about 2.81 of common salt and soda. The rest is water. From the mouth, the food passes into the stomach, where it is changed to a kind of pap called chyme. The nature of the food can readily be distinguished after mastication, but when converted into chyme it loses its characteristic properties. This conversion is produced by the action of the 8th pair of nerves, which are partly distributed on the stomach, for when they are cut the process is stopped. But if a current of electricity, by means of a small voltaic battery, be made to pass through the stomach, the process goes on as usual. Hence the process is obviously connected with the action of electricity. A current of electricity, by means of the nerves, seems to pass through the food in the stomach, and to decompose the common salt which is always mixed with the food. The muriatic acid is set at liberty and dissolves the food, for chyme seems to be simply a solution of the food in muriatic acid. The chyme passes through the pyloric orifice of the stomach into the duodenum, the first of the small intestines, where it is mixed with 2 liquids, the bile, secreted by the liver, and the pancreatic juice, secreted by the pancreas, and both discharged into the duodenum to assist in the further digestion of the food. The chyme is always acid, but after it has been mixed with the bile the acidity disappears. The characteristic constituent of the bile is a bitter tasted substance called picromel, which has the property of combining with muriatic acid and forming with it an insoluble compound. The pancreatic juice also contains a peculiar matter to which chlorine communicates a red color. The use of the pancreatic juice is not understood. During the passage of the chyme through the small intestines it is gradually separated into two substances, the chyle, which is absorbed by the lacteals, and the excrementitious matter, which is gradually protruded along the great intestines and at last evacuated. The chyle, in animals that live on vegetable food, is semi-transparent, colorless, and without smell, but in those that use animal food is white, slightly similar to milk, with a tint of pink. When left exposed to the air it coagulates as blood does. The coagulum is fibrin. The liquid portion contains albumin and the usual salts that exist in the blood. Thus the chyle contains two of the constituents of blood, namely albumin, which perhaps may be formed in the stomach, and fibrin, which is formed in the small intestines. It still wants the third constituent of blood, namely the red globules. From the lacteals the chyle passes into the thoracic duct, thence into the left subclavian vein, by which it is conveyed to the heart. From the heart it passes into the lungs, during its circulation through which the red globules are supposed to be formed, though of this we have no direct evidence. The lungs are the organs of breathing, a function so necessary to hot-blooded animals that it cannot be suspended even for a few minutes without occasioning death. In general, about 20 inspirations and as many expirations are made in a minute. The quantity of air which the lungs of an ordinary sized man can contain, when fully distended, is about 300 cubic inches. But the quantity actually drawn in and thrown out during ordinary inspirations and expirations amounts to about 16 cubic inches each time. In ordinary cases the volume of air is not so sensibly altered by respiration, but it undergoes two remarkable changes. A portion of its oxygen is converted into carbonic acid gas, and the air expired is saturated with humidity at the temperature of 98 degrees. The moisture thus given out amounts to about 7 ounces troy, or very little short of half an avoirdupois pound. The quantity of carbonic acid formed varies much in different individuals and also at different times in the day, being a maximum at 12 o'clock at noon and a minimum at midnight. Perhaps 4 of carbonic acid in every 100 cubic inches of air breathed may be a tolerable approach to the truth, that is to say that every 6 respirations produce 4 cubic inches of carbonic acid. This would amount to 19,200 cubic inches in 24 hours. Now the weight of 19,200 cubic inches of carbonic acid gas is 18.98 troy ounces, which contain rather more than 5 troy ounces of carbon. These alterations in the air are doubtless connected with corresponding alterations in the blood, though with this respect to the specific nature of these alterations we are ignorant. But there are two purposes which respiration answers, the nature of which we can understand, and which seem to afford a reason why it cannot be interrupted without death. It serves to develop the animal heat, which is so essential to the continuance of life, and it gives the blood the property of stimulating the heart, without which it would cease to contract, and put an end to the circulation of the blood. This stimulating property is connected with the scarlet color which the blood acquires during respiration, for when the scarlet color disappears the blood ceases to stimulate the heart. The temperature of the human body in a state of health is about 98 degrees in this country, but in the torrid zone it is a little higher. Now, as we are almost always surrounded by a medium colder than 98 degrees, it is obvious that the human body is constantly giving out heat, so that if it did not possess the power of generating heat it is clear that its temperature would soon sink as low as that of the surrounding atmosphere. It is now generally understood that common combustion is nothing else than the union of oxygen gas with the burning body. The substances commonly employed as combustibles are composed chiefly of carbon and hydrogen. The heat evolved is proportional to the oxygen gas which unites with these bodies. And it has been ascertained that every 3 3/4 cubic inches of oxygen which combine with carbon or hydrogen occasion the evolution of 1 degree of heat. There are reasons for believing that not only carbon but also hydrogen unite with oxygen in the lungs, and that therefore both carbonic acid and water are formed in that organ. And from that late experiment of M. Dupré it is clear that the heat evolved in a given time by a hot-blooded animal is very little short of the heat that would be evolved by the combustion of the same weight of carbon and hydrogen consumed during that time in the lungs. Hence it follows that the heat evolved in the lungs is the consequence of the union of the oxygen of the air with the carbon and hydrogen of the blood, and that the process is perfectly analogous to combustion. The specific heat of arterial blood is somewhat greater than that of venous blood. Hence the reason why the temperature of the lungs does not become higher by breathing, and why the temperature of the other parts of the body are kept up by the circulation. The blood seems to be completed in the kidneys. It consists essentially of albumin, fibrin, and the red globules, with a considerable quantity of water, holding in a solution certain salts which are found equally in all the animal fluids. It is employed during the circulation in supplying the waste of the system, and in being manufactured into all the different secretions necessary for the various functions of the living body. By these different applications, if we cannot doubt that its nature undergoes very great changes, and that it would soon become unfit for the purposes of the living body were there not an organ expressly destined to withdraw the redundant and useless portions of that liquid, and to restore it to the same state that it was when it left the lungs. These organs are the kidneys, through which all the blood passes, and during its circulation through which the urine is separated from it and withdrawn altogether from the body. These organs are as necessary for the continuance of life as the lungs themselves. Accordingly, when they are diseased or destroyed, death very speedily ensues. The quantity of urine voided daily is very various, though doubtless it bears a close relation to that of the drink. It is nearly but not quite equal to the amount of the drink, and it is seldom, in persons who enjoy health, less than 2 pounds avoirdupois in 24 hours. Urine is one of the most complex substances in the animal kingdom, containing a much greater number of ingredients than are to be found in the blood from which it is secreted. The water in urine voided daily amounts to about 1.866 pounds. The blood contains no acid except a little muriatic. But in urine we find sulfuric, phosphoric, and uric acids, and sometimes oxalic and nitric acids, and perhaps also some others. The quantity of sulfuric acid may be about 48 grains daily, containing 19 grains of sulfur; the phosphoric acid about 33 grains, containing about 14 grains of phosphorus; the uric acid may amount to 14 grains. These acids are in combination with potash or soda or ammonia, and also with a very little lime and magnesia. The common salt evacuated daily in the urine amounts to about 62 grains. The urea, a peculiar substance found only in the urine, amounts to perhaps as much as 420 grains. It would appear from these facts that the kidneys possess the property of converting the sulfur and phosphorus, which are known to exist in the blood, into acids, and likewise of forming other acids and urea. The quantity of water thrown out of the system by the urine and lungs is scarcely equal to the amount of liquid daily consumed along with the food. But there is another organ which has been ascertained to throw out likewise a considerable quantity of moisture. This organ is the skin, and the process is called perspiration. From the experiments of Lavoisier and Seguin, it appears that the quantity of moisture given out daily by the skin amounts to 54.89 ounces. This, added to the quantity evolved from the lungs and the urine, considerably exceeds the weight of liquid taken with the food, and leaves no doubt that water as well as carbonic acid must be formed in the lungs during respiration. Such is an imperfect sketch of the present state of that department of physiology which is most intimately connected with chemistry. It is amply sufficient, short as it is, to satisfy the most careless observer how little progress has hitherto been made in these investigations, and what an extensive field remains yet to be traversed by future observers. End of Section 68. End of the History of Chemistry by Thomas Thomson.